Welcome to Python for Data Science Complete live lessons. My name is 𝑁𝒂𝒓𝒔 and I'll be your instructor for this course. I'm a machine learning lecturer at Northwestern's Graduate Data Science program and UC Davis Graduate School of Management's MSBA program, and I've held business roles including CTO, General Manager, Consulting CTO, and Cloud Architect. I'm the author of the book Pragmatic AI, An Introduction to Cloud-Based Machine Learning, as well as many other technical articles and books.
My name is Kennedy Behrman, and I will also be an instructor for this course. I'm a professional consultant specializing in architecting and implementing cloud solutions for early-stage startups. I'm experienced in data engineering, data science, cloud solutions, engineering management, and have acted as a technical editor on numerous Python and data science-related publications.
As the founders of Pragmatic AI Labs, we consult with startups and other companies on machine learning, AI, and cloud architecture. We're excited that you've decided to join us in these Python for Data Science lessons. We will be helping you to learn Python for data science one step at a time. If you're just getting started in doing Python for data science, don't worry. These live lessons required are aimed at beginners just like you. Let's go over the lesson plan.
In Lesson 1, you'll learn about the history of Python and data science.
Lesson 2 introduces Colab Notebooks, a powerful new collaboration tool for data scientists.
Lesson 3 introduces the basic concepts in Python.
Lesson 4 explains strings and string formatting methods.
Lesson 5 covers Python data structures, including NumPy and Pandas.
Lesson 6 introduces common data conversion recipes for data science projects.
Lesson 7 covers execution control patterns, including loops and exceptions.
Lesson 8 explains functions and how they're important for data science problems.
In Lesson 9, we introduce common data science libraries like TensorFlow, Plotly, and Seaborn.
Lesson 10 explains functional programming and shows how it's a critical skill for data science.
Lesson 11 introduces the concept of lazy evaluation.
Lesson 12 covers pattern matching and text processing techniques.
Lesson 13 covers sorting in Python and the creation of custom sort functions.
Lesson 14 introduces core I/O concepts like concurrency and file handling.
Lesson 15 explains how to market yourself as a data scientist and share your work on platforms like Kaggle and GitHub.
Finally, in Lesson 16, you learn to apply real-world data science problems in case studies. So thanks again for joining us in this live lesson. We hope you enjoy learning the material as much as we enjoyed making it. In this lesson, you will learn to have a high-level overview of Python as it applies to data science. Lessons include the history of Python and data science and course goals. You learn how to create a machine learning data pipeline. You learn the goals of the course, and you also learn about the future of Python. Let's get started. The history of the Python language and data science is a really interesting history. The Python language itself first appeared in 1990. Let's go back a little bit and think about that era. This is when the internet wasn't really a thing. www wasn't actually a place where you could go and type in yahoo.com. There was no concept of a multi-processor machine. We're also, in that period, it was the period of peak Moore's law. So what that meant is, and if you look at this diagram here, it was a constant year-by-year change in the processor size. So you would have one year there would be a 25 megahertz processor. The next year, it would be 45 megahertz. You have this constant improvement. And so when the language was created, really there wasn't a thought probably for the creator of the language that they would need to do a high-level concurrency or be concurrency first. So really it's also an interesting accident that Python has had some of the success that it's had. So if we look at the language popularity in the last 30 years here, one of the things that we can look at is that C and C++ in 1989 were the most popular languages, right? So this is also informs a little bit about what was happening. Python wasn't even on the map. And then if you look at the Java era, you can see that Java really around 2004 here became the dominant language. And so this was a higher level language where you didn't have to worry about managing memory, and it had a huge run, and it's still a very, very popular language. And you look at Python, it was also starting to make some popularity changes, and it was becoming very popular. But then it's gotten better and better and better in terms of popularity. So now we're at 2019, and it's number 4. So what this is really telling us is that there is a need for this high-level language, and there's a need for something that allows you to think, and then your thoughts become code. And as I was mentioning here, Python has really been an accidental success, and a lot of the history of innovation is like this, where there was an accident, several things converged together, and those accidents actually created something that is now a dominant technology. One of the things that we mentioned was Python itself is not optimized for concurrency, so you don't want to do multi-threaded programming in Python. Also, Python is optimized for a programmer. It's not optimized for the machine like C or C++. And it's also best when it's used on top of a high-performance platform. So a good example is AWS Lambda. So the AWS ecosystem is almost like an operating system. And AWS Lambda allows you to do massively highly concurrent programming, and you can do it in Python, and you don't have to manage that concurrency yourself. The same with NumPy. NumPy allows you to do high performance Python computing where you're actually converting things right down to machine code. And then TensorFlow is built by some of the smartest people at Google, and it's constantly being improved, but underneath the hood, it's highly optimized C++. So this is really the takeaway, is that in Python, you don't want to be doing these low-level things. You want to let the experts do it. The history of data science in particular has an interesting footnote with IPython. IPython is the precursor to Jupyter. It's really the core technology that Jupyter Notebook has been built on, and it was released in 2006. A little bit of a footnote here is that I wrote the first, or one of the first articles, I think there might have been 1 or 2 other articles around the same time, around 2007. And then subsequently after that, in 2008, I co-authored a book with Jeremy Jones where we also used IPython exclusively throughout. And one of the interesting side notes to that was that at the time there was a little bit of a pushback, and why are you using this IPython technology? And now one of the things that's interesting is that it's really the dominant way that people even think about Python. Some people even think that Python is Jupyter. One of the things that made Jupyter so powerful is that in 2012, there's a grant by the Free Software Foundation, and that really kind of kickstarted this new era of notebooks. And then in 2013, 2015, there's millions in grants from foundations like the Betty and Gordon Moore Foundation. Now, if you look and you fast forward to today, we have Colab, we have SageMaker. Really, Jupyter is the heart of the data science ecosystem in Python. Some of the goals of this course are to really talk about the future of Python and data science, and also prepare new students for some of the things that are important, and also ignore some things that are not important. One of the things I'd like to discuss in the spirit of that is something I call the 3 laws of automation. 1, if it isn't automated, it's broken. 2, be the automation, not the automated. 3, if the automation of a task is being discussed, it will eventually be automated. And I think this is a really big thing that isn't discussed enough in the data science world, is that there are going to be many things that are automated. And an example of this is AutoML. AutoML is a technology that is rapidly being adopted by major cloud vendors, Google, Amazon, Microsoft, and also things like automated feature engineering. And as a new data scientist, one of my recommendations is think about these 3 laws of automation. You want to make sure that you're one of the people that's a part of this automation, and not one of the people that is not thinking the automation will occur. Another thing that's really important is functions are everywhere. And this is really a core concept that is important to understand. It's the building block of data science, machine learning, and AI. And it's about this input, processing, and output pipeline. If we look here, it would be, we have this initial input here. There's the input. Then we have the processing pipeline right here. And then we have the output. And really, this goes on and on and on And there's millions and millions and millions of these types of building blocks that go everywhere inside of a distributed system that's doing deep learning and machine learning. So it's really important to understand this functions are everywhere concept. Colab notebooks are also a huge part of this lesson, and every single lesson that we've talked about is in Colab Notebook. And this is an emerging breakthrough technology. Jupyter, as I discussed, I've been actually writing about for over 12 years now, and really Colab is the culmination of what this Jupyter and IPython technology really can be. And it's the sharpest tool in the shed, so to speak. It's really the technology that is really going to allow you as a newcomer to data science to be the most productive. And what I like the most about Colab Notebooks is it's really about results over purity. So on one hand, maybe you could have a more powerful ecosystem if you did everything yourself, but from a results standpoint, Colab is just a powerful tool. Let's talk about some of the new changes in machine learning and data science that are on the horizon. One of the big changes that's going to happen is that automation of many aspects of machine learning will become pervasive. And I think 2019 in particular is a year that's a very interesting year because there are new technologies that are coming out left and right that show this new future. One of the great technologies that's come out very recently from Uber is something called Ludwig. And here's an example of what Ludwig does, is it actually takes text features, category features, numerical features, binary features, set features, all these features, it combines them, and then it goes through and it creates features for you. It also does many different aspects of AutoML. And so from an open source perspective, this is really a tremendous emerging technology that I think will play a big role in 2019, 2020. Another technology that I'd like to talk about is SageMaker. So SageMaker is also in the spirit of this AutoML and managed machine learning system. I also talk about it in other videos, but what it does is it automates this whole life cycle around machine learning. What many different papers have said and what many people in the industry are saying is that really modeling is such a minuscule part of what happens with data science. Really the end game is, does your model work in production, and actually do you have a pipeline that makes it reproducible, and can you maintain your machine learning system in production? You can see here SageMaker kind of tackles that whole thing. It has the ability to automatically create labels for your data, to have notebook instances that are monitored. It also does things like it has algorithms and training jobs that are all managed inside, where you can distribute, let's say 1,000 node k-means clustering algorithms. And also it has a inference system where it can automatically pick the correct GPU sizing for you and also do A/B testing. So these are all automation aspects of machine learning and data science that are definitely not only here, but they're going to play a bigger role in the future. And also, not to be left out here, Google has a cloud-based AutoML system, and if you look at this, it allows you to do full-scale machine learning on computer vision, natural language processing, also translation. And if we take a look here at how this works, it's actually pretty amazing. You can go through here and actually completely automate a computer vision pipeline and actually train something to predict based on just clicking some buttons and actually going through a wizard. So really, this whole AutoML pipeline and this AutoML system is actually here to stay, and it's not going to be something where it's only going to play a small role. I believe it's going to take a very huge role in data science. And so, once things are automated, it is an important thing to think about is, can you be the automator and actually be on top of this automation and actually use these tools to get even more results and to get quicker feedback? And I think that's really the way to think about automation, is not to fight it, but to embrace it and actually use it to become a more proficient modeler or more proficient practitioner of data science.
In this lesson, we're going to create a production machine learning application. You'll learn to create Colab notebooks, including your first Colab document. Lessons will include managing notebooks and using magic functions. Finally, you will learn about compatibility with traditional Jupyter notebooks. Let's get started.
Okay, let's talk about creating your first Colab document. To begin with, let's start a little bit about Colab itself. It's a hosted Jupyter notebook. It has the ability to do GPU and TPU based computing, and it also has an integration with the Google Docs runtime. So if we look at this Colab environment here, we really have these three main interfaces. You can open up a new notebook, a Python 2 or Python 3 notebook. You can actually upload a notebook, or you can even open a notebook in GitHub, Drive, or again, upload it in their interface. And you can actually go ahead and see this. From here you can see there's new Python 3 notebook, new Python 2 notebook, also open a notebook. And if we go to that open interface, you'll see that I actually can upload from GitHub, I can upload from Google Drive, I can see the recent versions of Colab. I can actually directly talk to Google Drive and import documents just like let's say a Google Doc or a Google spreadsheet. I can actually preview my entire GitHub repository, or I can just go to this upload interface here. Let's again look at some of these key features. There's an iron icon, table of contents, code snippets, and files that I'd like to take a look at. This iron icon here is actually a secret that many people don't know about. If we go to this iron icon, you can see that there's a table of contents that shows all the different aspects of my Colab notebook. It's a really handy way to navigate between the different markdown cells. Another thing that's really powerful about this key feature is that you can actually upload code snippets directly into your Colab notebook. So let's say, for example, if you wanted to figure out how to do some visualizations, well, we could take a snippet here, grab this snippet, and then actually tell this to be inserted directly into our Colab notebook. So here I can actually go through, import this Vega dataset, go ahead and plot this, and get a real good overview of how to use this plotting library without having to go through Google and find the results myself. I also could go through here and look at BigQuery. I could go through here and figure out how to use the Google Cloud Platform. So really this snippets library is really a powerful feature. Another really interesting feature of the iron menu here is this ability to upload files. So if I go here to files and I click upload, I can go down to my desktop here and I can take a CSV file on my desktop and then actually upload this directly into my project. And now if I go through and I type in ls-l, you can see that MLB weight CSV file is now listed there. And so from here, typically what you would do is import pandas as PD, and then I could create a data frame from that uploaded file on my desktop. And then let's go ahead and do a head operation and see what's in the first few rows. There we go. Now one thing to be reminded of as well is that not only can you upload things directly into this file menu, but you can look at some of the sample data that they've actually included inside of there. So there's MNIST training set, there's California housing training set. So there's lots of really powerful capabilities in this iron menu. Let's move on now to another feature of Colab that's very unique, and that's forms. So if we go ahead and look at this example, you can see that if you use this syntax param, what it does is it actually enables you to create this form menu with a drop-down. So I can see I have false, true, right? And these are all defined by the parameters that I've set inside of this param section. Now if I go ahead and set that, and we can see here it's been set to true, if I print this, you can see you selected it's true, and then if I change it to false, and I run that, you can see I've now changed this flag to false. So actually a great way to do surveys or pass data around to somebody that's less technical is to actually use this Colab Forms menu. Another powerful feature of Colab is the ability to upload files directly into Colab. So if we go here and we say from google.colab import files, there's a file dialog box that will actually open up. Here we go. You can see here it says choose files. Again, I'm going to go to that MLB file. I'm going to upload it, and now you can see that it's located directly inside of my workspace. So this is also a great way to pass a notebook to somebody, let them upload their own data, and maybe you do some processing after they've uploaded that data. Another thing that many people don't know about with Colab Notebook is you can also just directly call Python by using this exclamation point here. So if I say exclamation point Python-C, I can actually run just raw Python code by stringing together snippets. So sometimes this can actually be a really handy feature if you're not aware of it. Obviously, you can run other commands as well by using this exclamation point. So I can say ls-l. I can also go through here and install software like you see below. We'll get into that in a second. Another thing to be aware of is you also can capture input to a program. So if I say import sys-argv, I also could actually capture input as well. So I can do some of the similar things that I would do in a Python script. Let's talk a little bit about this GitHub integration. So one really interesting thing about Colab is that if you look at this notebook that we're working on right here, the path is github.com PAIML, Python for Data Science. But if I load in front of it this URL, and I put colab.research.google.com in front, I actually can browse this notebook and directly load it into Colab. And you also can go through and browse GitHub repositories. So we go ahead and look at this. This would actually give me access to every single repository in GitHub. Or if I go back here, I could actually look at just my own organization's repository or my own organization's repos. So this is a really powerful feature. Another thing to point out is that you can also use this URL, and you can actually put this in your GitHub project. And if we go ahead and click on this, you can see it also gives you the ability to directly open up a notebook. So there's some really great GitHub integrations that really make it easy to work with Colab notebooks. Now, another thing I want to point out is that you can also save directly to a GitHub repository, and you can also save directly to a gist. So let's go ahead and do that. So if I go here and I say File, Save a Copy in GitHub, it'll actually give me the name of the file, and then it'll actually ask me which repository I'd like to save it to. So I'm going to go ahead and save to this Python directory. I'm going to say create in this location, and then I can go ahead and actually save this file. Let's go ahead and do that. So now that we actually go to this copy to GitHub dialog, I'm going to go ahead and say OK. And what it'll do is it'll actually take this notebook, do a commit on my behalf to a GitHub repository, and actually save directly into GitHub. This is a really powerful feature because it allows you to have version control of your Colab notebooks. Now if I click on this link, it gets me right back to where I started again. So really powerful workflow that you should be aware of. The final thing that you can do with GitHub integration is you can also save it as a gist. So I'm going to go ahead and save a copy as a GitHub gist. Here we go. And what's interesting about this is that it'll actually go through and directly create a gist for me. So if I go to gist, here we go, and I look at the gist that I've got created, I can see that lesson 2 was created, and now I can actually share this snippet as a gist. So it's possible that I don't want to save this to a repository in GitHub. I just want to save some kind of a snippet and actually share it with somebody else. Well, this is a great way to do it. I can go ahead and take this gist, share it with somebody, and share some idea, and also have that same open in Colab link. So really powerful workflow to be aware of. Let's talk about managing Colab documents as well. So as you can see, just from the very basic menu of Colab, there's some really powerful workflows that you can do with GitHub in particular. And one thing I would definitely recommend is that if you are using Colab Notebook, that you consider saving to GitHub and you consider saving to gist. There's a really powerful workflow that will save you a lot of time. Let's talk a little bit about managing Colab documents. One of the really powerful things you can do is mount the Google Drive inside of Colab. This takes care of a lot of the problems that you would typically have in a data science project, because you can put, let's say, a terabyte of data inside of the Google Drive, mount it, and then have access to that data inside of your data science project. So to do that, you would say from google.colab import drive, mount the drive, and here I actually say force remount true. Let's go ahead and do this. It's going to ask me for an authorization code. I'm going to go ahead and give it my authorization code here. And when I go back to this other screen, I'll go ahead and paste this in. And now I'm able to actually mount my Google Drive and get access to the resources that are included. And a really interesting thing to do is to actually load in API keys from, let's say, Google, AWS, or Kaggle. In this case, I'm going to go ahead and list what's inside of there. You can see I have a Kaggle JSON file, a credentials file for AWS, and a config file. So let's go ahead and look at this API key for AWS. You can see that in order to use it, I would CP those resources into my Google Drive first, and then once I have access to it, I can go ahead and install 𝑑𝒚𝒕𝒉𝒐𝒏. So here we go, 𝑑𝒚𝒕𝒉𝒐𝒏 is installed, and now what I can do is I can actually go through and copy that location into a tilde.aws credentials directory. So now I actually have access to call AWS inside of my Colab notebook. Now let's go ahead and test it. What I'm going to do is I'm going to import 𝑑𝒚𝒕𝒉𝒐𝒏. I'm going to make an instance of comprehend, which is the natural language processing API, and then I'm going to put a text message here that says there's smoke in San Francisco and it makes me angry. Now the comprehend API goes ahead and it detects it, and it shows me that that's a negative sentiment, and it gives me a breakdown. So this is a really powerful feature that you may not be aware of. That's a great way to interact with the AWS API. Now let's go ahead and look at a similar formula for interacting with Kaggle. A lot of times some users will be really comfortable using Kaggle, and there's lots of good things about Kaggle, but oftentimes you may want to actually take some of that data and manipulate it in your own project or your own notebook. So let's go ahead and take a look at how you could do that. So here's a Kaggle recipe where first you would mount your drive. Since I've already mounted it, I won't do that. I'm going to go ahead and list inside and make sure that I see the Kaggle JSON file. This gives me access to the Kaggle API. Now let's go ahead and do a list. You can see that credential file is there. Now let's go ahead and wire up Kaggle. So in order to get access to Kaggle and use those API keys, it's kind of a similar process as what we did with AWS. First, I'm going to install the Kaggle API. Then I'm going to make a directory that is tilde.kaggle. And then I'm going to take that Kaggle JSON file in my Google Drive, and I'm going to copy it to tilde.kaggle. So again, really similar to how you would wire up AWS. Let's go ahead and do that. Now that that's done, what I can do is I can actually run these commands that give me access to any data set in Kaggle. So this is a really powerful feature. I'm going to go ahead and start with the MNIST data set, or a version of the MNIST data set, and I'm going to go ahead and download that locally into my workspace for Google Colab. You can see here I've been able to actually load that in. Now what I can do is I can actually go into Pandas and create a whole data science workflow using that Kaggle data. Okay, now you can see that I've been able to load the Pandas data directly into Colab that has the MNIST data set. I have a train set, a test set, and a feature set. You can see I print out the shape of all those different variables. And now let's go ahead and show those MNIST handwriting samples. Here we go. So you can see it's a really powerful workflow to go to any project in Kaggle, wire it into your Colab notebook, and then manipulate it maybe with your own data set. Let's look at another thing you can do with Colab Notebook. A really powerful feature is the ability to change your runtime in a Colab Notebook. And this is actually an extremely powerful feature. So if we go to runtime here and I go and I change the runtime, you can see that I have access to hardware accelerators. One of those hardware accelerators is a GPU, another one is a TPU. What this means is that if I want to do deep learning, I can actually use an NVIDIA-based GPU, and I don't have to buy some separate machine to test out my GPU-based code, or I don't have to necessarily get an instance to AWS or to Google Cloud or to Azure. I can actually test that out right inside of Colab Notebook for free. This is a really powerful feature. Also, TPU is a TensorFlow processing unit, and it's specifically designed to run with TensorFlow. So if you develop TensorFlow-based code or Keras-based code, you can actually go ahead and use the TPU. In some cases, your code will actually run faster than a GPU-based workflow. So a really powerful feature. Another thing to point out about the runtime is that you also have 3 other options here. So one of them, if we go again back to this runtime here, is that you can change from Python 2 to Python 3. Another thing you can do that's really interesting is you can also create a local runtime. So if you're really a fan of the Kaggle interface, you can actually wire it up to talk to, let's say, a really powerful desktop machine that has, let's say, NVIDIA GPUs, and you can actually use the Colab Notebook as your own front end. Let's also talk a little bit about universal images and data inside of your Colab Notebook. So one problem that crops up with a web-based interface like this that's hosted is that you'll need a way of sharing images and files with people that don't have access to, let's say, your Google Drive. So one of the ways that you can do this is to use this hack where you use GitHub issues to actually store the image file. So you can see here, this is a picture of that iron icon. If I double click on it, you can see that I actually have this hosted inside of GitHub. So if we go back here and we look at GitHub, and if I look at a GitHub issue, let's go ahead and find that repo. Here we go. And if I go to this ticket that was created, this issue, you can actually upload any image you want by just dragging it and dropping it inside of an open issue. So again, if I take one of these screenshots that I created earlier, I upload it, you can see it then goes ahead and stores that image inside of GitHub. And if I click on it, it gives me a permalink. So that's a great little hack that you can use, and then you can actually paste that back into your project. Another trick that's similar to that is you also can take very large files, and you can actually take those large files and store those inside of GitHub. So let's go ahead and look at how that would work. So if you look at this GitHub workflow here, what you can do is you can install something called LFS, which is large file support, and then you can tell it to track a specific type of file. So it could be, let's say, a 1 gigabyte CSV file. You then go ahead and add attributes, and then you check that into your GitHub repo. So if we go back here and we look at this large file that I have linked here, this is actually a file that lives inside of GitHub, and you can see it's 963 megabytes. If you use GitHub frequently, you'll notice that that's actually over the limit. If you try to upload, let's say, a file that's 200 megabytes, GitHub will complain and it won't actually let you upload it unless you do this and you store it with large file support. And what's great about this is if I then go ahead and say copy link address, I can actually specifically load that directly inside of my Colab Notebook without a problem. So these are 2 really powerful hacks that you can use to make reproducible notebooks and actually carry both images and data across notebooks so that you can share them with other people. One other thing that's in the spirit of that I'd like to talk to you about is Colab to Colab cell copy hack. So this is something I use quite a bit because I create so many Colab notebooks. If I go here and I actually take one of these cells and I copy it, and then we go to copy selection, what it'll do is it'll actually copy specifically those Colab cells, and it will allow me to paste those in another notebook. And you can see when you do that, this is the exact workflow. And then if you go to another Colab notebook, you can just paste it right in. So this is a great way to actually share information between two Colab notebooks. And it could even be a very high multi-cell section that has, let's say, 63 cells inside of it. The way it works is you copy everything under the cell you've selected. Now, let's go ahead and wrap this up and talk about some of the highlights of what we discussed. In a nutshell, Colab has got many different features, and one of the ways to get a lot of power out of Colab is to wire up Kaggle, to wire up AWS, to use the Google Drive ecosystem, and also to communicate with GitHub. So something to keep in mind is to think about other ways you can integrate third-party systems to extend your Colab notebooks. Let's talk about some really unique features that you may not be aware of that you can take advantage of in Colab notebooks. They're called magic functions. And magic functions do things like add the ability to time snippets of code to show you the difference between one version and another. So now let's go ahead and look at this time it snippet here. What I'm going to do is I'm going to look at two different ways to do the same thing, and I'm going to time each one of them to get a comparison to see which one I want to use in my code. So I import NumPy, and I also am going to use the built-in round function to round this decimal. So if I go through here and I run it, you can see I first use built-in Python round, and it goes through and it runs it in a bunch of different loops, and it shows me that the best 3 took 500 nanoseconds. And then if I look at NumPy round, you can see it took the best 3 loops, and these were all microseconds. So we can see actually that the Python version is faster. So this is a great way to actually do a real-world test and check your assumptions when you're writing code. And it's really simple. You just use this %sign time it. Similarly, there's a really powerful feature in Colab Notebook called alias. And so what I'm going to do here is I'm going to create an alias, and the alias is called ls_csv. And what it is it's actually a very lengthy command. The alias is set to ls-l. I then go and I look at the sample data, and I look for all CSV files. So let's go ahead and wire that up. And now every time I want to look inside of this sample directory, because this is again the default directory that Colab Notebook gives you, I can go and run this alias and it'll show me all the CSV files. So you can see how you could create many of these types of aliases and save yourself a lot of time. Really powerful feature. Next, let's look at the who magic function. So what who does is it shows you what's actually in your memory space. So if we go ahead and we look at who, you can see that I've been running a lot of different code in Python. And if I go ahead and I just take one of those, let's just take the cars variable here, I can actually go ahead and type that out, and you can see that I can actually go through and play around with all those different variables that are available, but this who command actually let me get access to it. And I also can run who ls, which is a similar version of it, and that will actually give me a list version of the same thing. So really powerful feature that you should be aware of that gives you the ability to see what's been happening in your notebook. Now let's also look at something called write file. Write file is pretty powerful. What it does is it actually will take the cell that you're in, and it will take all of the output of that cell and put it into a file. So you can see how you use it. You do % write file, and then you just create a file that you want to write the output to, and then it'll actually literally take the output of the file and put it into this text file. So this could be a good way to, let's say, take a snippet of code and share it with somebody else. If I go through here and I run the cat command, you can see that it took the exact same contents of that cell. So really powerful feature. Now let's go ahead and look at another powerful thing you can do. You can actually use bash inside of Colab Notebook as well. So if I do % bash, I can actually write raw bash directly below this. And so in this example, what I do is I run uname-a, and I can see that this is the Linux kernel that's running on Colab Notebook. Another really powerful thing you can do that's a magic function is I can actually go ahead and use Python 2 inside of a Python 3 notebook. So if we go here and we do %% Python2, I can actually go ahead and print the old way if you've been a longtime Python user, and we can print old school, right? You know that if this was a Python 3 statement, if I go right below that and I say print old school, this will actually blow up because this isn't allowed with Python 3. So pretty powerful way to actually mix and match both Python 2 and Python 3 in your project. Finally, let's go ahead and take a look at HTML. You can also just print out straight HTML blocks directly in Colab Notebook. So there's a lot of really powerful things you can do with this. So if you use %HTML, we can make sure that we only print out the best tags. And so here we go, only the best tags. So in Colab Notebook, there's many different magic functions that you can use. Python 2, HTML, bash, write file, who, all really interesting ways to save time and actually make your workflow much smoother. Let's talk a little bit about Jupyter compatibility and also the ability to import and export files between Colab and Jupyter. Really, they're the same environment with a couple little changes, but let's go ahead and take a look at how that could work. So if I want to take a Colab notebook and then run it in Jupyter, a really simple way to do that is go to the File menu and actually say Download IPYNB. And what it'll do is it'll actually just drop out a Jupyter file, and you can load that in anywhere that runs Jupyter Notebook. So that's a great way to use that workflow. Here you go. You also can do the exact opposite workflow. So if I go and I say File, Open Notebook, I can actually go and do an upload, and I can choose IPYNB file here and go ahead and open it, and it'll actually go through and it'll create a Colab notebook from a Jupyter file. So you can see there's actually a great workflow that lets you go back and forth between the two different notebook styles. You know, a walled garden of many beautiful Python packages. Occasionally though, you will run into some problems where you have to maybe hack a little bit and change things around with your environment. So one thing that happens every once in a while is if you get the wrong package, you'll have to actually go through and uninstall the package that Colab installs and install your own. So here's an example where if you're using the version that I'm using, the version of Plotly is 1.12.12, which is a pretty old version. And so what I do in this example is I use pip uninstall, and I uninstall that version of Plotly. Next, I go and I do a pip install Plotly, and I say I want the one that's much later, 3.6.0, which is the current one, and I go ahead and download it. When it's done downloading, one of the tricks you have to do is you actually have to go to runtime, and you have to restart the runtime because it's actually a completely different package. Once I do that, if I go ahead and I say import Plotly, you'll see that now I have the new version. But it won't do that unless I do the restart. Another thing about the Colab environment is that you do have to do this little bit of a hack here where you have to run this enable Plotly in cell. And what this does is it actually enables Plotly to actually execute in the Colab environment. So let's go ahead and run that enable Plotly in cell. You can see how it works there. And now what I'm going to do is I'm going to set up a clustered 3D plot in Plotly. So I go ahead and I grab some World Food Fact data, and again I've kept this data in GitHub to make it really easy to copy. There we go. So what this is it's fat, carbohydrate, sugar, protein, salt, energy, and product information. And now I go through and I do some k-means clustering. All right, here we go. Now I've assigned all these to clusters, and now I'm going to take that clustered data, this unsupervised machine learning process, and I'm going to go ahead and wire that into Plotly here. And so if we go ahead and we run this code, you can see that it'll go ahead and create a three-dimensional plot that uses that latest 3.6 version of Plotly, right? And so you can see that I get this great little graph here, and I can actually hover over all these different sections, and I can see that in this z-axis, whey protein powder has got a very high degree of protein, and that's why it's up here. And if I scroll down here, we can see that there's other sugary foods that are more near the bottom. So in a nutshell, one thing that's really important to know about is that occasionally you may have to hack around your notebook, and this is one method of doing it. Finally, I'd like to wrap this section up in talking about how to install software. We've talked about it a little bit and you've seen some instructions, but in a nutshell, really it's just this. You would do exclamation pip install, and then you have the option to either do it without a queue, and that'll actually print the output to standard out, and you can actually see everything. Or if you don't want to create a giant text blob in your notebook and you want your notebook to look a little bit cleaner, what you can do is you can actually add a queue and it won't print out the output. A lot of times this is what I do after I've established that something works. I'll do a queue so that way my notebook isn't a huge 1,000-line installation output, and I want to save that maybe to a setup section of my notebook. So to recap this section, really it is a compatible environment for Jupyter. Almost everything you can do in Jupyter you can do in Colab and vice versa, and there's only a few little things that you need to be aware of, and some of those we've highlighted in this example. Welcome. We're going to be covering in this lesson the basics of Python. This includes writing procedural code. You learn to use simple expressions and variables. You create variables using built-in types. You learn to print. You learn to perform basic math operations. Finally, you access classes and objects by using dot notation. Let's get started. All right, let's talk a little bit about the basics of Python and procedural code. So procedural code is literally just a statement that you can issue one line at a time, and below are types of procedural statements. A few of the ways that you can run them are you can just run something in Jupyter Notebook, you can run it in an IPython shell, you can run it in a Python interpreter, or you can even write a script. And all these are just literally statements that you run. So for example, if I go ahead and I run 3 types of energy equals, and I put brackets around it, protein, carbohydrates, fat, this is a one-line statement that creates a list in Python. Now, if I want to make multiple statements, what I can do is I can go ahead and run this next statement that takes that list and divides it into 3 different variables: protein, carbohydrate, fat. And then I add a sentence that says carbohydrate, they sure taste good. Fat isn't bad for you anymore, right? And what this does is it does one by one a statement, and even though it's not a program per se, it is actually a great way to execute code, and it's a fine way to do data science in the Colab environment. Now, if I want to go through and do something more numerical, one thing I can do is I can actually just add numbers, and I can treat Colab Notebook like it's a calculator. So in this example, what I do is I assign a variable protein to 4, and I assign the fat variable 9, I assign the carbohydrate variable 4, and now that I have all those variables set up, I can actually add these different numbers together. So here we go. If I add a carbohydrate and a protein together, I get 8. So they're both 4 calories apiece, and I can see that I've actually created a combination of 8. Now, another thing you can do that's pretty interesting is that you can actually add phrases together. So here's an example. I take a phrase, a carbohydrate, and then I use this plus, and I say has, and then I take that variable that I had earlier, the carbohydrate variable, and I concatenate it with calories. So if we go ahead and rerun this, you can see a carbohydrate has 4 calories. So not only can you add numbers, but you can also add phrases together, and it's the exact same type of an operation as this plus operator. If I wanted to do a slightly more complex operation, what I would do is I would say for energy type in 3 types of energy, and I would actually go through and I would print each one of those types: protein, carbohydrate, fat. Now to really wrap this section up, the main takeaway is that you can think of procedural statements as a very logical set of instructions that just does one thing. And for data science, this is a great way to work, and it's actually a highly encouraged way to work because it allows you to do something that's really simple and repeatable. Let's talk about some simple expressions and variables that you can use in Python. One of them is assert. Something that you can do with assert that's kind of interesting is you can actually assert that something's true. So here's an example. I assert that a carbohydrate is equal to 9. And because I've defined that earlier, we know that a carbohydrate's got 4 calories, but a fat gram has 9 calories. So we can see this is actually an assertion error. That's not true. If I go ahead and I change it and I say assert carbohydrate is equal to 4, you can see that actually that error doesn't get matched anymore. So this is a great little trick to use if you want to add some debugging to your code. Is you add an assert statement, and if a statement actually turns out to be false, then it throws up an exception and you can actually do something with it. Another statement that you should be aware of is pass. A lot of times you use pass to just syntactically complete something. It really does nothing other than allow something to be completed. So here's an example of what that means. I go through here and I say class calorie pass. So what it does is it allows me to finish creating a class. And then if I go ahead and I make an instance of that, I can actually go through here and use that instance of that class. So I can say value is equal to, let's say, 9. There we go. And now I've actually been able to manipulate something because the pass statement actually allowed me to complete it. Another interesting statement that you can use is deletion. So let's go ahead and again and create a class using that pass statement. And now what I'm going to do is I'm going to run this whols command, which again shows me all the variables that are available. So you can see here that this kcal now shows up. So now it's actually in memory and I can actually do something with it. And actually let's go ahead and use it so you can see. Maybe we'll set this one to 9. Now if I go ahead and I use delete, what it does is it actually reduces it and deletes it from the memory space, and now I actually don't have that available. So it's just a way to, let's say you've created a really large structure in memory, you could actually go through and just delete it yourself. Another statement that's very powerful is the return statement. This is used quite a bit, but it's worth explicitly showing you how it's used. Here's an example. I create a very simple function, food, and it returns back the string way. And what I do is I make a print statement that says, make way while the sun shines. And what this does is it uses that function to return that value. Yield is another statement that's really powerful, in fact, and especially for data scientists. And what it does is it allows you to only get one value at a time from an iterator. So for dealing with really large data, this can be extremely valuable. So here's an example where I create a function called too much food, and inside we've got an orange, an apple, turkey, ham, and what I do is I iterate through and I yield one of those snacks at a time. Here we go. And then I make an instance of those snacks, and I actually use next to one at a time call that generator and get something out of it. Now if I want to actually get one more value out, I could actually, on the line below here, call it one more time, and it'll give me the last, the second to the last value out. So here we go. Let's call that snacks again. There we go, turkey. And if I want to do even one more, I can get the very last value. Here we go. And then if I want to actually get to the very end of it, we can call it even one more time. So let's go here. And now you can see that I get a stop iteration error. So a great way to deal with a large data structure, very common to deal with this in a data science pipeline. Now let's talk a little bit about break. Break is a statement that allows you to break some kind of a loop. So here's a loop that has a carbohydrate set to 4, some calories at 0, and what I do is I iterate through and I add calories until I actually reach a number of 8. And so if I go ahead and I run this, you'll see that the first time it runs, it says, okay, let's eat some more carbohydrates, and then it adds that next group here at 8, and then it adds one more, and you can see as soon as I get to 12, 12 is now larger than 8, and so now this line below here goes, and I can actually break through. So normally a while true statement will run forever, but in this case, because this condition is met and 12 calories are over 8, I actually break out. So it's a great way to actually break out of some kind of a loop. Another statement to be aware of is continue. So here's an example where what I do is I actually take 3 types of energy, protein, sugar, fat, and I say for energy in 3 types of energy, if the energy is sugar, I want to skip that and I actually want to continue, so I don't want to do anything with it. Otherwise, I want to actually say I'm going to run this statement below here. So continue allows you to actually do some alternate action in the middle of a loop and not run the line below. And so here we go. If I run this, you can see that the first thing that is processed in the list is protein, right? So it goes directly down below here. It doesn't match this condition. And then the next thing that happens is it takes sugar and it notices there's a match. And so what it does is it doesn't run the line below, right? So it goes through here and it skips through and goes to the next iteration of the loop. And then finally it says, okay, let's eat fat. And then it goes through and it grabs this last statement here. So this is also a very powerful workflow to be aware of. And this is a really simple example to play around with. Finally, one of the things you can do as a statement is import. And import is something that you'll do all the time in Python. And here's an example of a pretty fun module that you can import. It's called the this module, and it actually imports the Zen of Python. So to wrap up, there's many different statements that you can use in Python. We covered assert, we covered pass, delete, return, yield, break. We're going to go into more detail on those in later lessons, but these are little examples that you can actually use to get more familiar with these statements. Let's talk about some of the built-in types that you may come across in Python. Probably the most common one is a dictionary. We're going to go into how to use those in later lessons, but just from a really high level, here's how you would go through and define a dictionary. There's an omelet variable, and I put an egg as a key, and I have a value of 3. I have a ham as a key, and a value of yes. And if I go ahead and I click type, you can see it's a dictionary. A list is another really common data structure, and this is just a sequence. So you can see here I say ingredients, and I have an egg, a ham, bacon. I go through and I can see that that's actually a list. And so the real difference between these two things is this is key value based access, and this is an iterator, right? So an iterator allows you to do things like yield, and a key value lets you do things like a membership lookup. Another really common data structure is a set. Here's an example of what a set does in action. So I go through and I put in 2 items that are the same. So we have 2 eggs in here. But when I print it out, one, it says it's a set, but also if I go to the line below here and I look at this egg set, you'll see that it's actually got 1 item inside of it, because a set by definition will only allow unique items to be included in it. So it's a really simple way to, for example, dedupe things. Another powerful data structure is a tuple. And what a tuple does, you can see here, there's assignment error, but let's go ahead and comment that out for a second. A tuple allows you to go through and put things inside of it. And you can see the brackets around it. We've got egg, soup, and you can access it the same way that you would access a list, right? So if I go through here and I say breakfast, I can access the first thing, right? And if I want to access the second thing, I can access the second thing. But the key takeaway is, unlike a list, if I go through and I want to actually assign something to it, I'm not allowed, because a tuple does not support assignment. So if you want to create something that's a read-only variable, very similar to, let's say, Erlang or Haskell or one of these functional languages, you could actually use a tuple. Let's talk a little bit about printing in Python. So since Python 3 in particular, printing has actually been a little bit different. Printing is a function now in Python 3, and you can see what you do to print is you put in a string. So you just literally go ahead and add a string in there, and if I want to go ahead and I want to do a fancier string, I could go in and I could do an f string, and I could, let's say above here, create a variable, and we'll call this maybe ham. And then if I want to print that out, I like, and then I put a variable inside of here, I can actually go ahead and print that out. So it gives you the ability to actually do more complex things. So let's get into how you would do this in a typical Python workflow in Jupyter or Colab Notebook. A lot of times you'll see this style here where you'll create a variable and then you'll actually use a semicolon and then you'll print that variable out on the same line. And typically it's not a great practice in, let's say, a application to use these semicolons, because it's better to keep things a line at a time. But oftentimes in these cell-based approaches, this can be a great way to actually solve a problem, because you, for example, want the last line to print out, or you want to make it clear what you're doing. Now let's talk a little bit about how you could actually use print as a function and do something even trickier. So here's how I take this print statement here, and I actually have multiple things that I put inside, and I actually can specifically create a separator that's a plus separator. So here I take some really San Francisco specific food items, kombucha and Manuka honey. Both of these you're not allowed to enter San Francisco unless you drink or eat. Here we go, kombucha plus Manuka honey. Now I'm officially allowed to enter San Francisco. Let's talk about some of the basic math operations you can do with Python. Python really is a built-in calculator, so not only can you do all these really great things like use data science and plot things, but you can also just treat it like a calculator. So here's an example on this nutrition theme is, if I want to go through and I want to create a word problem where I have a couple things together here and I say 2 steps forward, 1 step back, you can see it's pretty easy to create a word style problem, right? Where I both add things in a parentheses and subtract things. I also could go through and create a more sophisticated, health-based scientific problem where, here's a body fat percentage, a weight of 200, and I want to actually go and create some kind of a body fat calculation. You can see this would be a great way to do it. So even if someone isn't a massive expert at Python, you can see how it's pretty intuitive and almost there's no programming at all to go ahead and create a word problem. It's essentially logic, right? So you create a variable, create a second variable, then you do your calculation in the third variable, and then you just print it out. So this is actually a really powerful way to get started with Python, and if you're coming from a scientific background, definitely would be one of my recommendations to make yourself more comfortable with the language. Another thing you can do is you can actually use decimals and set precision with those decimals. So here's an example of the decimal library, and if I use this get context submodule here, I actually can set the precision to whatever I want. I don't know if I want to set it to 20. Here's an example. You can see I can create this really long decimal, or if I want to make it shorter, I can create a shorter decimal. So this is great when you're dealing with more complicated scientific problems. Additionally, you can do exponents in Python. There's a couple ways to do it. So one is to import the math module, and you can say math.power. So here's an example of something that's 2 to the 3rd power. Or this is probably my favorite way to do it, is you can use asterisk asterisk right? So 2 to the third power is a really clean way to do exponents, or just to show you the example here, right? This is just multiplication, and we could even add a little note here that says, multiply, and then we have exponents above. So again, a great way to get familiar with it. Now let's talk about converting between different numerical types. When you're doing calculations, it's really common to need to convert between, let's say, integers and floats, or strings and integers. So one way to really get comfortable with that is to be familiar with type. And what type does is it shows you what the type is of the variable that you're dealing with. So in this case, I first create a number 100, and then I actually run this command here, which will show me what the type is of that number, and then I go ahead and I print it out. So you can see 100 is type integer. Now if I want to go ahead and I want to explicitly create a float, which would essentially give it a decimal, and I run that, you can see that the num type is type float. And then if we want to go through and I want to actually see even more type examples here, if I create an empty class and I do type, you can see that this is going to show me that it's in fact a class. So type is a great way to really get familiar with what's going on when you're doing conversions. Another thing to point out is that numbers can be rounded. And so here's an example. We talked about some of this earlier. I can go through and I can use the built-in round. I also can do the same thing in NumPy, right? So NumPy also allows you to do rounding, and I also can create an empty data frame in Pandas, and I can actually round it as well. And so we were previously talking about these magic functions and how powerful they are. And so again, you can see in action, now I've added a third function here, and I can actually compare the difference between built-in round, NumPy round, and Pandas round. And again, this is a great way, as you're getting comfortable with the Python language, is to use timeit to really get a feel for intuitively how long something takes. And what this actually shows us is that, again, the built-in Python round function is actually much faster than NumPy and Pandas for this particular operation. Now let's talk a little bit about another really common thing that will happen in basic Python, and that's that you'll have to interact with classes and objects. So here's an example of how you can interact with special class methods and other class objects. If I want to go ahead and I want to make a really basic list here, you can see how it actually works. And then if I want to make a length of that list, you can see that it is actually shows me that there's something inside of it, right? There's two things in that list. But if I do a class here, you'll see that it actually will not work because object foo has no length, right? So classes, it doesn't really make sense. It's a kind of a nonsensical thing to do to ask a class how long it is, right? It just doesn't really make sense. But we're going to get back to that later. I just want to set that up. Now let's talk about a class that we create from scratch here. So here's an example of a class that's John Jones. John Jones is a mixed martial arts fighter, and he has a 84-inch length. And so what I'm going to do is I'm going to override this class to actually give it the ability to tell me how long it is, right? So even though it didn't make sense here, I can actually go through a class and actually override that length method and actually make it return something. So now if I run this and I make an instance of John Jones, we can see that the object John Jones is now returns 84. So this is a neat little trick that gives you more of an understanding of how you can do powerful things with classes. Now again, if I go through here and I try to make some empty class, you can see that it just doesn't work. So there is a way to do it. To do it, you'd actually need to use that length override. Another thing you can do with a class that's kind of interesting is you can actually add a property decorator, which makes it a read-only property. So if we again go to this John Jones class here, and I create a method inside of here that has the app property on top, what this will do is it'll actually return back 84. So let's go ahead and do that. So we see I make an instance of John Jones. I look at John Jones's reach, and then I go ahead and I say John Jones' length, that's 85. So the length is 85, but the reach, if I go ahead and I print that out, is going to be 84. Right, so it actually acts like it's an attribute even though it's actually a method on that class. And then if I want to go through and do what the example says above, and I want to try to set it, it's not going to be happy because I'm not allowed to. So if I want to set it to 85, I can see I cannot set that attribute. So this is a neat little trick that really mimics some of the behavior that you'll get from other languages like let's say Java or C# that allow you to protect different parts of classes. Another thing you can do with classes that you may be aware of is that you can actually use this thing called a static method. And what this does is it allows you to treat a method like it's a function. And so what this does, if you see here, there's no longer a self available. And what this does is it actually just kind of bolts on a function into a class. So in this example, I also can have the static method return back something. Now, this is not something that's going to act like an attribute, right, because I call it with the function operator, but it still accomplishes the same thing. So let's dive a little bit deeper into this concept of playing around with objects, and let's look a little bit at that movie Unbreakable. So in that movie, there was a couple characters. There was a villain, and there was also a superhero. And the villain was this person that was actually could, you know, if they even fell, they would shatter the bones. And there was another character that actually nothing could be done to break it. So kind of the same thing could happen with classes, right? So if I go here and I create an unbreakable property, right? Here we go. I say this is unbreakable. But then I also can create an attribute that is breakable, right? Because it's not, again, a property. I can see that not unbreakable is actually available inside of this under dict here, right? So I can see that it's actually set on the instance of the object, and I can actually play around with it. And if I set it again, you can see that I'm able to change Elijah into Mr. Glass. But if I go ahead and I try to break this other character, David, which is played by Bruce Willis, and I say unbreakable, you can see I can't set that attribute. So really this just walks you a little bit further through that concept of how you can create, on one hand, an attribute that is completely immutable, cannot be changed. On the other hand, generally attributes on classes are changeable. And so it just depends on what it is that you want to do, but both options are available in Python.
We'll talk about strings in this lesson. We'll learn how to use strings, including string methods, string formatting, manipulating strings, and using Unicode strings. Now let's take a deeper look at strings. Strings are an important data type in Python. They're essentially a group of characters, could be letters, numbers, blank spaces, special characters, all grouped together as a unit, as a data type. Strings have a lot of built-in methods that you'll be using as a data scientist. Let's take a look at some of those right now. Now, a string is defined as characters or spaces surrounded by quotes. String could be done either with a single quote. Here we see single quoted string. It could also be done with a double quote, and that is effectively the same thing. So here we see that a single quoted string is equivalent to a double quoted string. And it's really just a preference as to which you use most of the time. If you want to do a multi-line string, then we can do a triple quoted string. And that allows us to, as you can see here, type on multiple lines without having to do a continuation or put in a new line character. This will show up if you print it with the line breaks there. These are the standard formatted strings. There's also something called a raw string. So here we have a normal string, and notice that we have a new line character as part of the string. If we print this string, we get a new line. The print takes that new line character and interprets it as a new line character, as a special character. If we preface the string with an R, make it into a raw string, then all the characters are treated just as the characters they appear to be. So here, if we print the raw string, we see that the new line character stays as a \n. Strings have a lot of built-in methods for manipulating case. So let's look at a couple of those. So here we have a string, and if we look at it, we see the 2 letters are capitalized at the beginning of the words, and the rest are lowercase. If you call capitalize on a string, you see that it puts it into the state you would expect at the beginning of a sentence or a paragraph, where the first word is capitalized and the rest are not. If we want to make it all lowercase, we can call string lower, or make it all uppercase, make it string upper. An interesting one is we can swap all the cases of all the letters in a string. And here, if we start with a string that's all lower, and we want to make it into a title, so this would be the title you'd expect in, say, a heading of a book, so all words are capitalized, we just call string title, and there you go. So all of these are returning a new string as the output, and that new string can be set to a variable and used or printed as you see fit. There are a number of methods for interrogating the information in strings and getting information about strings that are built into Python. So if we have the string Mississippi, we've set a variable to Mississippi. We can call leng, which calls the length method of the string, and we see that it's got 11 characters. We can count characters in it with the string count method, so we can count S's here, and there are 4 S's in Mississippi. We can find an index into the string to find the location of another string, a substring in this case of 2 P's. And you see that's at location 8 in the string. We'll look at indexing the strings a little bit later. But we can also call index on a character that's not in the string. And you see we get a exception, a value error, because it's not there. If we want to be able to look in a string without getting an exception for a letter that's not contained in the string, we can use find instead of index. And we'll see that find will return a -1 instead of throwing an exception. So depending on what you're doing, you may prefer to use find rather than having to catch the exception. We can see if a string starts with a letter. We can see if it ends with a letter. We can also check a string for containing a substring by using the in syntax. So here we see that it will return a Boolean, true or false, depending on whether it's there. There are many built-in methods for checking the content of a string. One is to check if it's alphabetic. So in this case, we're calling isAlpha on a string. And we expect it to return false because 1, 2, and 3 are numeric types. Then there's an alphanumeric, which we see is true in this case because it's characters and numbers. We can find out if a string is all lowercase letters by calling isLower, or all uppercase letters by calling isUpper. We talked about what a title was before. There is an isTitle method. And we can see the isTitle method if the string is not formatted as a title. In this case, because of the lowercase words, it'll return a false. So these all return Booleans, which can be used in conditionals and loops, which we'll talk about later on. Now let's look at format strings. Format strings are a powerful Python feature that were introduced in Python 3.6. They allow the runtime addition of values to a string by using what are called replacement fields. The replacement fields are delimited by curly braces. To insert a variable into a replacement field, so here we have a variable called strings count, and it's 5. And we have a variable called frets count, and it's 24. And here we have a f string, as they're called. The f string is prefixed by an f. It can be lowercase or uppercase. It doesn't make a difference. The replacement fields are surrounded by the curly brackets, and we're able to insert variables from the local scope into the string. So you can see when we output of the string, it has inserted the values of those variables into the string. This is a really fun and easy way to manipulate strings in runtime, and it has a lot of power. So the replacement field will take pretty much any expression. So in this case, we have two variables that are integers, and we replace them as we did above, just their normal value. But here we're multiplying one by the other, which is an expression. And we'll see that the output is what is inserted into the string. Here's an example of taking a list of strings and indexing into that list in the replacement fields of another string. So here we grab not the first, but the second, which is index 1, because it's a 0-indexed list. Here's the first, and here's the third. They're all inserted as per our instructions. Replacement fields allow for what's called a conversion flag, which converts the type of the value being inserted before additional formatting is called on it. Currently, the three available flags are S, R, and A. The S is for string conversion. This is the same as calling the str Python function. Here we call it on a list. It will show up the same way as the list would otherwise, because things are cast to strings implicitly when they're inserted if no other conversion function is called. The repr is called using the R flag. Here we see the effect of calling that on a string is it actually inserts quotation marks around the string in the parent string. So repr is something that exists on all classes in Python. It's basically a printable version of a string, just has the quotation marks around it. And the third, the A, is for an ASCII conversion. So here we have a non-ASCII character, a check mark, which is a special character. And if we want to see what it looks like when converted to ASCII, what the ASCII code is, you see right here. So that's how we convert in the string to ASCII. It's also possible to pad numbers in the strings. Here we have a number, and we want to pad it 5 places. So we put the number value here, and then we have a colon, and then the amount of pad. And you can see that there's 5 blank spaces added there. An exciting and powerful part of this is that we can actually use a variable to set the padding, which means that we can change the padding during runtime. So here the padding is in a variable called padding, and you see it's in a nested curly brackets inside the greater curly brackets. And it returns the same string we saw above, but does so at runtime. In addition to the f-string syntax, there are a number of other ways to manipulate strings in Python and to create new strings based on the changes you make. A very simple way is called concatenation. We can use a plus symbol and actually construct a new string from multiple other strings. So here we've created a new string just by adding these two strings together. We can even use a multiplication symbol. So here we have a 2-letter string, and we're multiplying it times 8, and the result is a 16-character string comprised of the substring 8 times. There are a number of ways to remove white space from a string. This is a problem that comes up a lot with form-based inputs. Sometimes, generally data that's coming from users often has extra white space in places that makes it difficult to work with. Here we have a string that has both leading and trailing white space, and we can call the strip method, which will remove this white space while retaining the white space that is contained in the middle of the string that we want to keep. If we want to take white space from one end of the string without removing it from the other, we can use the L strip for left, remove it from the left side, or the R strip for right, remove it from the right side, and you can see in both cases we've retained the white space on the other end of the string. A nice thing with all of these strip methods is that you can actually define a substring to strip instead of just stripping white space. So here we're using the rstrip, the substring, and you see it removes that from the original string. There's also numerous ways to add padding to a string. So if we have this string and we want to surround it with star characters so that the total return string is 12 characters long, we can call center on it. And we'll do that, and we can do this to the left and to the right. So here's to the left, and here's to the right. Places where this will come in really handy is when you're outputting to a user and you want to line up words in the output. So here we have a list of city names that are of different lengths, and we want to print them so that they line up. So we're calling rjust to make sure that they all expand to 12 spaces. So let's see what that looks like. And you can see they all line up nicely, which is a great way to get clean output to your users. There's also a specialized fill method for work with integers called the zfill method. And so here we have a negative number as a string, and we call zfill on it. And it will pad it 4 places while retaining the negative value and being intelligent about where it puts the zeros. Commonly used method for strings is the replace function. So here we have a string, and we can define what character we want to take out and what we want to replace it with. And that comes in really handy in a lot of situations. Now, a lot of times you're going to get strings that represent some series of values that are separated by something, and you want to break them up into those values to get a list of values that you can then manipulate and work with. So here we have a list of words separated by commas in a single string, and you can see when we look at that string, it's one string with the commas in there. And we can use the split method on that string to get a new list of substrings as split by the character that we specify here. So now our words are a list of words, and the character we used for doing the splitting, the token, is not present in the results. Now, if we have a list of words, as we do here, and we want to join them together with a character, we can use the join function. Here we have a string, which is the character we wish to insert between the values in the list, and we call join on that string and give it the list as an argument. And you can see the output is a single string with that character in between the words that we asked it to. And what we see here is a single string with that character in between the words that were in the list. In addition to splitting based on characters that we specify, it's pretty common to get strings that come in that represent multiple lines with the new line character is part of the string. If we want to break that into multiple lines, there's a special split lines method on strings. And here we are. We can iterate through those lines once they've been split into separate lines and break the document up by line. Slicing is a really powerful part of Python that can be used on both strings and lists and other sequences. Basically, you use an index into the item that you're slicing. And so here, if we want to get the first letter of this string, the 0 index is the W, and so we get the W. The -1 could be used to start counting from the right side of the string instead of the left. So we get the last character because it's -1. We can also take a slice, which is a section of the string as defined by the positions here. We separate them with a colon. And you can see that we get from index 13 up through, but not including index 18. We can also leave out the beginning or ending index. In this case, we're indexing from the end of the word back 7 characters. By leaving the end spot blank, it'll automatically go to the end of the string. Now let's talk a little about Unicode in Python. Unicode is a way of encoding characters to bytes on disk. Previous versions of Python used much more limited encodings than Unicode, but now Unicode UTF-8 is the Unicode encoding that is standard in Python. So if you make a string in Python 3, it will be a UTF-8 string. What does this mean? This means that we can use special characters like this pi sign in a string without any special sequencing or escaping. We can also use these characters in actual variable names. So you can see here that the variable name itself includes the special character pi. We can also use these characters in variable names, and you can see here that the variable name itself includes the special character pi. There's also a syntax for pulling certain special letters out in strings. So here's the Greek capital Pi. And here we can get a numeric version of the string as an ASCII number. And we can take that number and cast it back to a string by calling ch_r on it. And we see we go back and forth. In terms of encoding, there's an encode function on strings, and we can use it to encode to a specific encoding. Since we're using UTF-8 here, it's pretty much the encoding you'll find the most and covers the most ground. If you want to save a file in Unicode, you can specify a specific encoding as part of opening the file object. So let's save this file, and then we'll cat the file's contents on disk, and you can see that indeed the file has Unicode characters in it. There's a lot of more depth one can go into with Unicode, with the move over to Unicode or UTF-8 being the standard in Python 3. You don't have to deal with it as much as you used to in Python 2, which is a real relief and makes things much easier to work with.
In this lesson, you'll learn about Python data structures. Lessons include using lists, dictionaries, sets, you work with NumPy arrays, you use Pandas data frames, and finally, you use Pandas series types. Let's get started.
Let's talk about lists and tuples. Among Python data structures, lists and tuples are among the basic data structures that we'll use almost all the time. They are a building block for so much of what we will do. Both lists and tuples are types of Python sequences. Other sequence types include strings, byte literals, and range objects. We'll see that there's methods that we've seen on strings that will also work on other sequence types, so there'll be some familiarity there. Why don't we start with making an empty list. So here we call the list constructor, and we see we get an empty list. Lists are represented with square brackets. We could also create an empty list by just using the square brackets themselves. If we want to make a list with initial values, we can take the square brackets and put the values in them. So here we have a simple list with 3 items in it. We can also create a list by casting from an iterable. An iterable is an object which reacts to a next function, which means that it returns items through a sequence. We'll talk more about iterables in a later lesson. But for now, we're going to use the iterable returned by the range function. And you see the range is given a number, and it returns numbers from 0 up to that number. And so we're going to cast this range to a list. And in doing so, you see we get 0 through 9, as expected. If we want to create a list of a certain length with some default value, we can use multiplication. We've seen this with strings already, but the same idea works here with a list. So let's say we're creating a game, and we wanted to have the scores of all the players start at 0. We might take the number of players and create a list of zeros with that number of spots. It's important to know that a list can be created and contain multiple data types in the same list. So a list does not have an item data type, as some of the other data structures we'll look at later will. What this means is that a list can have mixed data types in it, and it doesn't care or know what those data types are. We looked at indexing with strings. We can also index into other sequence types, such as lists and tuples. So to get the first item, we grab the first index, the 0 index, because they're 0 indexed. Some languages index from 1. In Python, we tend to index from 0. We can use the negative sequence to index from the end of the list, or the end of the sequence, rather than the beginning. So -1 would give the last item, -2 would give the penultimate item, etc., etc. And of course, we can arbitrarily access any item in one of these sequences just by using its index. So here we have the 4th item in our list of numbers. If we want to add items to the end of a list, we can use the append method. Append is a highly efficient and therefore very fast method for use with lists. Here we have a list that contains one item, the letter A, and we're going to add the character C to the end. And you can see that the list now contains A and C. If we want to insert at the beginning of a list, we can use the list insert method. Insert is not as efficient as append because when an item is inserted anywhere but the end of the list, the other items in the list need to be moved over in memory. And so insert should only be used in times where efficiency is not of the utmost importance. But here we see we're inserting to the 0 spot, which of course is the beginning of the list, and so we've inserted B before the A in the list. With insert, we can insert at an arbitrary position too. So here, if we want to insert it in the 2nd spot, it is inserted. Now, insert is creating a new location. It is not replacing what was at the 2nd spot already. We can also take the items from one list and put them in to the end of another list. So here we have a list with more letters, and if we call the letters extend or list extend with the list whose contents we want to add as the argument, we'll see that those contents are added to the end of the list. That comes in handy quite a bit. Now, if we want to change the item at some particular position, remember the insert didn't do this, but we can index into the list and then use an assignment to that index to change. So here we are taking the item at index 3, so that's 0, 1, 2, 3, which is a C, and we're going to set it to a D. And we see that that D is there now. If we want to swap two items in a list without creating temporary variables, we can use this format. Notice what we have here is we want to swap the A and the B, so index 0 and index 1. And so we're doing an assignment. We're assigning index 1 to spot 0 and index 0 to spot 1. So that's a handy way to swap items in a list without having to pull them out and put them into temporary variables. There are a number of ways to remove items from a list. A common one is pop, and pop with no argument will take the last item in the list, it will return it and remove it from the list. So after we pop the F off the list, we'll see that it's no longer there. We could take the pop and assign it to a variable and use that popped item for something else. Now we can also call pop with an index argument, in which case we'll pop off a particular item at that index level. So here we're popping index 2, which is C, and we see that the C is now missing. Now if we want to remove a specific item from a list without knowing its index, we can call that item out by value using the remove method. So here we've removed the D from the list without calling its index directly. Let's move over and talk a little bit about tuples. Tuples are like lists in many ways, but while we are able to change the contents of lists, which means that they're mutable, tuples are immutable, which means once we create them, we cannot change their content. So we can create tuples in a number of ways. One, we can use round brackets, parentheses, around the numbers. You can see that creates a tuple, which is represented with parentheses. We can also create a tuple by just putting a number of items with commas in between them. We see the tuple is still represented with the parentheses. To create an empty tuple, we can just call the parentheses directly. Now with a single item tuple, it's important to note that whether you use parentheses or not, you need to put a comma after that item. You see, that makes the tuple. So if we had done this without the comma, it would not make a tuple. It would just take the contents of what was in the parentheses. A side note to this is that since you don't need the parentheses there, one bug that can happen is when you're putting an item in as an argument to a function, if you by mistake leave a comma after that item, it will be cast to a tuple on the fly. So if your function isn't expecting a tuple as the argument, this could create a bug that you'll have to track down. So keep an eye on that. Let's talk about some of the sequence behaviors that are shared by lists and tuples. We've seen the in format before with strings, and those also work with tuples and lists. So we can see if 3 is in it. We can also use the not and see that A is not in our list of numbers. We can use the in and not in structure in a number of places that use conditionals. Conditionals are a execution control that we'll be talking about in a later video, but these come in really handy for those. So we want to know if something's in a sequence, and if it is, then we do something with it, or do something to something else. We've seen slicing with strings. Slicing with lists is really common, and you see that a lot. So similar to the strings, the format is we use square brackets. We put in a start, colon, and an end. If we leave the end out, it defaults to the end of the sequence. So here we have a sequence. This will be a tuple of A through F. We're going to start at 3. The start is inclusive, so 0, 1, 2, 3. It should start at the D and go all the way to the end. We could also put an end value in there. Now, the end value is not inclusive, so if we put 4, we'll only get the D out. As we said, we can leave the start value blank, and that will, by default, start from the beginning. And we can also use negative numbers to index from the end of the sequence. So here we're starting from 4 away from the end. Let me see, C, D, E, F, 4. One thing we can do, which we did not talk about with the strings, but will work with them as well, or other sequences, is we can set the step by which the slice happens. So let's look here. We've got our letters A, B, C, D, E, F. We're going to start at index 1, which is A, or which is B rather. So we'll start with B. We've left the second spot blank, so we'll go all the way to the end. But now we've set a 2 here. And what that 2 means, that's the step in between items. So instead of going B, C, D, E, F, we'll skip over every other item. And you can see that's what happens. You can also make that number negative. And you see we just get a B. Unpacking. Unpacking is a powerful and useful way to make Python a really usable and readable language. Basically, when you unpack a sequence, you take a series of variables that you want to set to the items in that sequence. Now this will work with other sequence types as well. So strings, tuples, any of the sequences we can do this. So here we have 3 variables and 3 items. And we use the assignment operator. And so the first variable is set to the first item, second to the second item, the last to the last item, as expected. To do this type of unpacking, you need to have the same number of variables as items, or else you'll get an error. Let's try that out. See, too many values to unpack because it doesn't know where to put the extra value. In order to handle the case where we have more items in our sequence than we have variables that we want to capture with assignment, we can use what's called extended unpacking. With extended unpacking, you see we still have variables and we still use the assignment operator, but one of the variables we prefix with a star. And what will happen is all the non-starred variables will each get 1 item, but that starred variable will take all the unclaimed items. So here we have a middle that is starred. The first we would expect to take the first item 1, and the last item 5, and then the middle items will all be assigned to a list as the middle value. And there, you see, that's how it works. That's a really powerful language feature that a lot of people miss, but it's comes in really handy when you have big lists and you need to take certain items as individual items, but then maintain the remainder of the list as a variable as well. One data type in data science is a stack. Now, the way a stack works is it's a last in, first out data structure. Basically, if you think of it like a stack of books or a stack of papers, the last item is the item on top, and that's the one you take off first. In order to simulate a stack in Python, a list is a really easy data structure to use. So basically, we create a stack as an empty list, and we use append to put items onto the stack. And there's our stack with 3 items on it. When we want to retrieve items from our stack, we use pop. And of course, pop takes the last item first, and so it does simulate stack behavior very well. Let's go ahead and what we're going to do here is we're going to pop all 3 items off in order. So whichever one is first will be here, second here, and third here. And we will see that in fact the last item on is the first popped, the second item on is the second, and the first item on is the last to be retrieved. Queues can also be simulated in Python. Queues are more like a line. The first item in the queue is the first item to be popped off of queue. However, lists are not a very good data structure for simulating queues, and so we'll have to talk about those in another video. Another Python data type that you'll find yourself using all the time is the Python dictionary. If you've studied any computer science about data structures, you'll know about hash maps, and the Python dictionary is based on the hash map principle. Basically, it's a mapping of keys to values. The dictionaries can be created, either calling the dict constructor directly, and this will give us an empty dictionary. Notice the dictionary uses the curly brackets as a representation. We can also create a dictionary, an empty dictionary, by just calling curly brackets. There we go. You see we get a dictionary that way as well. The dict constructor also will accept a list of lists where with every sublist being a key value pair. So here we have key 1, value 1, key 2, value 1 as sublists to a list. When we pass that to the dict constructor, and we see it creates a dictionary. And you can see here how the representation works. You've got the curly brackets on the outside, and then we've got a key, a colon, a value, comma, key, colon, value. And that's how dictionaries will be represented when they're printed. We already showed that we can create an empty dictionary with the curly braces. And we can also use the curly braces to create a dictionary with initial values. So we just, similar to the way the dictionary is printed out, we put a key, a colon, a value, comma, and so on and so forth with each additional pair of key values. And you can see that this gives us the same dictionary as we got by using the nested lists up here. Now, to access a value in a dictionary, the general way is to use the key that's associated with that value and index in. We index in using the square bracket, similar to what we did with slicing, but instead of an index number, we're giving the key whose value we want to return. So here we gave it key 2, and we see we get value 2, and if we gave it key 1, we get value 1. Now, if we have an existing dictionary and we want to add new keys and values to it, we use a similar syntax to what we did with assigning to specific indexes in sequences. Except once again, instead of an index, we're putting a key in. So here we have a new key, and we put it in square brackets, and a new value. And we see now we have a key 3 and a value 3 added to our dictionary. If we want to change the value for an existing key, we can do this as well. And once again, it's very similar to when we change the value for existing items in a sequence, except that instead of an index number, we're using the key. So here we have key 2, and we're going to give it a new value. And we see that when we get key 2 now, we get the new value instead of the previous value. Now, dictionaries have some built-in methods, one of which is the keys method, which allows us to look at all the keys a dictionary has. So this is actually returning a special dict keys object, which contains all the keys in it. It is an iterable object, so if we're doing a for loop or some other iteration, we can iterate through this. We could also, if we wanted to, cast it to a list. Or do anything else we could do with an iterable. Now, similar to getting the keys for the dictionary, we can get an iterable that contains all the values using the values method. And you see we have a dict values object that has all the values that are contained in this dictionary. And once again, you can use this for iterating through those values as you see fit. One thing that's interesting is in the current version of Python, the keys have an order. And that order is the order in which they were put into the dict. In older versions of Python, the keys are unordered, and so you cannot have any expectation of this coming out with the same order whenever keys is called. But currently, you can, and so you can take advantage of that if that's useful to you. Another built-in method on dictionaries is the items method, and this returns an iterable that contains both the keys and the items, or values, as pairs. Let's pull that up. And you can see it's a dict items object with the key value pairs. Because it's an iterable, we can iterate through it. We'll talk more about iterables and for loops in a future lesson, but real quickly, let's just look at an example of we're unpacking the each item here with the key and value. So we see here key and value, and then we're printing them, and we're going through until we've done all of them. So there, we see that for each key and value pair, we print them as a separate line using the print function. That items method is something that I use all the time. I think you'll find that you do too. It's a really useful way for iterating through dictionaries and modifying and making modifications and values from the contents therein. We can use the same in sequence we saw with sequences to see if a key is in a dictionary. So the in sequence or in not sequence will look for key membership, not for value membership. So here we have key 3s in a dictionary. If we did a key that's not in our dictionary, it should return a false. And once again, this can be used with conditionals, with if statements, or anywhere where a Boolean value, a true-false value, is what we expect returned. Now, if we have a dictionary and we try to get the value for a key that doesn't exist, we're going to get an exception. However, there is a built-in get method. So we can do get, and let's go ahead and get a key. You can see this returns the value the same way that the square bracket indexing would. However, we can also with get give it a bad key, and instead of giving an exception, it returns a none object. We can supply a default, which will be returned if that key does not exist. If we want to remove an item from the dictionary, we use the del function. We call the function with the dictionary and the key whose pair we wish to remove. So here we're going to remove key 1 from our dictionary, and we can see that key 2 and key 3 remain, but key 1 and its associated value are removed. We mentioned earlier that lists are mutable and tuples are immutable. And one of the places where this comes into play is as keys in dictionaries. We mentioned that a dictionary is a form of a hash table or hash map. Because lists are mutable, they're not hashable. So what this means is if we take a list, here's a list, and we try to add it as a key to an existing dictionary, we'll get an exception, a type error, and it does say that it's an unhashable type list. Now, because tuples are immutable, we can take a tuple with the same items in it, and use it as a key in a dictionary, and it works just fine. So that's one of the advantages of tuples if you need to use them as keys in dictionaries. This has been an introduction to dictionaries. They're a really powerful part of the Python toolbox, and I think you'll find you use them all the time. Now let's talk about sets. Sets are a native Python data type which represents a non-ordered bucket of unique items. Creation of a set is simple. We can use the set constructor, and we can call it with an argument of some iterable. So in this case, we're going to use a tuple. We'll see we'll get a set. Notice our tuple contains duplicate letters. Because sets are unique items, there's no duplicates in the set. And the set is represented with curly brackets again. You can tell a set from a dictionary because a dictionary has the key value pairs, and the set just has a sequence of items, non-ordered sequence, of course. We can use any sequence to create a set. So if we pass a string to the set constructor, we'll see it creates a set of the characters in the string, removing any duplicates. So these are all the unique letters in the word Mississippi. We can also use the curly braces to create the set directly. And once again, any duplicates that we pass in are removed, and we end up with just the unique values. And if we have an existing set and we want to add to it, we use the set add method. So here we're adding the number 6 to our existing set, and it's put in there. If we try to add an item that's already in the set, it doesn't change the set at all. Sets have a pop method. Unlike a ordered sequence, the pop method on a set returns a random item from the set. So there's no guarantee as to which item the set will be popped first. Here we popped 1 first, but if we call it again, got 2, but it's not guaranteed to come in that order. The pop method, if the set is empty, will throw an exception, so that's something to keep in mind. Since sets have no order, you cannot use the indexing we used on sequences or slicing. So this attempt here to index into a set with the bracket and index number will in fact throw an exception because sets do not support indexing. We can use the in and not in syntax to check membership in sets, similar to what we did with sequences. So here we have an item, we want to see if it's in our set, and indeed it is, and it returns a Boolean. We can use this in conditionals just like we could with any of the other membership checking we've done. Now sets have some specific operations that are unique just to sets, and so let's look at some of those. First, I'm going to create 2 sets. The first is the numbers 1 through 7. The second is even numbers 0 through 8. So we'll see these sets have some numbers in common and some numbers that are different, which will help demonstrate. So we can use a minus symbol to get the items that are in the first set, so this set, but not in the second set. And we see 1, 3, 5, and 7 indeed are not in the second set. If you want to see items that are in either or both sets, we can use the bar syntax. And so this basically makes a new set that contains all the items. All of these set operations will return a set as their result. If we want to just see the items that are in both sets, so the items that are shared between sets, we use the AND syntax, and that looks like this. And if we want to see the items that are in either set but not in both, so not shared between the two, we can use the caret syntax, and we get that. This has been a quick introduction to sets. They're a powerful piece of the Python toolkit. Now we're going to talk about some third-party libraries that are not part of the native Python installation, but which are core to what every data scientist uses. The first is the NumPy array. NumPy is an open-source numerical computing library for Python. The NumPy array is a data structure representing a multi-dimensional arrays, which is optimized both for memory and performance. It's a huge part of the basis of a lot of data science in Python, and you'll see that other packages are actually based on the NumPy array. So it's the core of quite a bit of what we do. to create a NumPy array, first we have to import NumPy because it is a separate library. And here's an example of creating a NumPy array from a list of lists. So here we have a list, and each sublist has 4 items in it. And we create a NumPy array. We pass it into the NumPy array constructor. And what we get in response is an array, and you can see that its representation looks kind of like a list of lists. So the first list is the first row, second list is the second row, etc. It has some built-in methods for initializing arrays. If you want to initialize an array of zeros, we can use the NumPy zeros, and we give it its dimensions, in this case 4 and 5, and we get 4 rows with 5 slots in each row, 5 columns, basically. There's a similar ones method, which once again takes the dimensions as an argument and populates the whole array with ones. And so these are great ways if you want to basically initialize a matrix-like structure with some value and then start doing operations on it. So another way to start creating arrays is to use the arrange. We touched on the arrange function before. This is similar. So NumPy arrange on 9 will give us 0 through 8, or first 9 whole numbers. And you can see it gives this to us as a flat dimensioned array. Now if we want to take this array and then reshape it, there's a reshape function, and we'll call that here on the same one, and you can see we made it into a 3 by 3 matrix. So this is another way that we might commonly create a NumPy array. There's a lot of built-in methods for introspecting these arrays. NumPy arrays, unlike Python lists, do have a specific data type. So here's our array, and we see that it was created with an int64 data type. All of our items that we input were integers. NumPy will do its best to guess at what the best data type for your array is, but keep in mind that its guess may not fit your uses perfectly, so you may want to set that specifically. We can get the array's shape. So our array was 4 by 4, and it's 4 by 4. The size method, which tells us the number of items in the array, similar to the length of a list or a length of a sequence. So ours has 16 items. Then we can also get the number of bytes the array takes. So our array is using 128. Now, as I mentioned, you may want to consider setting the data type explicitly. So we can create an array here. And here we're going to set it to int 8. The guess that NumPy made on our original array was int 64. So we've created a new array from our list of lists. The array contents look the same, but note that the data type is different. What does this mean? Well, if we now call the n bytes and see how big it is, this array is only 16 bytes as opposed to the previous one, which was 128. So if you have a lot of knowledge about what your data type is and what you can restrict it to, you can use NumPy arrays and really be conscientious of the amount of memory you're using, which is important as they grow large. One important aspect is that because that data type is set, it doesn't change once the array is created. It's immutable. So if we take our array, which we know has a data type of int 8, and we try to add this nice float to the array, we'll see that that float is returned as a truncated integer. So it's not even rounded up. We've just truncated everything but the integer part. That can lead to all sorts of bugs if you're not aware of it. So be conscientious of what the data type of your NumPy arrays are and what data you want to be able to put in there. Well, we've just sliced into this array, so let's talk some more about array slicing. This is in some ways similar to the slicing we've already seen with the Python sequences. Let's just look at our array again. But now we're slicing into both columns and rows, and it's actually the rows first. So here we're starting at row 2 and taking all the other rows and starting at the first column and going up to column 3, but not including column 3. And we can see that row 2, 0, 1, 2 is this row, and we start with that row, and we see we start at the beginning, and we go up 0, 1, 2, 3, and not including 3, so that is exactly what we expect from our slice. It's important to note that these slices, when we slice into a list, what we get is a new list returned. A slice into a NumPy array is a window into the original data. This is really helpful when we're talking about really large data sets, because instead of recreating and using up memory with these new slices, we just have a window into the original data. It's one of the important features of NumPy arrays. Another distinction between a NumPy array and, say, a list of lists, which is a more primitive way of representing a matrix, is math operations. We've already seen with a list, if we multiply it by a number, what it does is it duplicates the length of the list, or creates the length of the list to equal that number. Okay, but the math operations on a NumPy array will act on the contents of the array instead of acting on the object itself, as it does with native Python lists. So let's create two arrays. Here's one, and here's another one. Notice we're using the arrange and the reshape to create two 3x3 arrays with different numbers. Now, if we use multiplication between these arrays, we'll see that the contents of the arrays are multiplied rather than the object structure itself. And the same is true if we use addition. So we can see here, with addition, 0 is added to 10, 1 is added to 11. With the multiplication, so you'll see that 0 was multiplied by 10, 3 was done by 13, get a 39. This is math operations that are more like what we'd expect in terms of using math with a matrix. There's also some specific matrix operations built into NumPy arrays. We can call transpose by calling t. We can see we've transposed our array. We can also do a dot product between arrays. So here's the dot product between the two arrays we started with. This has been a very cursory introduction, but I think it gives you a sense of the power of NumPy arrays. They're something that you're going to end up using a lot in data science, whether directly or through Pandas data frames. Let's take a quick look at the Pandas data frame. Pandas is another third-party library which is hugely leveraged in the data science world. The Pandas data frame is one of the data structures that you'll use more than anything else. It's a table-like two-dimensional data structure. Sort of, if you think of it as a table, that goes a long way towards understanding its behavior. It is actually built on NumPy arrays, so hence the power of those. So let's look at creating a data frame. We have to import pandas, and in this case we're going to create a data frame using three lists. The first list of first names, second list of last names, and third list of ages. Each of these lists represents the values in a column for our table. And the way that we're inputting them into the data frame constructor is as a dictionary with the title of the column and then the list of values for each one. Okay, let's go ahead and take a look at it. So we can see Colab does a nice job of presenting these, but we have our column headers here, and here's the contents of our columns, and then this is an index value that's put in for each row. There's a lot of built-in methods for introspecting on our data frames. One is head, which will look at the top items. And with head, we can use the number of items we want returned as an argument. So if we only want the top 3, we could do that. Or if we wanted more, if we wanted 10, we could get 10. Complementary to head, there's tail, where we want to look at the last items, the bottom items in our table. And in a similar way, it will take the number of items as an argument. One thing that I think I call almost every time I create a Pandas data frame with new data is the describe, which is descriptive statistics about that data frame. So here we can call describe on our data frame. And you see it gives us some information, means and maxes and counts and things that are useful in looking at our data frame, at least for numerical data. Now, accessing our data in our data frame, we can access it by column. And here, very similar to the dictionary syntax, we put in the column as an argument using the square brackets, and this gives us our column. And it's returning the column as an object. We'll talk about what kind of object a little bit later. That object that's returned is sliceable, so here this is the same sequence slicing that we've done before. So if we want to start from the fourth object and go to the end, we can see we start at number 4 and we go to the end. Now, we want to pull data from our tables sometimes, or our data frames, using conditionals. So if we want to only pull the rows that involve an age that's greater than 50, you see what we do here is we pull that column of the data frame, the age column, and then we compare it to the number we want to compare it with. And what this actually does is it then indexes into the data frame in a way that only returns the values that return true for that condition. So you see here we only get the columns where the age is greater than 50, which is something that you'll do a lot with data frames when you're exploring new data and you're trying to understand its shape and what its characteristics are. This has been a very quick introduction to Pandas data frames. You're going to use them a lot. There are whole books written about how to use these, but they're an integral part to what you're going to be doing with data science. Let's talk about Pandas series. Pandas series is a one-dimensional labeled array, and it can contain data of only one type. It's similar to a column in a spreadsheet. That's a good way to think about it. So to create a series, we can directly call the series constructor with some sequence as an argument. And we can see we get the values, and over here is an index. I think if we change these values to not match the index, it'll be easier to understand. So there. And you can see it has a data type, which is what we've seen before in the NumPy arrays. It has some introspection methods that we've seen before, so if we want to know the number of items, we can call size, and we can get the data type using dtype. And we see this one has 3 items, and its data type is int64, as we see up here. So the way you're going to see series a lot is a Panda data frame is actually composed of Panda series. So if we take the age column from our data frame, we'll see that that column is actually a Pandas series. So each column in a data frame is basically a Pandas series, and that's a good way to think about their interactions and how you use both of them. So the series have some built-in methods. There's a mean method, so here we have a series, and we just call mean to get the mean value. We can call unique, which is similar to casting it to a set. We can just see which values are unique in it, and we can get a max value or a min value. Anyway, you'll probably use the series mostly in the context of the Pandas data frame, but it's good to understand how they exist on their own. And I hope this introduction gives you a little bit of that. Thank you. In this lesson, you will learn about data conversion recipes in Python. You convert between lists, dictionaries, you convert a dictionary to a data frame, you learn to handle characters in integer conversions, and finally, you convert between different numerical types. So let's get started. Let's talk about doing conversions between lists and dictionaries and back. These are both basic elements of the Python toolbox, and you'll need to go back and forth in various ways between them many times. We already saw when creating a dictionary, we can create it from a sequence of sequences where the subsequences represent a key value pairs. So this is something we did when we talked about dictionaries already. Another way to get to the same result is to have 2 lists. So here we have a list of instruments and a list of performers, and to call the zip function on those 2 lists. And what the zip function will do is it'll actually create sublists that pair up the items in these 2 lists. And so we end up with a dictionary, once again, of keys, so keys in the instruments and values from the players. So another way to create a dictionary from a list is to use the _from_keys method. In this case, we're putting a default value in for all of the keys. And so if we were doing a game or something similar where there was a initialized value that we wanted to start at, in this case it's a race and there's a start distance of 0, this allows us to set that value easily for all the keys. So here's our keys, our start initialized value, and we can see it makes a dictionary with those keys all set to that value. In terms of converting dictionaries to lists, usually what we're going to want to do is pull out some aspect of the dictionary. So here's a dictionary we've created. Now if we want to get a list of the keys in the dictionary, we can actually just cast the dictionary to a list. And so you see it's just the keys, not the values. If we wanted to get these keys but have them in a sorted order, we can actually just call the sorted method on it, and you can see that it returns them sorted. To get the values, we have to call the values method, which we've talked about it before. So here we see all the values come out, so that's only the values and not the keys. So we've seen some of the ways that we can go back and forth between dictionaries and lists. They're both integral parts of what you're going to be using in Python, and being able to move back and forth between them is a powerful but simple methodology. We've already talked about Pandas data frames as being one of the most powerful and most used data types and data structures in data science. Going back and forth between data frames and DICs is something that you'll have to do quite a bit for various reasons. So let's take a quick look at that. We can create a data frame using a dictionary. So here we have a dictionary, and this is similar to the way we'd create a data frame before. We have the column name, and then we have a list of values, or a sequence of values. And we call the data parameter, and we can see we get our data frame with the columns as prescribed and the values for each column appropriately. There's also a data frame _from_dict method, which we can pass in a dict of the same format and get the same data frame out. We've talked a little about how data frames have an index, so we can use that index. And so instead of creating a data frame with a dictionary where the keys represent the columns, here we have the keys representing the index, and then we're setting the columns explicitly after we create the data frame using the _from_dict method. So we can see here, for index 0, we have this row. For index 1, we have this row. So we have an index, and then the sequence that follows the index in the dictionary actually represents the row instead of the column in this case. And then by calling the columns method afterwards, we can name our columns explicitly. So here we have a dictionary of key values that's flat. And we're going to create a dictionary by listing the items in this value and then setting the columns. So remember, when we list the items, we're getting both the keys and values. So this is just another way effectively of creating the nested sequence of sequences of key value pairs. And this has been a really quick look at how to go from dictionaries to data frames. In most cases, your data frames will probably come from data sets that are in either CSV or other outside data formats. But it's good to know how to create a data frame on the fly from a dictionary. It comes in handy from time to time. Let's talk about converting between characters and integers and back. If we want to cast a string to an integer, we can just pass that string to the int constructor, and you can see we get, as expected, a number in base 10. But the int constructor will actually take other bases as an argument. So we can do base 2, and the 0, 1, 1 becomes 3. We can do base 6, or 8, or 16. So it's a very straightforward function to cast to an int, just keep in mind that if you want to use bases other than 10, that you need to explicitly specify them. Now, if we want to cast an int to a string, it's even simpler. We just call the string method, and we can see that what we get back is of type string. Both of these, going to ints and from ints with strings, is a really basic and easy thing, but it's something that you need to be aware of doing and know how to do on the fly. Now let's talk about converting between some other numerical types in Python, specifically hexadecimal, binary, and floats. If we want to cast a float to a string, it's as simple as using the string constructor and calling it on the float in a similar way that we have with ints and other objects. And we can see that the string that results is a string, and it has the representation of the float. So that's very straightforward, and that's pretty much true with the string method on most types of objects. Now, if we want to go from a string to a float, so here we have a string of the float 12.3, we can just cast it to a float using the float constructor. In a similar way, the object that comes out is of class float and has the value of 12.3. Notice in the string case, when we called repr on it, it wraps it in quotes, and in the float case, it does not. Now, if we want to go from an integer to a hexadecimal string, we can use the hex method. And so here we're calling hex directly on the integer 18. And you can see it returns a string with the hexadecimal value as the value of the string. If we want to cast a float to a hex, floats actually have their own hex method on them. So we have the float and then call .hex. And there we can see it returns a string with the hex as the string's value. Now we want to convert to and from binary. We should talk a little bit about a bytes literal. We've talked about other sequences, strings, raw strings. If we take a string object and prepend it with a B, it makes it into a bytes literal, which is based on an ASCII encoding of characters. So here is a bytes literal, and you see it's of type bytes. So if we want to do encoding, we can take a bytes literal. Here it is, encode this string. Then we want to encode it using base64, and we can see what we get here. And here's the encoding, and it's of type bytes. Now, if you want to decode it, we can use base64 and call decode on the encoded string, and you can see it comes back as the original value of the string. So that's a quick run through of converting with non-integer numerical types. Most of it is in Python is very simple as casting in most cases, but it's something that will come in handy when you're working on data science.
In this lesson, execution control plays a center role. You'll learn how to use the control of execution to make programs in Python. You learn to use for loops, you learn to execute while loops, you learn to handle exceptions. Finally, you use conditionals to branch between statements. Let's get started.
Let's look at Python for loops. For loop is one of the most fundamental control structures in Python. We've talked a bit before about iterators, and a for loop basically allows you to iterate through an iterator item by item. A common iterator that's used in for loops is the range type, which comes from the range function. We've seen this a little in some previous examples. So here we're calling range with 3. We're actually casting it to a list so that you can see what it looks like, but we can look at it on its own too and see we have a range object that goes between 0 and 3. So the way a for loop works is you put the term for, and you put a variable, which is the variable which will be assigned the next item from the iterator. So in the range object, the first I will be assigned to a 0, and then the next to a 1, 2, and so forth. So here we're just calling print on the I so you can see how the iteration works. The for loop can iterate over any iterable, which includes all sequence types. So here we have a list, and we can iterate through that list and print out an F string that's based on the contents of that iterable. And this is something you'll see a lot in Python. Iterating through lists or iterating through range objects are two of the most common ways that for loops work. Now let's take a quick look at while loops. The syntax for a while loop is the word while followed by a Boolean, or actually it's a Boolean detection code, so it could be the existence of any object. And as long as it evaluates to true, the loop will continue. We have an example here. Well, here's our while loop. And we see it's calling next on the animals. Now, animals is basically an iterator that returns the contents of this list here. So there's whale, orca, porpoise, and Moby Dick. Each of these will be returned with each call of next to the animals iterator. So what this is saying here in the while loop is as long as the returned item does not equal Moby Dick, it will continue the while loop. We have a count that goes up. So this is the count is set to 0 here, and the +1 syntax increments the count up by 1. Then we're doing a print statement using that count. If the while loop ends, then the else is called at the very end, and we have a print statement based on that. So let's go ahead and run this. And so you can see the output. First we print the number of creatures in the sea, and then we iterate through, each time increasing our counter, until the animal returned equals Moby Dick, at which point the else is called, and we fire our harpoon. Now let's talk about exceptions. An exception is an error that is thrown and basically stops at the execution of the code. We've seen exceptions before in trying to use a bad key in a dictionary and other examples. It's important that when you're working with code that you learn how to handle exceptions because they will come up and you don't always want your code to stop in the case that they do. In handling exceptions, we use a try except block. Basically, we wrap the code that we think might throw an exception in the try section, as we can see here, try. And then we catch an exception with the except block. Here we're catching an individual exception called index error, which is what you get from a list if you've popped all the contents off. So you have an empty list and you call pop and you'll get an index error. So what we have here is a loop, a while loop, and we're calling try when we're doing the pop and printing out the contents. And then if that pop does throw an index error, then we call this string, and we call break to break out of the loop. So let's go ahead and run this. And we see that our loop outputs the text until we've popped all the whales off the list. One important note when catching exceptions is the best practice is to catch the very specific exception, be as specific as you can about what you catch, because you don't want to catch unintended exceptions which may indicate an error that you do want to stop execution for. One important thing when catching exceptions, especially in production code, is to log information about the exception. And we do this using the logging module, which we see here. We have the same list of whales and the same while loop, with the exception that when we catch this exception, now we're calling logging and the exception method on logging to log that exception. You can see what this looks like quickly. And you can see what this does is it logs out the exception, the type of exception, and where it happened. Now this really comes into play in production code. When you have lots of different code running and something goes wrong and you're trying to track down what caused your errors, having good logging is really important. It's what makes the difference between quick fix and days of downtime. And this has been our introduction to exceptions, an important thing to understand, especially when running in production code. Now let's talk about conditionals. There are a number of types of conditionals. The if-else is the main one, and we'll also talk a bit about how to use the break statement, continue, and pass statement. So the way an if block works is it checks a Boolean, and if that Boolean is true, it executes some code. So here we have a function named recommend whale, and we pass in an argument that it's an emotion. So our first if tests if that emotion equals the string angry, and then executes this code if that is the case. The way an elif works is basically if this is not true, then it falls through to the next elif, and that also checks the emotion versus happy, and if that's true, it runs its code. Now if neither of these runs, it falls through to the trailing else, and then that code is run. Okay, let's see how this works. So if we call our recommend whale function with the argument angry, we expect the first statement to run, and we see it does. It says, you are very angry, and I have just the whale for you, Moby Dick. However, if we change this from angry to happy, then we get Shamu. We can try entering something that is neither of those first two arguments, so neither happy nor angry. If we do sad, then we see it falls through to the third statement, the else statement, and we get a crocodile. Another thing we can do with if-else is run them as a single line assignment. So here we have an if-else that is assigning a value to a variable. So we have a variable called cloudy, and it's set to true. We have a variable called happy, and it's false. And then we test. If cloudy is true, then we set happy to false. And if it's not, we call else, which will set it to true. When you're doing a conditional that assigns a value to a variable, such as this, let's look at this example. We have cloudy set to true and happy set to false. We say if cloudy, so if cloudy is true, then happy is set to false. And if that's not the case, it hits the else, and the happy is set to true. In this case, cloudy is set to true, so happy is to false. If we change it, we can see that then happy is set to true. However, this kind of conditional to set the value of a variable can be rewritten in one line. So there's a handy syntax which says this. You say happy equals this kind of one-line function can make code much more readable if there's not a lot of complication in the conditional that's called. Now let's talk about using the break statement. We did see a break statement earlier in a while loop. Basically, a while loop that says while true will run infinitely if left to its own devices. So here we have a while loop. We set a variable called crew members to 0. And we say while true, we increment up the number of crew members. We already mentioned that the plus equals 1 will increment the variable by 1. And then we have a print statement. But the interesting part here is that if we check the number of crew members, if it's greater than 3, then we have another print statement, but then we call break. And what break does, it will end the while loop's execution. So let's run this one. And we can see here that we run through the first print statement for every crew member up to crew member 4, and at that point, since 4 is greater than 3, we run the second print statement and break from the while loop, and we don't print anymore. And it looks like Moby Dick is full. In terms of conditionals, another breaking function is called the continue. So here we have a variable set to a list of whales, and we're iterating through the whales using a for loop. But then we have a conditional which says, if the whale is not Moby Dick, we continue. And what continue does is it breaks out of that iteration of the for loop. So we'll see what this will do is it only reaches the print statement when the whale equals Moby Dick. In all other cases, the continue is called, and the iteration continues, but the statement is not printed. The last keyword we'll talk about now is the pass keyword. Pass is basically used for making placeholder functions and placeholder objects. So if you're developing code and perhaps you want to set up the framework of your code before you write unit tests for it or something like that, you can use pass to create a function that doesn't do anything. So here we have a function, we put pass there, and the function does nothing. But if we didn't have the pass there, Python won't let you have a function with nothing there. So you see we need the pass. We can do the same thing with a class. We're not doing a lot with classes, but so here we have a class, we put pass on it, and we instantiate that class. And you can see that what we've done is made an instance of that class, even though the class has no contents and does nothing. So this has been an introduction to execution control in Python. These are all basic control structures that you'll use again and again, and are really a useful and readable part of the Python arsenal. In this lesson, we'll learn about functions. You'll learn to write functions. Lessons will include using functions and function decorators, composing closures, and writing lambdas. Finally, you create advanced use of functions. Let's get started.
Let's talk about writing and using functions in Python. Functions are really interesting because they're the building block of distributed computing. Here's an example of a really simple function that demonstrates this. So we have a work function. Inside it has an input. Inside there's a process that happens. So that input has one number associated with it, and then it's returned via this output. There we go. If you go ahead and you pass that in. So really simple example, but this in a nutshell is really what happens with machine learning, with distributed computing, with concurrency. And it's an important thing to study is this concept of a unit of work. There's something that comes in, there's something that happens inside of the function, and then it returns back a value. So we're going to build on that throughout the rest of this lesson. So let's go ahead and look at some of the key components of a function. One of the key components is a docstring. Here's an example of a function called docstring. And to create a docstring, what you do is you make triple quotes and then you put some documentation inside. Go ahead and call that function. And then to actually run it, all we need to do is go ahead and put a question mark here. And what happens is you'll see that it pops up a help menu and it shows us that exact docstring. So if I go through here and I add a exclamation point and then I run this again, you should see now that's changed. So a great way to actually document what you're doing, even if you're using a Colab notebook project and not writing, let's say, projects that are more software engineering based, docstrings are a great way to communicate your intent. Another key component of a function is arguments. So again, that's the input to the function. And there's really these two styles in Python. There's keywords and positional. Positional is order-based processing, and keyword is key value processed. So let's go ahead and look at positional here. If I go ahead and I define this function positional, there's first, second, third. There's some arguments that are processed. What we can see here is that I'm going to print out each one of these arguments as they're actually called. So here we go, positional 1, 2, 3. You can see that it was actually processed in the order that you would expect, right? So first, second, third. First is 1, second is 2, third is 3. But one of the problems with positional is that if you accidentally forget the order, things can get messed up. So here we say process first, and it turns out because I put 2 here, now actually that's not what I intended, right? And if I go to third, it says 1. So one of the problems with this is that you can really make a very subtle mistake quite easily, and a solution to that is to use keyword based arguments. So let's go ahead and take a look at how we could do the same thing with a keyword based argument. So I make a function called keyword, and here we have first is equal to 1, second is equal to 2, third is equal to 3. And now we can see that I can process this in any order I want. So again, I'll do the same thing, keyword 1, 2, 3, but now what I'm going to do is I'm going to use keyword arguments, and you can see that even though I actually pass second first, and I pass first third, it still comes out process first 1, process second 2, process third 3. So this is really a key learning, and it's really important to know that you can prevent a lot of errors by just using keyword arguments instead of positional arguments. Another thing to point out is that also because keyword arguments can store default values, It also can be easier to call a function because it can retain, in this case, the first argument and also the third argument. So definitely recommend preferring keyword arguments versus positional arguments. Let's also take a look at the final key component of a function, which is the return statement. So here, if we look at this function called bridge to nowhere, it does nothing. And if we call it, and I actually do an equality statement here where I compare it to none, you can see that it is in fact none. If you actually want to go even deeper, you can even do this, type bridge to nowhere, and you can actually see that yes, in fact, it is a none type. So what do you do if you want to return something? Well, you explicitly need to call a return statement. In other languages, actually the last line would be returned, but in Python you have to explicitly return something if you don't want none to be returned. So here's an example of a function called more than 0. And what this does is it returns 1. And if we go and we look at this, you can see that it actually does return 1. Now, one final thing about functions here is that a function, not only can it return something like 1, but it also can return another function. So this might blow your mind for a second, but let's go ahead and take a look at this function called inner piece. So this is a very deep function. What this does is it actually has a function inside called piece, and it returns piece. And then if you see here, this what it actually is returning is it's returning this inner function, right? So here's an outer function called inner piece. Inside there's another function called piece, and that function actually returns the string piece. So if I go ahead and I tee this up, and I actually make an instance of inner piece here, and I actually assign it there, you can see that I can then call that function that was returned, and it says, hey, I need that piece. So let's go ahead and take a look at this a little bit more detail here. So if I say type, and I make an instance of inner piece here, there we go, and we'll call this inner2. Let's go ahead and run that. And then let's go ahead and look at what the type is. You'll see that it's actually a function. Right, so it's a very powerful way to distribute functions and distribute logic, is to have a function that actually returns another function. We're going to get into some more advanced use cases of that in a little bit. In this example, we have a decorator that we're going to actually be using, and we're also going to talk about writing decorators. So let's go ahead and look at using decorators. In Python, it's really common to use decorators for things like dispatching a function via command line tool, or dispatching it via web routes, or for speeding up Python code. So here's an example of how you could write a very simple command line tool that actually does something. So here I actually use this special magic function Python, which will invoke a sub process and actually run this in Python. And I import the click function, and then I write a function here called less than 0, and what it does is it returns Iron Man and it returns -1. So this is really the bit of work that's actually being done. Then inside of here I create a click command, and so that's that dispatch that will actually run this from the command line. Now what I do is I call that function, and then I echo it out here. Here we go. If we run this, you can see it says Robert Downey Jr. is versatile, and it returns back Iron Man, it returns back -1. And you can see that really the power is that you write a function, and then I put a decorator on top to route that function to the command line. But also this function could live in a module somewhere, and maybe it could be run in the cloud, or it could be run using some deep learning framework, or it could be run in many different aspects. And really this is the power of that decorator-based workflow, is routing something to a specific type of function or a specific type of utility. Now let's go ahead and take a look at how a similar thing could be run in, let's say, a web app. So here's an example where I actually use write_file, and what write_file does is it takes a cell and writes it out to a cell. So let's say I was writing a very simple web application that I was going to share with one of my coworkers. Well, I could use this approach. I could import Flask, again, create that same function, and then I could actually create a route here and actually return back that exact same function via web request. So you can see here that it goes ahead and it writes it out. And then if I wanted to call it, if it was running somewhere, it would look something like this. What you do is you do curl, localhost 5000, and if you did that, it would return back that exact same dictionary that we defined earlier, right? Here we go, and we'll put this out like that. Yet one more thing you can do with a decorator is that you can actually use a just-in-time compiler using NumPy. So let's go ahead and see how that would work. Here's a function called crunchy normal. And what this does is actually just adds a bunch of numbers together, right? So I have a count at 0, I have a huge number, and then basically I iterate over that huge number and I keep adding things to this count here, and then I return back the count. So if I tee that up and then I do a time, this is regular Python. You can see it takes almost a second, right? Because this is a really expensive operation. But if I use this NumPy just-in-time compiler and I use a decorator on top, I can take essentially the same function and I can actually run it with a just-in-time compiler, and that'll actually let me run this as machine code. So now if I do a timer, you can see that it actually is about 5 times quicker, right? So this is almost 200 milliseconds, and the other one was almost a second. So much different runtime characteristics when you actually use this just-in-time compiler. And really the key takeaway, again, is this decorator, right? So you can see here there's a pattern in Python where you create a function, it does something powerful, and then if you want to dispatch it to some unique framework, you just put a decorator on top. So you can do machine code, you can do web apps, you can do command line tools, and they all work with this decorator on top. And now that we've used decorators, let's talk a little bit about writing your own decorator. And here's an example of a decorator that we're going to use to both time, debug, and also instrument code. So what I do first is I say from functools import wraps, and what wraps does is it allows me to wrap up a function in a way that makes it clean to make a decorator. And then if you see here this instrument decorator, what it does is it takes in all arguments, it takes in all keyword arguments, and it creates an instance of time.time. And then I actually take the result, that was the result of the function, and then I take, again, the time, and I basically am able to take the name of the function, all the arguments that are passed in, all the keyword arguments that are passed in, and also the duration that it took, and actually return all that back as a print statement. So it's a great way to debug code. Now if I go through here and I do some simulated work, so I write a very simple function that goes through and it just sleeps and prints out a sleep, I can instrument how long that would take. So here we go, I add that decorator on top, and now when I go through and I simulate this work, you can see it's going to take about 3 seconds, and then it prints back the name of the function, which is simulated work. It returns back the argument that was passed in, the keyword argument that was passed in, and also the duration. And then finally, this is the last statement, which is processed inside the function. So you can see how powerful it is to write your own instrumentation code. So maybe you want to change this, it's very easy to change, but it gives you this ability to reuse code, write your own custom logic that helps you understand what you're doing. And you can see how decorators are an extremely powerful and advanced feature of Python that really even a beginner can begin to use and take advantage of. So let's talk a little bit about functions with state. and closure function. So really what a closure function is it's a function that has another function inside. And if I take a look at an example of how that would look, I created a calorie counter function. And inside of here, what happens is I have some protein, I have some fat, I have some carbohydrate, and I also have a total. And then inside I have a nested function here. So that's all the logic right here below. And so this outer state is going to be modified by this inner function. And the way to do that with Python 3 is that you can declare a non-local variable. And what's powerful about this is it means that this inner function can mutate the state right above it. But if there was something above this calorie counter, like a global variable, it wouldn't change it. So it's a very safe way to keep track of state when you're using functions. So it's an alternative really to using objects. So if I take a look at how this would work, when I pass in food into this calorie counter, if it's protein, it's going to go ahead and it's going to add 4 because there's 4 calories in protein. If the food is a carbohydrate, it's going to add 4 calories. And then if it's fat, it's going to add a total of 9 calories. Now if I go through here and I look at total, it's going to be protein plus carbohydrate plus fat. So it's going to take those totals and it's actually going to then mutate this total. So all 4 of these values are going to change throughout the course of this function. Finally, what I do is I print out not only the total, but each breakdown. So the carbohydrate, the fat, the protein, right? So you could see how this could be an interesting part of, let's say, a data science workflow. So I'm going to go ahead and tee that up. And now what I'm going to do is I'm going to make an instance of this closure. So I have this meal, and it's now assigned, the meal variable is assigned from the calorie counter. And if I, again, run the type, you can see that it's a function, right? Because this inner function is returned by this outer function calorie counter. So I'm going to go through here and make an instance of the calorie counter, and it's going to assign that to meal. And if we look at the type of this meal variable, you can see it's a function. And why it's a function is that it's taking this inner function here, calorie counter inner, and it's returning it back. So now what I'm going to do is I'm going to start passing in food, and this outer function is going to keep track of it. So here we go, meal, carbohydrates. You can see that it prints out consumed 4 calories of protein, I'm sorry, 4 calories, and actually 4 of that is carbohydrates. And now if I pass in fat, you can see that it's now incrementing up, and there's 13 total, and that's going to be 1 fat gram and 1 carbohydrate gram. Now if I go through and I pass in protein, you can see that it's incrementing up. So what's really powerful about this is that I'm able to actually get these intermediate results, and also at the same time I'm able to reuse this function, and it's able to keep track of the state. So this could be really powerful in, let's say, a machine learning pipeline where you're going through and you're calculating a bunch of intermediate results, and I don't have to worry about these variables being mutated. So this function, for example, maybe it's the individual calories of millions of people, and it's all being run in some machine learning pipeline. These functions could be distributed out to many different machines, and they could be run and calculated, and each one will individually be able to generate both the end result and also these intermediate results. So a really powerful concept for distributed computing. All right, let's talk a little bit about lambdas. Lambdas, for some reason, just never go away in Python. You see them all over the place, and basically every new generation of Python user, you'll see them start to explore lambdas, and they'll start to get really enamored with them. And my advice is that you need to think about YAGNI. And it's a great acronym. It stands for a yink and a need it. And with lambda, really you don't need to use a lambda. Here's an example where I create a function, and it looks really cool, right? It has x, and then there's x to the x exponent, and if I call it, it's all in one line of code, and it returns back this value. But I can do the exact same thing by writing a function. So here is the exact equivalent function, and I call it expo. And if you look at the two differences here, this is potentially very unreadable because it's all nested on one line of code. And in fact, in Python, if we go through here and I show you import this, what we have here is the Zen of Python. So this is something that has been around for decades. And I won't read the whole thing, but a few different things here are simple is better than complex, complex is better than complicated, flat is better than nested. In a nutshell, what they're saying here, I mean, this is built into language, is that, keep it simple. And unfortunately, if you look at lambdas, it's a way of taking something that's very simple and making it more complex and less readable. And so really my recommendation is to try to avoid using lambdas, because you can do the exact same thing with functions and there's really no advantage to it at all. That being said, let me show you an example. Even if you're not going to be writing lambdas, you probably will have to have some close encounters with lambdas. And one of the ways that you may see it is something like this. So let's say there's a Pandas data frame, and inside of here there's a series that's created. You may see someone do this. So you may see someone say series.apply. And again, the thing to remember here is that, and we can actually just code this up right now, is it's just a function that's being passed in, but it's a less readable function. And I don't know why a lot of the Pandas documentation has a lot of lambdas in it, but unfortunately they do the same thing. So instead, right here, if you look at this, this looks almost like gibberish. I can just go like that, and I can just type in expo, and it does the exact same thing. So to me, I would say this is much more readable than this. This sounds like, someone is having some fun and playing around with code. And my recommendation is, even when you have to encounter lambdas, just remember that you can reverse engineer it and turn it back into a function. And that's my advice, is to stick with functions and try to avoid your close encounters with lambdas. Now let's talk about some advanced uses of functions. So we've gone through and we've established how functions are really powerful units of work, and they can be used for dispatching things, distributed computing. But what about data science workflow? So one of the ones that we're going to cover, and we'll also cover in other lessons, is applying a function to a Pandas data frame. So here's an example of a data frame that has some nutrition data. I'm going to go ahead and import this. You can see it's got fat, carbohydrates, sugars, protein. And so what I'm going to do here is I'm going to create a function that actually classifies a new feature. So what I'm going to do is I'm going to make a new column that shows whether something is high protein food or low protein food. So what it's going to do is it's going to take each value and it's going to return back high protein if it's above 80 grams of protein, or otherwise it's going to return low protein. So the way we're going to use that is we're going to create a new column, and here's the column high protein, and then I go and I take that existing 100 gram column, and you can see here's some of the example values, and then I'm going to run apply. And so what this does is, row by row, it goes through and it takes this function and it actually creates a new column that's one of these two values. So when we go ahead and we run this, now you can see there's a third column here called high protein. And what we can do is we can actually do a describe now as well, and you can actually see what this looks like. Here we go. And you can see actually that it's not a numerical column, it's actually a categorical column, and so it doesn't show up in this display. So this is a great way to actually do feature engineering, is to, again, write a function, have that function take an existing column, do some kind of transformation to it, and then potentially now what I could do is I could classify foods and predict whether there would be high protein or low protein if I didn't have that value, for example. Now let's go ahead and look at another interesting way you could do an advanced technique with functions, and this is a partial function. And what we do in this example here is I import from functools partial. And here's an example of a function that takes two columns. And in this first example, I have a sort, and I actually can sort by two columns at the same time, and I tell it to do ascending false for both. So with Pandas, that's one feature that you can actually take advantage of, is you can actually sort by columns and then additionally sort by a secondary sort on another column. So what I'm going to do here is I'm going to take this function and allow it to basically have a partial assigned to it. So what happens is I assign a multi-sort here, and I use partial, and I pass that in. So what this does is it essentially tees up this function, but it doesn't fully execute it. So if I run it, you can see that I was able to actually create a partial function that has only one thing that's actually assigned to it. So I have a sugar column that I'm going to sort by as my primary sort, and then I can actually pass in a secondary sort key whenever I want. So if I go through here and I create an instance of this and I pass in fat here, you can see that I've actually been able to now do a secondary sort on fat. And what's really powerful about that is now I can actually say find sugary and fatty foods, and actually I can get the results here. And you can see here that it is actually doing this secondary sort. So the first one, you can see these are all very high values, and the second one is being able to find that. Now I can do it again, because again, remember that it was already been teed up to look for sugary foods. Now I'm going to look for sugary and salty foods. So if I go through here and I run this, now I can see that again, the sugary food is at the top, right? But then there's a secondary sort by salt, and you can see these are all salty foods as well. So a great technique actually with Pandas. I've had people ask before, about partial functions and what could be a good use case for them. Well, this is exactly a good use case for them. Is you create reusable code where this is essentially one problem you've solved, right? So you've written a function that can do sorting and return back multi-column sorts, and then you've written a second function that actually can do sugary and fatty foods, and then you have a third function. And what's great about all this is I didn't have to modify this code, right? So partial functions allow you to create many different workflows out of one piece of code. Another thing to point out about this partial function as well is I could see how you could, let's say, run thousands or millions of these partial functions and all tee them up with different configurations, and then as they get processed through some pipeline, each one of those gets triggered with their final value. So it's a great way to do pipelining as well. So if you haven't had a chance to take a look at partial functions, take a look at this example and play around with it a little bit, and I think you'll find that partial functions are really powerful. In this lesson, you'll learn to use common data science libraries in Python. You learn to use NumPy, then you learn to use SciPy, you create solutions with Pandas, you learn TensorFlow basics, you use Seaborn to create plots, you create beautiful interactive data visualizations in Plotly, you create specialized visualization library solutions. Finally, you learn natural language processing. Let's get started. Let's talk a little bit about NumPy. NumPy is a foundational piece of many of the data science libraries in the Python ecosystem. I like to think of it as a low-level, multi-dimensional array library. And if that's a mouthful, an easier way to think about it would be a programmer's Excel. So really it's a columnar structure, or it has multiple dimensions that you manipulate. The building blocks of NumPy are really the foundation for Pandas. They're the foundation for sklearn and also for TensorFlow. So having some understanding of NumPy is going to be really helpful. So let's go ahead and do a hello world NumPy to see what NumPy is all about. So step one, we're going to go and import NumPy as NP. That's really the convention that you'll see all over the place. And then let's go ahead and make a very simple array. So if you see here, there's a convention that a lot of times when you make an array, you call it A. And then what I'm going to do is I'm going to make it of a size 6, and a shape is going to be a 2 by 3 array. There we go. And now let's go ahead and print the shape out. So if we see when you print out the shape, you can see that it is in fact 2 by 3. And then if we print the size, you can see that it's actually a size of 6, right? So it's 2 times 3. And finally, we also are going to print out the type. You can see that these are int64 types that are stored inside of that array. And then really the last step here is to actually look and completely see the inner workings of this. So you can see that from a horizontal structure, there's 3, and from a vertical structure, there's 2. So this would be a 2 by 3 array. So this is a great little sequence to play around with if you're having trouble understanding a NumPy array, and it will give you a good feel for how to manipulate things. So now let's go ahead and create an array again, but do a very specific one-dimensional array. In order to do that, we're going to look at, again, making an A variable, and I'll just put in 2, 4, 6, 8, and then I'm going to print the shape, and I'm going to print the actual contents. So you can see that this is also a great way to create arrays, is you can specifically populate them with what you want to populate. In addition, you can see the actual contents there as well. If we want to make a two-dimensional array, what you do is you use this syntax where there's square brackets on the outside, and then there's these parentheses that have one set, and then parentheses that have the other set, and this will actually make a 2 by 2 array. So you can see this is the first part of the array, and this is the second part of the array. And then if you look at the shape again, it's 2 by 4, right? So there's 4 here, 4, so there's a total of 8 items inside. So this actually is a really important concept to understand. You'll see this a lot when you're doing things with sklearn, for example. If you have, let's say, a one-dimensional data structure or a two-dimensional data structure, you may need to reshape it so that you can do machine learning modeling. And if you ever get stuck, you can come back to this notebook and actually play around with a little bit and get a feel for how that would work. Another really important thing you can do with NumPy is you can also create a sequence, just like you can create a sequence with regular Python. So we're going to go and do that by using npRange. And what I'm going to do is I'm going to have this npRange create a 1 through 20 sequence. And you can see that the shape is 19. So starting at 1, there's a total of 19 items inside. And it's, again, a one-dimensional array, and I'm able to populate it with a sequence. So this is also a great way to potentially create a test data set. Finally, I want to show you a way that you can create an empty multi-dimensional array. So there's something called NP-zeros, and this is a kind of a great way to really play around and maybe even do some unit testing if you're going to do some unit testing around NumPy arrays. So what I do here is I say A is equal to NP-zeros, and I do a 2 by 3 array. And then you can see that the shape, again, gets printed. It's a 2 by 3 array, and then you can see the contents. There also is an NP-ones, and you can populate it with ones as well, but this is a great way also to play around and really get a feel for it. Now let's move on to some applied NumPy. So as we were talking about earlier, NumPy is this foundational piece for a lot of the data science libraries in Python. And so one of the things you can do with it is actually use it to do more mathematical computation. And in particular, one of the really fun mathematical computations people like to do is create a Mandelbrot. So I'm going to use NumPy to do that. So I import NumPy right here. And then I'm actually going to have a timer so I can time how long it takes. You can see this is the NumPy operation here. I'm going to go ahead and load that. And then I'm going to create a fractal in this next section here. So again, you can see there's some NumPy type operations happening here where something's getting shaped around. We'll go ahead and run that. And then finally, again, we see that some of that other code that we were playing around with earlier, that boilerplate code where you can see this is quite a large array that's been created with zeros first, and then it actually gets populated with data later. So let's go ahead and run this. Let's start back here again. So we'll go here, we'll go here, we'll run this code. And then what'll happen is that it'll actually take a few seconds here, and it'll actually create this really cool Mandelbrot image, right? So it's a random visualization that really shows the power of how NumPy arrays can be used. So this is definitely a great thing to know about, but one of the really powerful things you can do is use NumPy, which is a just-in-time compiler, to do that same operation, but to massively speed it up. So what we're going to do is we're going to say from NumPy import auto_JIT, and then we're going to do the exact same code, but each one of these pieces of code is now going to be converted into machine code. So orders of magnitude faster. And again, if we look before, this took about 5.6 seconds. Now if we use the same code and just put a decorator on it that makes it run in NumPy, we can actually have it run in a fraction of the time. So you can see that that's another really powerful thing that you can do with NumPy, is it has this really high performance just-in-time compiler that you can actually use. So really powerful tool set to know about, and one of the advantages of knowing that low-level aspect to NumPy. Another thing you can do that's really powerful, and it works with a Colab notebook, is that you can actually go through here and run CUDA versions as well. So this was just turning it into machine code, but if we wanted to, we could actually go through here and add a CUDA just-in-time compiler, and what that would do, it would actually do that same Mandelbrot and actually use the GPU as well. So there's some really powerful things that you can do on your own, and I would encourage you to check out NumPy. Even if you typically don't use it directly, you can see that there's some really incredibly useful things that you can do if you understand that low-level version of NumPy. Let's talk about sklearn. If you're doing data science in Python, you are going to come across sklearn. It's really the 800-pound gorilla of machine learning and data science at Python. And a few of the things you're going to do are you're going to do supervised machine learning in terms of classification, or you're going to do supervised machine learning in terms of regression, or you're going to do an unsupervised version in terms of some kind of clustering. So we're going to go over 3 different types of examples here. We're going to start out with a supervised machine learning problem and walk through that workflow. So in this example, let me just define a few key terms here. In terms of doing a classification problem, a lot of times you'll look at precision, and this measures the fraction of actual positives among the examples that were predicted as positive. There's recall. This is the fraction of actual positives that are predicted as positive. F1 score, the weighted average of recall and precision. And AUC, area under the curve, this measures the ability of the model to predict a higher score for positive examples as opposed to negative examples. And then also there's a false positive rate, which is the ability to measure a false alarm. So a really good example of the false positive rate and why you want to customize it for whatever model you pick is if you were doing, let's say, image classification, and you were trying to detect a cancer in, let's say, prostate or breast cancer screening, you want to be pretty careful about telling someone they have cancer because of how disruptive that could be to their life. So you want to really minimize that, false positive rate. So let's go ahead and look at this classification data set. So I'm going to use the digits data set, and you can actually import that from sklearn. This is a great place to find data sets to play around with, and a lot of times the data sets that are included are really good to use initially as you're getting comfortable with something, like a library like sklearn, so that you can understand exactly how they do something. First, matplotlib is imported, sklearn again is imported with data sets, and then this digits data set, which is the handwriting data set's loaded. We go through here and kind of clean things up and show a picture. And now, in order to apply the classifier, again, here's our NumPy interface here as we reshape the data frame. And then I go through and I use a classifier. So this is a support vector classifier, and then I fit that to the model, right? So I say classifier.fit, and I actually break up the data so that I train it on one half of the data, which is a common way to do training. And now the prediction is actually set right here. So I say expected digits.target, and I classify those handwriting samples. So let's go ahead and run this and see what it looks like. So when you run, it actually goes through and it gives you a classification report. So you can see there's precision, recall, F1 score, support. So all these ways of figuring out how accurate the model is. And then there's a confusion matrix that's printed at the end. And what this confusion matrix does is it shows you how many accurate training examples you have and which ones were inaccurate. And so you can see here, this is 0, 1, 2, 3. You can kind of see what the model actually predicted those results to be. So this is really a great example to play around with. And what I would encourage you to do is actually go through here and change things like how much data you train, or maybe swapping out what kind of algorithm you use. Now, let's go ahead and see a slightly more sophisticated way to analyze the results. There's a library called YellowBrick, which is a great visualization library, and it makes it really easy to do visualization around your classification model. And you can see the code is much smaller as well. So I just say digits load. I then do X and Y here. So here's the data, here's the target, Y is what we're going to predict. And then I use from scikit-learn, and actually a much simpler approach, which is you go here and you say import train test split, and this exactly figures out how to split your data for you. And I tell it I want to do 20%. So I want to take 20% of the data and hold it out so that I don't overfit against my model. I also have this random state set. And this is really important to know about. What this means is that every time you run, you'll get the same result. And this is really important. A lot of times when new people are using the scikit-learn library, they won't set this, and they'll get different training results, and they think that they're improving the model, but it's just randomness. So whenever you're doing something that involves randomness, it's important to set a random seed so that you can repeat your results and you know if you're getting better. So here we go. I make an instance of this model. Again, I use this confusion matrix report. I fit the model. I then score it, and then I use this YellowBrick's visualizer to actually go through and create a really fancy report. So you can see that this confusion matrix is much cleaner to look at, and you can see that this is the predicted class, this is the true class, and you can see how many accurate predictions that were made, and then in which case did something else get predicted, right? So it predicted this, but it should have been this, for example, right? So really a useful and very easy and intuitive way to understand is to use this YellowBrick visualizer. Also, YellowBrick has a ROCAUC visualizer as well. And if we go through and we run this, what it'll do is it'll actually show you for every one of the classes. Again, these are handwriting samples, 0, 1, 2, 3, 4, all the way down here, exactly the true positive rate and also the false positive rate, right? So you can go through here and you can see there's some classes that have more false positives, and there's some that are great at both true positive and also false positive. And really this is what that ROC curve does, is it shows you the trade-off when you're creating a model. How much do you want to tune things between a true positive rate and a false positive rate? So I would encourage you to play around with this data set. It's a well-known data set, and you can see the tools around it are really handy to use. Now let's talk about the second supervised machine learning problem that you're probably going to encounter with scikit-learn, and that would be a regression-based approach. So here's an example of some commonly known data set around MLB baseball players. So I'm going to import that into this data frame here. So you can see I say df.head, and these are some baseball players. It shows you the team, it shows you their position, their height, and also their weight and age. So a lot of times the first approach is to look at the shape of the data frame, and we can see that there's 1,034 rows and there's 6 features. And if I go through here, I then check to see if anything are null, and so I can see that there is in fact at least one null value, so an empty value. So what I'm going to do is I'm going to go ahead and drop that. So I say, oh, there we go, let's drop it. And now if you look at the shape, you see here there was one null value, and now I have 1,033 rows. So I dropped one of the values that had something missing. Now what I'm going to do is I'm going to go through here and clean it up a little bit. So a little confusing to me to have all those inches and pounds and weights. I'm just going to put it into a more easily consumable title. So height, weight, age here is now the new name. And now I'm going to do a little bit of exploratory data analysis. So I'm going to look at the statistics of this data frame. So if I go through here and I say df.describe, you can see here that the median for the height is 74 inches. The median weight of a baseball player is 200 pounds. So, you know, baseball players are definitely large people. And then the median age of a baseball player is 27. So now let's go ahead and take a look at the modeling aspect of things here and actually convert this into a regression-based model. So what I'm going to do is I'm going to say from sklearn import linear model. And again, this is a supervised machine learning model, and then I also am going to import train, test, and split. Now I'm going to go ahead and create a feature, and this is really where the NumPy expertise really comes into play here. So in order to create a feature that I'm going to predict, I want to predict the weight. And so if I go here and I look at that column weight, I then grab the values out of it, and now that becomes a NumPy array. And if we look at the shape here, you can see this is a one-dimensional array, right? We went over that earlier, how if it's two-dimensional, it'll actually show that two-dimension. Now, in order to do the target, right here, I create a y variable, I then reshape it, and then I also have the feature. So this is the height is going to predict the weight, and I make that an x feature. And in each case, I go ahead and I reshape it. And now if we go and we run y shape, you can see that now it actually has 1,033 rows, and it's actually in the shape that I need so that I can do the machine learning training. Next, what I'm going to do is I'm going to again use that built-in scikit-learn train, test, split module, and I go through and I divide the data up so that here's my training data, so this is 80%, and then my test data is 20%. So this is actually going to be kept and held out, and we're going to test what I predict against this 20%. So next, let's go to fitting the model, and we go through here and we create just a traditional linear regression model, really simple, and that's something that's available from scikit-learn. I then put in that again the training data, so we want to predict X, we want it to come from Y, right? So we're going to predict the weight, and it's going to come from the height. And then I actually take those predictions and I put them into the prediction variable. There we go. And if you want to look at more things about what's around that model, if we do this, you can go through and you can see, you know, all the different things that you can do with that predict function. So if I go through here and I again look at the predictions, it returns back a NumPy array. And now that we've done the training, we can go through and we can plot our predictions. So I use just regular matplotlib here, and I actually have the predicted weight right here, and then I have the actual weight. So really it's going to be in between here. If we did a regression line, you would see that, you know, it's an okay prediction, but you can see there's a lot of variance between what was predicted and what's actual. So in some cases, I don't know, they predicted, you know, 230, and maybe it should have been, you know, maybe more like 210. Now, we also can print out exactly what the prediction accuracy is, the model score here. So we can see the score is 0.19. And also, I can do a cross-validation step to improve it. So if I go through here and I import scikit-learn, they have a couple different libraries here. They have cross-validation score and also cross-validation predict. And so what this does typically is just clean up your model a little bit to make it less likely to overfit. And if I go ahead and I plot this, you can see it actually does improve it a little bit. You can see things are a little bit tighter in a more visual way. And you can see that the R-squared score, so R-squared is what is explained by the variance between this prediction. And you can see that 28% of the relationship is explained. So it's an okay model. But in general, this is something where you could go in if you wanted to and actually change things around, maybe try to predict things by position, or add some new data to actually make a better prediction. But it shows you the pathway where you would use in order to create a machine learning prediction. So here's some takeaway steps here. Cross-validation, improved accuracy. Adding more data can improve it. Major League Baseball, though, might be a strange set to predict data unless you were trying to predict only for Major League Baseball. It probably doesn't fit with regular people. And then also you could look at like a larger data set. So let's go ahead and look at the final aspect of machine learning with sklearn, which is unsupervised machine learning. So let's talk a little bit about what is unsupervised machine learning. Unsupervised machine learning is really you don't know what the correct answer is. So in the supervised examples we showed above, we knew what the correct answer was, and we trained something to predict based on that correct answer. In the case of unsupervised machine learning, we have no idea what the correct answer is. We're going to tell these clustering algorithms to tell us some patterns, and then those patterns will then reveal additional information. So that's what unsupervised machine learning is. It's a way to discover new information or to discover new labels. Here's a food data set here that has fat, carbohydrates, sugars, proteins, salt, energy, and also the product. And I import that from Pandas, and then I go through and I clean things up a little bit here. And then if I go next here, I can see what the columns are. So this is what I typically do when I import something from into Pandas. Next, what I do is, in order to do feature engineering, I'm going to drop all non-numerical fields. So you can see here that this is numerical, this is numerical, this is numerical, but the product itself is a text-based field. So I'm going to go ahead and drop that from the data frame. Next, with clustering, it's really important to scale the data so that it doesn't have one column that is kind of skewing the results. So you want everything at in some kind of a range. So what I do here is I scale all of the columns so that the values are between 0 and 1. There we go. I do that and I do the scaling. And now what I'm going to do is I'm going to do a k-means cluster algorithm, and I'm going to pick 3 clusters, and then I'm going to fit those clusters to the data, and then I'm going to add that label that was created. So it's either 0, 1, 2, and I'm going to add that back to the data frame, right? Because I want this product information, but first I have to do a numerical clustering algorithm, and then I take that data and put it back. Here we go. Now I can see here that I've got cluster assignments, and really that's the final step to doing unsupervised machine learning. And what we'll do in some lessons in the future is we'll go through and show how you can visualize that data and get even more information. Let's talk about Pandas. Pandas is also a huge aspect to most data science professionals' workflow. And there's a couple different types of Pandas operations that I commonly find myself engaged in, and I'm going to walk through both of them. So first, let's talk about a time series workflow. So I'm going to go through and I'm going to grab some Zillow data, some really recent Zillow data, and I'm going to import this into a Pandas data frame. So I've checked this into my GitHub repo, and I'm going to go ahead and show it here. So you can see it's very recent from 2018, but this is every housing price in the last 30 years. And now I'm going to do a little bit of exploratory data analysis. So if I do a describe here, I can see that the median housing price, for example, back in 1996 was $96,000. That's not the case today. Now I'm going to also clean up the data frame a little bit. So I'm going to take the region name and I'm going to change it to zip code, and then I'm going to not follow my own advice here and actually do use a lambda, although I could have used a function, and do some formatting so that they're formatted as floats. And then next here, I'm going to go ahead and look at what the median price is and grab that. So those are kind of common things that I typically do. And if I look at the median price for the last several months here, you can see that the median home price in the United States right now, as of December 2018, is $200,000. So very different than 30 years ago. Now, if I go ahead and I look at the city of San Francisco, which is a pretty wealthy city, you can see that the median home price is actually, let's see here, this is 1.8 million. So a little bit different than the median home price in the United States. How about 10 times different? So that definitely shows me some interesting information. Now, next, what I'm going to do is I'm going to go through here and I'm going to transpose this data frame. So what transposing does, and it's a really interesting feature, is it actually flips the shape. So you can see that these are actually rows. Well, it's going to flip the rows into columns. So let's go ahead and take a look at how that works. So these, again, used to be columns, and now they're rows. And now what I'm going to do is I'm going to make a city's data frame. So I'm going to take the city's values, which are right here, right? So this is 0, 1, 2. This is the second row down. And I'm going to use something called iloc. And this allows me to grab the entire row and put it into a variable. Next, what I'm going to do is I'm going to drop certain parts of the data frame that I don't want anymore. So you can see I do that by doing taking this transposed data frame and dropping a whole bunch of these rows here. Like basically all this stuff I don't want anymore now that I've actually grabbed the cities out. And then what I do is I add the cities back in again as a column. So this is a fairly sophisticated way to manipulate a data frame, and really common if you're dealing with something that's in the wrong shape. Now I've actually got the data exactly in the correct shape that I want, and I can actually think about converting it into a time series format. So in order to do that, what I'm going to do is I'm going to import the autocorrelation plotting from Pandas, and then I'm going to again use this iloc. So I'm going to go ahead and grab some values out of this data frame, and I'm going to then use the Pandas data frame index, which is how you create an index in Pandas data frame, and then I'm going to actually assign that to a series. Now that I've actually made this time series formatted type, I can actually go through here and I can do an autocorrelation plot. So this is just a diagnostic plot that shows me, what's happening with time series data. I also can go through here and do tail plot, which shows me the last parts of this data frame for San Francisco in particular. And then finally, at least in this particular zip code, you can see that the housing prices were 4 million. So this is a very expensive part of San Francisco. And in this case, I also can go through and just use a regular plot as well. And so this is the last 30 years for this zip code in San Francisco. Because I've created a time series format, and I've told the data frame that it's a time series data frame now, you can see if I just call plot, it'll exactly do the right thing. You can see back in the 90s, this real estate was under $1 million, and now in the last 30 years, it's gone up to about $4 million. So you can see a pretty incredible shift in real estate values in the last 30 years in San Francisco. So that's really time series in a nutshell. And if you want to play around with this yourself, this is a great data set to actually manipulate a little bit more on your own. So now let's talk about a second type of Pandas workflow that I use quite a bit. And this is more of a specifically like traditional data frame oriented workflow. So I'm going to grab a different data set here. So I'm going to import Pandas. I'm going to go back to this nutrition data set, and I'm going to do the same thing I did before, clean it up a little bit. And then I'm going to do some exploratory data analysis on it. So again, first thing I typically do is I look at the columns. We can see what the columns are. And then a lot of times what I'll do as well is I'll look at the shape. So we'll see here 45,000 rows. So this is a really big data set with 7 potential features. And if I want to look at the first 5 columns, I would do df.head. You could actually put in another number like 3 if you want to only look at, let's say the first 3 rows. But I typically just 5 is often good enough, so I leave it at the defaults. And if I want to do descriptive statistics, I can go through here and I can see that, for example, proteins of all 45,000 values, the median value for protein is actually 4 grams, right? So four of 100 grams total would be of protein, right? So these are maybe lower protein foods. In terms of carbohydrates, a lot of the foods here have 22 grams as the median. Now, if I want to go through and start to get into some maybe prediction, a lot of times the first step is to look at the correlation. So, what is correlated to what? If I do df.core, that actually shows me how every different column is correlated with how every other column is. Now, if we look here, we can see that carbohydrates are negatively correlated with fat, which is kind of interesting. I mean, slight negative correlation. We also see that carbohydrates are very strongly correlated with sugar, right? So that makes a lot of sense. Things that have carbohydrates are typically have sugar in them. So there's some interesting learnings just from that. Another really powerful thing that I do a lot in Pandas is I look at quantiles. So if we wanted to look at, for example, really fatty food in this data frame, what I could do is I could go through here and I could take that data frame and I could say if any value is in the 98th percentile, so I take the column right here and I say dot quantile, which is a method that's available on the column, show me all of the values that are over the 98th quantile, so 98th percentile. And we go here and I actually grab that into this column here, and then I look at the text. And so now I actually can, if I wanted to, I could even go a little bit further and I could look at, let's say, high fat text here, and I could actually maybe grab like one value out and just see what one of those would be. There we go, organic salted nut mix. Yeah, that seems like a high fat food to me. I also could go through here and do the same thing for some other type of food. So I'm going to look at the high protein food in the 98th percentile. Again, I just take that protein column and I say anytime you find something that's in the 98th percentile, go through here and give me it. There's 896 results, again, out of 45,000 foods. And then if I want to go through and I want to, again, look at the first thing in here, we can go through and grab high protein text and look at that, and we can see that organic yellow split peas. So split peas, so beans do have quite a bit of protein. So we can see that that's actually a great high protein data source. Let's talk a little bit about TensorFlow. TensorFlow is a deep learning framework that is created by Google, and it actually runs really well inside of this Colab environment. It's almost impossible if you're doing data science that you haven't heard of TensorFlow, but one of the maybe drawbacks of it is a little bit complex. So what I'm going to do is I'm just going to show you a really simple TensorFlow based workflow here. And this is based on some Hello World examples from Google. So the first thing you're going to do when you use TensorFlow is you say import TensorFlow as TF. And a little bit like the NumPy workflow here, you can see that you go ahead and you create an array, right? So this is a 2x3 array. And again, just like NumPy, they also have this range functionality. So I can say, create something from 1 to 7, again with a 2x3 array. And now if I print both of those out, I can say to TensorFlow matrix with the shape, and I can actually print both of these out here. You can see that these are two 2x3 arrays. Now what I'm going to do is I'm going to take those two 2x3 arrays and I'm going to do matrix addition. So next what I do is I take this output variable and I assign it to the first array I created and the second array I created. And the way to do that is I use a TensorFlow session. So this is something that uses the with context, and this with context, all I have to do is say tf.session and do eval. And what this will do is it'll actually then do that calculation for me. So let's go ahead and run that. And now you can see that it says the result of addition of two matrix are this array. And so it's 2, 3, 4, 5, 6, 7, and it also tells you the type. So this actually is a really good basic overview of what TensorFlow does underneath the hood and how actually deep learning works in general. It's really deep learning is, if it's at its lowest level, is there's a bunch of very small functions that do some operation, and then that data is actually translated from one layer to another layer. And so it's really a series of many different, very small computations. And you can see here, this is a very small computation, right? It's 2 arrays, they're added together, and then they're evaluated with TensorFlow. One final thing I want to show you with the TensorFlow ecosystem is there's something called Seed Bank. So Seed Bank is made by Google as well, so it's almost a companion to Colab Notebook. It has a bunch of recipes available that show you things in the TensorFlow framework. So I figured a great way to show you TensorFlow would be to take you to what the experts have set up. And we see that there's a Keras-based example here. And I can look through here and see this is made by the TensorFlow authors. And what it does is it takes the MNIST fashion dataset, which is a bunch of fashion pictures, and it uses Keras and TPUs. One thing to point out here is that Keras is actually built on top of TensorFlow, so it's like an easier way to do TensorFlow. So I'm going to go ahead and click on Run Seed in Colab, and it's going to go through and it's going to open up this tutorial. We can see here that what it does is it actually trains a model using the Keras and TensorFlow framework and also TPUs. Again, these are these TensorFlow processing units that are available as a runtime type. So if I go here and I say change, we can see Python 2 TPU, right? And so if I want to go through here and first download this data set, let's go ahead and do that. All right, so what this does is it goes through and it grabs this fashion data set and actually puts it into both training and testing. Now what I do next here is I actually define this model using Keras. And so what we do is we create a sequential model with Keras, and then these are a bunch of layers here. So these are all different layers that will again transform our model so that we can actually do some training on it. There we go. So that's all done. You can see this goes through here. And now let's actually train this model using, again, this ASIC, or accelerated integrated circuit called a TPU. And we import the OS, and then we go through here and use that Keras to TPU model. And then this goes through and it actually does a very similar thing that scikit-learn thing does, is it goes through and it trains and it learns, and it gives us back a trained model. Let's go through and let this happen. There we go. You can see it's going and it's grabbing one TPU worker, and it's using 8 TPU cores. And again, this is freely available inside of Colab Notebook. Let's let that run for a second. All right, now we've gone through and had TensorFlow do its hardware accelerated AI training, and now we've got a trained model that was trained using deep learning. Next, what we can do here is we can actually go through and have some label names here. So t-shirts, trousers, pullovers, import matplotlib, and then what we're going to do is we're going to plot these predictions based on the model that we just trained. So if I go through here and I do this, you can see it's copying the weights to the CPU. So again, this model has actually been done on one hardware chip, and it takes that data and then transfers it over to a CPU. And now you can see here that these are all of the predictions, and it was able to do inference in about 2 seconds. And these are all the different predictions. So you can see that it was able to get a really high accuracy with all these other 1 values, and maybe a coat was slightly less accurate with 0.996 accuracy, and a sandal was a little bit harder for it. So in a nutshell, this Keras fashion MNIST example is a really great example to go further with your trainings in TensorFlow, and I definitely recommend you take a look at Seed Bank and try it out for yourself. Let's talk about Seaborn to do 2D plots. Seaborn is a really commonly used plotting library in Python, and I'm going to talk about some of the really common plotting types of operations that I typically do. One of the ones that is pretty interesting is this faceted distribution plot. So if we go and we look again at Seaborn here, and I import it as Seaborn as SNS, and then I also have to import matplot with it. You can see how I do that. And here's the part that's a little bit tricky, is I go through here and I create these subplots. And so I've got a 2x2 subplot. So again, we have to think about matrix type operations all the time when we're dealing with data science in Python. And I'm going to actually have 2 rows and actually 2 items, right? So it's a 2x2, and you can see the figure size is what I've set here. And then what I do is for each one of the parts of the grid, I actually put a different column. So I say I want to look at the proteins here, I want to look at the sugars here, I want to look at the fat here, I want to look at the carbohydrates there. And when I plot that out, you can see here at the very first part of this grid, I have the distribution of proteins, right? So we can see how it skews to the left. We also can look at how sugars also skews to the left. And then if we look at the last two, carbohydrates and fat, you can see that carbohydrates is actually a bimodal distribution, right? And we can see fat also skews to the left. So a great way to really look at maybe the core features of your data set is to use this faceted distribution plot. So you take maybe the 4 features that you think you're going to use, and then you just plot them out. And you could obviously put even more. You don't have to do 2x2, you could do 3x3, or however many different things you'd like to plot at the same time. Let's also talk about a really common approach as well, which is a pair plot. So if you import Seaborn as SNS and just literally put your entire data frame inside of this pair plot, it essentially just does the right thing. And what this does is it actually, you can see here, here's fat, here's carbohydrate, it goes through here and it sugars, it plots everything against everything else. And what this does is it allows you to look at patterns and find patterns. So, for example, there's something going on here, there's something going on here. Like these are, you can see that there's these relationships that are actually forming between these different rows. So, carbohydrates, this is one row. You could say, well, what's down here? What is that? That's sugars, right? And so we know, because we looked at this earlier, that sugar and carbohydrate have some kind of correlated relationship, right? So we can see here that this is sugar and carbohydrate. There's definitely a very, very strong relationship. It's almost exactly a linear relationship between those two things. Let's also look at LM-plot. So LM-plot is a really simple plot that might be a good way to just kind of get it started and just look at 2 different things that you think there may be a relationship with. So here I take fat and I take protein, and I do a little trick here where I actually sample the data. So we know that there's 45,000 rows, so there's a lot of rows inside of this this data set here. And so what I do is I actually just grab a little bit, so it'll just do a real quick plot. I just sample, I say, just give me 1,000. I sample it, give me 1,000, and I can see there's a linear relationship here between these, and you can see here's where the protein and the fat. So there's definitely some kind of relationship. It's not very strong, but there's something going on. Now I also do something kind of cool here. So if I change this to a smaller sample, 100, right, that might be another way to get a little bit more information. And I even could do this. I could say hue, and I could look at the total calories, so like the energy that's available. And let's just say I say energy 100. And if we do that, so another thing we can do is we can actually go through here and look at the energy, which is basically the total calories, and color the relationship by that. So if I go through and I plot this, we can actually see the relationship between X and the relationship between Y, and also the coloring that shows for each one of those dots how much energy is actually associated with it. So you can see here that it kind of shows up a weird plot here, but an interesting thing to play around with a little bit. Now I'll go through and get rid of this, and we'll go back to our regular plot. Now a final thing that I want to point out is a heat map. So one of the things that you can do with a heat map is you can take that correlation that we've talked about previously, or even the pair plot, and you can actually see in a very concise and dense way exactly what's correlated with what. So we know that carbohydrates and sugars are really related. So let's look at carbohydrates and let's go find sugars here. Here's sugar. And you can see for sure that, look at this, it's very, very like cherry red here, that there's something going on here. Now, in the case of carbohydrates and carbohydrates, well, of course, that's going to be, dark red because it's the same thing. It's exactly correlated because it's the same thing compared against itself. But in the case of carbohydrate and sugar, you can see it's just a very, very strong correlation. So, if we wanted to do some kind of prediction where we predicted, carbohydrates by how much sugar appear in a food, this could be a great feature to add. And really, that's it. Those are some of the main ways that I use Seaborn, and I think a great way to play around with it is to take this data frame and actually tweak it a little bit and explore for yourself. Let's talk a little bit about how to use Plotly for interactive plots. So let's start out with a 2D plot. Plotly is a great library for doing interactive data visualizations. And with Python inside of Colab Notebook, one of the things you'll have to do is do this. So enable Plotly in Cell. And you can see I import Python, I do Plotly offline, import notebook mode, and all this little snippet does, and you can find it right inside of examples for Colab, is it just initializes each cell so that it can run this Plotly graph. So I'm going to go ahead and do that. And then next, what I'm going to do is I'm going to tell Plotly to go offline. So this will actually not talk to their paid service. And then I enable Plotly in Cell, right? So that's that code above. And then I say connected mode false. And then from here, what I do is I use something called cufflinks. And cufflinks is just a way to make it easier to plot directly from a data frame in Python. So here we go. I say I want to sample just 1,000 items, again, because this is a pretty big data frame. And I want to create a bubble plot. And then I want to actually have the size of the bubbles be essentially how many calories are in the food item. And then I want there to be an X, and that's the fat, and the Y is going to be the protein. And then the text that I hover over will be the name of the actual food product. So if we look down here, you can see that there's a bubble plot where, again, the X is the how much fat is in the product, and the Y here is how much protein, and the bubble size is like, the bigger it is, the more calories it is. So we know that fat is over double the amount of calories per gram as protein. So you can see there's already some really interesting relationships here where you can see like butter, right? So butter has a lot of calories. So the circle is very, very big. But if we go through something like this, lemongrass paste or chicken fajitas, like these are much less fat and much less total calories in the bubble, smaller. But you can see it really gives you a really incredible way to kind of explore a data set, because you've got one dimension protein, another dimension fat, you've got another dimension which is the actual name of the product, that third dimension, and you've got a fourth dimension which is the size. So really a powerful way to explore data sets is to use this this interactive data visualization from Plotly. Now let's look at a three-dimensional version, which gives you even more power. So in this example, what I do is I look at the protein, fat, and carbohydrates, and I take a k-means clustered model that we actually created earlier, and I'm going to go ahead and throw this into a three-dimensional plot. So really, this is mostly boilerplate code here. So we already talked about that, but I'm going to go into this part that makes it three-dimensional. So what I do is I define an X, I define a Y, I define a Z. So there's, again, with a 3D plot, there's three different dimensions. So fat, carbohydrate, and protein. And then the hover text, I make the product. And then the color I also add is the cluster, right? So because we did some clustering earlier, I can go through and actually add that cluster. And then this is just the title, essentially. So this is really boilerplate that you can just cut and paste and put your own code into. And now if we look at this, this is the food energy types against all three dimensions. So we have carbohydrates at the y-axis, the z-axis is protein, and this x-axis is the fat content. So really fascinating way to look at a data set, and especially these clusters here are kind of interesting. So you could think about, what is this cluster really showing me? What does this mean? Like chocolate scone, caramel popcorn, butter toasted pecan. I mean, my gut hunch here would be that this cluster, you could call it junk food, right? This is all stuff you really don't want to have a lot of if you're into health. Fruit Loops, right? This is maybe the canonical junk food that exists. Now, if you look at this other color here, this is more, I don't know, these are potato toppings, nutrition bar. Maybe these are like, general purpose, nutrition foods, like they're more medium nutrition foods, or you could even call them healthy foods, right? They're right in the middle. And then we have this third green cluster. We've got salami crisps, cheese, seeds. So maybe you could call this like high protein, high fat foods, could be an example, right? So very interesting. This shows how by doing clustering and also plotting the clustering on a three-dimensional plot, it allows the data scientists to come up with these labels that are really based on their own domain expertise. So I do actually have a bachelor's degree in nutritional science, so I have some domain expertise here, and I'm able to then go and look at this cluster and say, that's actually junk food. And now we're going to call this a junk food label. And what's really powerful about it is that label was created by using machine learning. Now let's look at one more chart here, which is a sugar, salt, and carbohydrate 3D plot. And so if I go and I look at that, we can see here that now I'm actually doing a three-dimensional plot, again with the same clusters, but they're just visualized in a slightly different way. So we can see that the higher up here we go, the higher salt it is, and the higher here we go, the more sugar it is. So if it's sugary and salty, maybe not a very healthy food, and also high carbohydrates. So like, what is this thing? Organic Santa Maria grill cooking seasoning. So what's a little bit surprising about this is that this sounds like this is some kind of seasoning you'd put on your food, but it's very sugary, salty, and high carbohydrates. So maybe not a very healthy type of thing to be putting on your food. We look at some other ones here, like deluxe ice cream, Rocky Road. Like these are all not great food items here, but it gives you a different visualization approach, even though it's the same data that we had before. Or here we go, Maya coffee rubs. Really in this example, maybe this really shows us more of like a different way of visualizing the same data, but we could call these labels something slightly different when they're actually visualized this way. So this could be seasoning based ingredients. And really this is it from the 3D visualization. And I think the takeaway here is that you can see the power of interactive data visualization, both 2D and 3D, really exposes new information and allows a data scientist to take that information and communicate it back to the stakeholders in their company. Let's talk a little bit about some specialized visualization libraries that will crop up quite a bit. And in particular, Yellowbrick is an emerging one that's pretty impressive. Here's an example of Yellowbrick in action here. And what this does here is it actually goes through and it does a prediction using lasso regression, and actually shows the R-squared, and it shows the best fit and also the identity, all plotted on this same plot here. And you can see really a very small amount of code. As long as you have an X train, a Y train, it'll then go through and it'll both fit it, score it, and then do a visualization. So if you are doing regression-based models, Yellowbrick is a great way to actually visualize that data. Another thing that Yellowbrick does is it also can go through and show you, in case of a cross-validation, all the cross-validated folds, what's actually happening. So one of the things that cross-validation does is it allows you to actually take many different samples and train against many different samples at the same time, and then average out the score so that one sample isn't overwhelming your data set, so you don't get, again, like overfitting. And so you can see here that there's 12 different folds, and you can see all the different scores that were done, and it's just a great way to really get more information about your training and actually go through and maybe tune things based on the results of these visualizations. So not only do you get great information about your data sets by doing visualizations when you're doing exploratory data analysis and clustering, but also when you're doing the model training as well. So let's go ahead and look at a final part of this lesson here. Let's go ahead and look at word clouds. So word clouds are on one hand, they are a little bit hokey, and it's easy to make fun of word clouds, but there are some things that word clouds can do that are pretty powerful. So I'm going to go ahead and look at a previous example with food data. And from a previous lesson, we were talking about how you could go through and look at quantiles of food, right? So these are some high protein foods that I'm sorting on. So I have a whole bunch of high protein food. Now let's go ahead and take a look and visualize what all that high protein food looks like by looking at the product labels. So I go through here and I use that word cloud library, and I create a 3000 by 2000 grid, and then I actually take some stop words here, and then I go through and I do a plot. So you can see that these are all high protein foods that were found. So beef jerky, pumpkin seeds, Swiss cheese. So for a data scientist, again, this is a great way to actually really kind of confirm maybe a suspicion, or maybe show the results to a management team. It's basically showing us that, yes, this is actually what I was looking for. Here's another example we can look at. Same thing. I look at high-fat foods, and I get 878 high-fat foods, and I do a visualization. And from this data set, we can see things like chocolate truffles, almonds, roasted salted, all these really interesting data labels that, again, show us some additional context about our data set. Now here's a final one here, high sugar foods. So again, out of that 45,000 rows of data, we can see that when I look at just one specific version of it, something highlights itself, and we can see that iced tea in particular seems to be a very sugary section of the data set. And so we look here too, there's a total of 900 different products that are actually visualized here, and of those 900 products, iced tea is actually, most people wouldn't think of it as a candy, but it's actually basically in the same quantity as candy. So maybe just as a takeaway, for teachers or school programs that maybe they're banning candy because of the ill effects, but they need to also maybe think about iced tea and how iced tea could really be harmful to many kids. Let's talk about some common natural language processing libraries that you'll experience when you're using Python. Really, the two top libraries are the NLTK library, which is one of the oldest ones, and 𝑔ensum. So let's first look at NLTK and one of the things that you do with it. One of the things that you use the NLTK library for is to actually find stop words. And I've mentioned stop words in some other lessons. Let me just define it real quick. A stop word is something like a, the, a word that basically you can throw away. It doesn't add any predictive value when you're doing natural language processing. So you can download a bunch of these, and then if I take an existing data set, so if you remember, this is the data set that actually had the food products in it, I can go through and say, every time I find an empty value here, go ahead, and if I find a null value, just make it an empty string, and then take those stop words and actually, as long as the stop word doesn't appear, then give me back the result. So basically clean the data and remove all of the stop words from it. So this is a really common thing to do as a pre-processing step whenever you're doing natural language processing, and NLTK has a lot of other things as well. So it can do things like entity analysis, and it can find the which ones are the nouns and which ones are the verb, parts of speech. But in general, this is a typical pre-processing step. Next, let's also look at 𝑔ensum here. And so 𝑔ensum will, in this example, will actually assume that I've gone through and I've cleaned out the stop words from it. So I import 𝑔ensum, and what I do is actually take that clean data and I turn it into a corpus. And what that does is it allows me to do more complex data modeling aspects on the data. And in this case, I import 𝑔𝒉. I say I want to do something called topic modeling. And what I do is I take all those food products, again, the food products that are cleaned, and I actually tell it, I want you to convert all those things into a total of at max 5 items. So what it's doing right now is it's crunching through. It's going to actually try to find every one of those food products and come up with, essentially what are 5 topics that it can actually, describe about all those 45,000 food items. And then in this section here, we can see that it actually goes through and it's going to generate 4 words that describe that topic. So again, there'll be 5 topics total from those 45,000 food products. And then of those 5 topics, there'll be 4 words that describe those 5 topics. All right, we can see that it's actually done the work for us of identifying these 5 topics, right? So it starts with 0, 1, 2, 3, 4. So of 45,000 food items, this is one of the topics that it came up with. And what it does is it describes this topic in 4 words. So chocolate, cream, milk, and juice, right? So it's kind of interesting. Like maybe you could think of this as maybe like a liquid topic of some kind of like a dessert type liquid. The next topic is fruit, light, and premium are all words, and right? So are all things that come up. Next one, cheese, candy, cheddar, in, sauce, sweet. So we can see from here that there's like, cheese, candy, cheddar, in, sauce, sweet. So you can see that there's really some interesting things that are learned from this data. And, for example, this last one, beans, mix, green, maybe you just call this topic, these are health foods, right? So anything that could be classified in this category here could actually give us some additional predictive power. And so we've done a couple really interesting things now with this data set. One, we've done clustering, right? And we've been able to get those 3 clusters. Now we've done topic modeling, and we could add that topic modeling as a feature. So really we're learning all these really powerful things by using these algorithms that discover data and then create new labels for us.
In this lesson, we'll learn about functional programming. You'll learn how to think in terms of functional programming. And the lessons will include how to understand functional programming. You create functions and apply them to data science problems. You use map, reduce, and filter built-in functions. You create list comprehensions. And finally, you will learn how to create dict comprehensions. Let's get started. Now let's understand some things about functional programming. First, let's talk about the idea of state and side effects. State is the current valuables for variables in data in which your program is running. And side effects are the act of modifying the state outside of the current scope. So if you have a function, you may have a scope inside the function, but if you're modifying data that exists outside of the function, that's called a side effect. Some aspects of functional programming that are important to understand is that a functional program does not depend on the state and does not change the state. It tries to limit side effects. A function called with the same inputs should always produce the same outputs in functional programming. So let's look at some examples of using state. Here we have a very simple state. It's just this shared variable, the shared variable that is in the outer scope. The local state of this function is literally what's happening inside of the function itself. And you can see this function uses this variable, which is defined in the outer state, internally to produce its output. So let's just run it once. And we can see if we change that outer state, the output of the function changes. So this is not how you'd expect to do it in functional programming. Here's a more functional approach. So in this case, the function itself takes this wind variable as an argument instead of relying on it existing in the state. And so when we call the function itself doesn't know what the outer state is. It only knows what arguments we've passed to the function. So if we pass the same argument again, the function has the same output again. Now let's talk about changing state or side effects. So here we have a state, we have a global array with a list of wind directions, and then we also have a wind which is defined and initialized to the first value in that array. And we have a function which grabs this global wind variable from the global state and sets it to a new value. So we can look and see that wind starts out as northeast, which is the first entry in this winds array as it was initialized. But now if we call this function and then call the global variable wind, we see that it starts at northwest rather, so it's changing through the different states. What that means is it's actually changing the outer state outside of its local scope. This is called a side effect, and this is not something we do in general in functional programming, though there are some small exceptions. So a more functional approach would be to pass in an index to this array, so there's no global array anymore. We pass in an index specifying exactly which entry in the array we want, and then print that entry in the function. So you can see here, if the function's called with the same index, it's always going to return the same result, which is what we want in a functional program. Another form of changing state is changing mutable data. So if we pass in a mutable data type, such as a list or a dictionary, and then change it within our function, then we have caused a side effect, which is a change in the data. And this is something that can introduce a lot of bugs and make it hard to track things down because the state is changing and you can't trace it exactly through the functions. But let's take a look at this. Here we have a function, we pass in something called data. And the function takes that data and changes the owner entry in that data. So our data here, you can see we've got a vehicle, which is a ship, and an owner, which is Joseph Bruce Ismay. And if we call our function on that data and then print the data out, the owner has been changed to white star line. So that's a side effect, and it's something that we do try to avoid in functional programming. So a more functional approach is this. So we create our dictionary the same way we did before. We have a function that changes owner, but instead of changing owner on the original data structure, we make a copy of that data structure and return it. Now, we may take that data structure and assign it to the same variable we began with if we want, but the function itself is not changing the outer scope. And we can see how that worked. Let's talk a little about strict versus non-strict functional programming. In strict functional programming, there are no variable assignments and no side effects. This is something you'll see in languages such as Erlang and Haskell. In using Python for data science, we use a less strict version or a non-strict version. In this, we do use variable assignments in local scopes, and we do allow for limited side effects. The side effects in particular that we allow for are printing and logging. Logging especially is very important in any production code, but is technically a side effect, and in a strict functional sense, you wouldn't do it within a method. So some common alternatives to functional programming are procedural programming, which is a series of statements and functions whose behavior depends on the current state. And this is the style of program we talked on earlier in this series. And another is object-oriented programming. We've touched a bit on objects, but a short definition is to say that in an object-oriented programming, the state and the functions are bundled together into a single unit and can be passed around together throughout your program. So this is the basics of functional programming, and I hope it's enough to give you a general understanding of the direction you go to write better functional code. Let's quickly talk about applying functions in a data science workflow. This apply functionality is something that we've touched on before and we'll touch on again in this series because it's such a basic part of what you're going to do with Pandas data frames. So here you see we have an array of quotes, all very important. We've got a Pandas data frame based on those quotes, and we've named the column quotes. So let's take a quick look at that. You can see the quotes, each row has its own quote, and the column's header is quotes. Now, if we define a function that we want to apply to this whole data frame, let's say we want to take the quotes on each level and make some characteristic decision about them. In this case, we're going to decide if that line is a religious or secular line, and we're going to do it with the very simple mechanism of looking for the word God in that line. So this is our method. Now, if we use the apply on the data frame to take our function and pass it in as a functional object to the data frame, it will apply it across the data frame, and we'll see it will create a new column here named quote types, which will have done our analysis. So here's our new column, and you can see it decides whether they're secular or religious based on the existence of the word God. So that's a simple example of using functions in a data science pipeline in a functional manner. Now let's talk about some functions that are provided as part of Python that are very functional in nature. That is map, reduce, and filter. First, we'll talk about mapping. Basically, with mapping, we can take a function and apply it to a sequence or iterable. So here we've got a function called count flower petals, and it takes an argument d and returns a string using that argument to create a longer string. Now, we could loop through this in a for loop or a while loop, I suppose. But with map, it's a much cleaner and more direct and functional way to do it. So you can see here we take a function as the first argument to map, and then the iterable as the second argument. And when we call it, and here we see the result, which is a list of strings, each string with the items in the iterable in order. Now with mapping, we can use multiple inputs. So here we have two lists of numbers, and we've defined a function that takes two arguments. So when we pass to our map function, the function and then the two lists, it will use the items from those two lists as the arguments into that function and use them to create the results. So we see here the results are the result of multiplying the first item in this list with the first item in this list, and so forth all through. You can do this with more than two iterables as well. It can be as many as you like for your function. Another built-in Python function is reduce, and with this we can take some type of sequence or iterable and turn it into a single number. So here we see a for loop where we're going through the debits in this list, and we're subtracting them from the initial balance. This minus equal means that the initial balance is set to the value of itself minus the debit. So at the end of running through this, we get this number. Now, this is fine. We can do this in a for loop, but with the reduce function, which exists in the functools module, we can do this in a shorter function. So here we define our function as minus, a minus b, and we call reduce on minus with the two lists. And you see we get the same result as if we had gone through a for loop to do it. In this case, the for loop is very small. It doesn't seem like a big deal of code, but there are times where it's useful to pass around a function and be able to call this in one line in order to make your code much more readable. So here's another reduce example. In this case, instead of having to define the function subtraction, there's a predefined operator module which has a sub on it so that you can just pass that into reduce on its own. That way you don't even have to define that function, and it becomes much simpler to write a one-line reduction of whatever iterable you need to reduce. And lastly, let's talk about the filter function. With filter, we can go through an iterable and only return the items in that iterable that fit some condition. So in this case, we've created a condition that says, is the item passed in, is it uppercase? So that's a simple little test there. With filter, we pass that function, cap in, and then we pass our iterable, and the result is only the items in that iterable that fit the test is upper. Okay, that's the end of our introduction to filters, reduce, and map. Now let's talk about one of the most idiomatic pieces of Python functionality, the list comprehension. So here's an example with a for loop. We have a list of names which are all in lowercase. We want to get a list of the same names but with the first letters capitalized. So this is the title function we saw earlier when we talked about strings. Now we can go through them in a for loop, and we can call title on each one and append it to the list, and that will work. And we can see the output is what we expect. But we can do the same thing with what's called a list comprehension. A list comprehension is effectively a way of doing a for loop in one line. It's optimized at the code level, so they tend to be more efficient than a normal for loop. And they can be used for a lot of things in Python. So here's an example of doing the same thing we did above, but with a list comprehension. So the syntax for the list comprehension is the return value comes first, and then you have the for, and then you set a variable for what you're iterating in. So where we had name up here, name in names, here we have x in names. And where we had name title, we now have x title. And we see we get the same result. So this is something that you'll see all over the place in Python and that you'll want to use for a lot of the work you do. Now, we already looked at the map function, and here's the example we had before, where we map the contents of this list into a series of strings based on that list. Now, with a list comprehension, we can do the same thing in one line. So here, we have our output, which is the string, which we saw appear as a return value. And then this is our iteration through the list. And that's all we need to do the same thing we did above in 4 lines. So you can see that the list comprehension can be used anywhere a map function is used, and often is easier to read. Now, here's our example from the filter function again. And we can see that in this one we return only the capital letters in a list of characters. This we can also do with a list comprehension. Here we see that we can do the same thing with a list comprehension. And the trick is that we add a conditional to the list comprehension. So once again, we have our return value first, our iteration through the iterable, the for x in characters, and then we add a conditional at the end. If that conditional returns true, then that item will be returned as part of the list. So we can see that it has the same output as our filter above, but we do it all in one line. And it's very readable and very idiomatic to what you'll see in Python. Now, list comprehensions can work with multiple variables as well. So here we have 2 arrays, and we want to print out the 2 arrays as points, of xy points. So it begins the same way. We return value first, and then we have our iteration through those 2 lists. Now you see we've zipped these lists together. We've seen zip before, and it creates a list where a sub-lists are tuples of the contents of the other 2 lists. And you can see we unpack those into x and y variables here in the iteration part, and then we can use those x and y variables there. So you can see this prints out a list, and we have the items from each of the other lists used together as pairs in the output. And just as an example, we talked about the zip function. Here's what it looks like if you just call zip. So it pairs them as a list of tuples paired together. So what if you're given a list of lists and you want to turn it into one flat list? This is something that you can do with a list comprehension rather easily. So let's look at that. So what we're doing here is we want to go through each item in each list. The way we do this is first we say y in list of lists. So y then becomes each sublist. And then we want to go through each item in each of those. So we have for x in each y, and then x is the return value. And you'll see that what this produces then is the flattened list that we desire. We can also nest list comprehensions, which becomes very powerful. So if we want to find all the integers greater than and with 3 as a factor and divide them by 2, we can start by making a list comprehension that goes through all the numbers below 20. So I think we're assuming we want to start with that. we want to find the ones that are divisible by 3. So we use the mod function and say if mod 0. And remember this, by using the conditional at the end, it effectively filters the results. And so now we only have results that are divisible by 3. Now if we take this whole list comprehension and nest it in another list comprehension, then we can filter that one for ones greater than 3, and then have the result be divided by 2. Now you can see here you can build up very complex functionality in list comprehensions, and I have to warn you that if you go too far with this, they become very unreadable, and at a certain point it's better to fall back to traditional for loops if you're going to have a lot of complication for the sake of maintainability and readability. But a simple one like this is still a powerful and useful tool in Python. Now let's take a real quick look at dictionary comprehensions. Very similar to list comprehensions. Instead of using square brackets, we use curly brackets. We iterate through some iterable, and then using that iteration, we create a dictionary. And you can see the format is, instead of a single item as the return value, we have a key to a value as a return value. So in this example, we start with a list of dictionaries, and we want to create a new dictionary where the keys are the names and the values are their IDs. So we iterate through each item in this list, and for each item we set it to X. Then we grab the name and set that as a key, and the ID and set that as a value. And you can see you get a dictionary as a result, a new dictionary that has the key value pairs as we expected. You won't see dictionary comprehensions as much as you see list comprehensions, but they are a powerful tool and useful to know for creating dictionaries on the fly, such as this.
In this lesson, you'll learn about lazy evaluation. Lessons include using generators, designing generator pipelines, and implementing lazy functions. Let's get started.
Let's talk about generators and lazy evaluation. In Python, generators are one of the most powerful and commonly used ways to implement lazy evaluation. We've touched on generators earlier. Generators is similar to an iterator in that you can iterate through it, but it evaluates in chunks as opposed to all at once. So let's look at a list in a generator. So we can see using a list comprehension we can make a list of 10 numbers. Very similar, we can make a generator of 10 numbers. Notice that we use the parentheses instead of square brackets to do so. And if we compare these two objects, you can see the list is a list, and when we print it we see the full contents of the data. In the generator's case, when we print it, we see it's a generator object because it has not evaluated the full contents of the data at this point. All generator objects will return a value using the next function. And we can see that it returns the first value, and then the next time we call it, the next, and so forth, and so on until it reaches the end of its iteration, at which point it will kick out an exception. Stop iteration exception. We can iterate using a generator. Let's reestablish this generator. The same way we can with a list with a for loop. And you can see we get the same response we would with a list. The difference being that instead of the generator holding the whole contents in memory at once, it only holds one item at a time. In a small example like this, that really doesn't matter, but when you start dealing with large pieces of data, this will come in really handy. Now, one difference between a list and a generator is that because a generator only knows about one item at a time, you cannot index into a generator. So that's a list. We can index, as we've seen before, into a list or any other sequence. But if we change this to a generator, we see that the generator object is not subscribable because it doesn't have the idea of multiple items within it. One big difference between a generator and a list is the amount of memory it takes up. Because the generator only knows about one item at a time and generates a new item each time, it takes up a lot less memory than a large list would. So here let's compare a list and a generator made up of a large number. So we can see that the list is substantially larger than the generator. This comes in when you're using large data sets. You're going to find that generators are a real time saver and really make some things possible that wouldn't be possible if you have to load it all in memory at once. So that's been an introduction to generators. Let's talk about designing generator pipelines. We can take generators and string them together into pipelines that are effective in dealing with large data sets and take advantage of the generator's ability to analyze limited data at a time. So we've already seen creating generators with the parentheses syntax. Now what we can do with these generators is string them together. So in this case we have a generator called evens, which is just producing even numbers. And then if we want to take that generator and find only the factors in those numbers which are divisible by 3, we can see we create a new generator using the parentheses syntax again. And you see that what we're iterating through is the first generator. So this generator will receive one item at a time. It will not produce all these items at once. It'll test to see if it's a multiple of 3. And if it is, it's actually going to return the factor that produced that number when divided by 3. So we have the 3 factors. And then we take this generator and we pass it to another generator. This one, you see it iterates through the 3 factors. It takes the value from that and puts it into this string. Inserts it, says this number is. And then we pass it to yet a 4th generator, which takes the value from the titles generator and calls title on it to capitalize the first letter. So let's go ahead and run this. Now we mentioned the next syntax, so we can see as we iterate through what the values would be. And as expected, we get 0, 2, and 4. The first letter is capitalized, as is the first letter of each word is capitalized. So we can string these and do really powerful things by stringing generators together. You'll see a lot of this in terms of processing data, especially large data sets. Let's talk a little bit more about why we want to use lazy evaluation. We've mentioned large data sets, and there's times where you're going to find data sets that are just too big to put into a Pandas data frame. So if we want to get our data from a large data set and reshape it to just get the parts of it that we're interested in and then put that in a data frame, why don't we do an example that shows that kind of pipeline. So in our example, we have a large data set of information about foods. But what we actually want is a Pandas data frame which only has the salt and protein counts for organic foods. So the first thing we can do is define a generator that only returns one line of the data at a time. So let's go ahead and do that. And we can see if we instantiate our generator with a file path, we get a generator object back, and we can call next on that object and the top line, which of course is the headers, and then we can see that one line at a time we go through. So let's make a new function which strings generators together to produce the output we want. So the first line here, this is the same functionality we defined in the previous generator. It returns one line at a time from an open file. The next line takes the outputs from that generator. It splits the data of that line, that row, and checks to see if the product in that row starts with organic. So it will only return then organic rows. Next, we look at that organic row, and we want to pull out only the title, which is the last item, and we use the negative indexing. We're going to pull out the salt and the protein, which are 6 from the end and 7 from the end, respectively. And then we're going to return that last generator as a generator object. And so, if we instantiate that generator with a file path, we can call next on it and see that what we get is only rows of organic food and only values for salt and protein. Now, with a generator pipeline like this, we can then instantiate a Pandas data frame with the columns we want, name, salt, and protein, instantiate one of these generator objects, and use that to populate our data frame with only the data we needed, and hence avoid having to process the very large data set, which with Pandas would be slow and ungainly. So let's run this. And we can see our result is a nice Pandas data set with only the data we want. We could process that data along the way if that was desirable. But this is a really important thing, because you're going to find large data sets come up all the time in data science, especially in production data. And getting a large data set into a form that you can then begin to explore and manipulate it in Pandas is a problem that you will run into again and again. Let's talk a little bit more about implementing lazy evaluation functions. With generators, we've seen the quick generator syntax, the generator comprehension as such, with the parentheses. But you can also create generators using the yield keyword in a more traditional function definition. If you want to do something more complex, you'll find yourself doing this a lot. And so you see here, we define a function. It takes some parameter. It doesn't have to, but in this case it does. And then what we do is we iterate through this, in this case it's a sequence, and we yield a value. Now what happens in the generator is it keeps its own state, so it knows where you are in this, and each time you call it, it iterates one place further. So here we go ahead and call this with a reasonably large number. You can see that each time we call next on it, it remembers its own state and moves on. So that's the basics of defining a generator. That yield statement is really important. One thing we can do with generators, which is a really interesting and powerful feature, is create infinite generators. So we've already talked about while loops, and if we have a while true, it will iterate forever. So in this case, we can create a generator which, given a starting value, will increment that value by 1 and yield a new value. And the generator, because it's keeping track of its own state, can continue forever. So let's go ahead and run this counter. And we can see that the generator knows that it started at 10 and increments up by 1 each time, as expected. Generators are not the only form of a lazy evaluation. Sometimes what we'll find is there's a expensive operation you need to do. Perhaps it's connecting to a particular database or remote server. And it's best to not actually make that connection until you need to do it. So this is the general pattern you'll see. So if there's some expensive operation, in this case we're calling it an expensive connection, what we may do is create a variable which holds that connection and is set to none, but then when someone tries to interact with it, if the connection hasn't been already made, then we create a new connection, but if it has been made, we reuse that one. You'll see that kind of pattern a lot in production code, especially with big databases and remote servers and that sort of thing. This has been an introduction to lazy evaluation. It's a really important part of dealing with large data sets, and you'll see it again and again in data science. In this lesson, we'll discuss pattern matching. You'll learn how to apply pattern matching. Lessons include performing simple pattern matching. You'll learn to perform regular expressions. And finally, you'll learn to apply text processing techniques. Let's get started. Let's start with talking about some simple pattern matching in Python. Some of this we've covered before, but it's good to review. First, let's talk about string pattern matching. We've already talked about using the in and not in syntax in all sorts of sequences, including strings. So here we can see that it returns a Boolean. If we had done not in, we'd get a false because, in fact, it is there. We've also seen the starts with and ends with, and those also return Booleans. One that's interesting is find, which returns the first index at which the substring is found. So if you're interested in slicing the string or something, using find is a way to find that substring within the outer string. Let's talk about list membership matching now. So if we have a quote, this is a fine quote, ignorance is the parent of fear, and we split that quote, we get a list of the words within the quote, because the split with no argument will split on white space. Now we can use the in syntax here again in that list, the same way we did with the string. And if we detect the fear in that list, then we can print a result. And we can see that we did detect fear, and we've determined that that is the best Moby Dick quote ever. We can also do membership matching with dictionaries. So here we have a dictionary of quotes from Moby Dick. Better to sleep with a sober cannibal than a drunk Christian is one. And for there is no folly of the beast of the earth which is not infinitely outdone by the madness of men is another. So what we're doing here is we're going through using the items function or the items method on the dictionary. We're pulling out the key and value of each key value pair in the dictionary. And we're checking if the word cannibal is in the value, and if it is, then we are printing out this string. So we should find it in the first quote, but not in the second quote. And we'll see that is the case. That's the end of the simple matching. These are methods we've used earlier, but they're powerful methods, and you should keep them in mind when you need to look at the contents of strings, dictionaries, and lists. Now let's talk about Python regular expressions. Regular expressions are defined as a whole language for doing matching and searching within texts. It's a very powerful area. There's whole books written on regular expressions in Python specifically. But here let's take a quick look and get some useful methods out of it that you can use right away, even without having to dig in that deep. So we'll start with, here's our text we're going to search in. We've got a variable named text. You can see it begins with Ahab and then Ahab's email address and so forth for other members of that text, all people associated with the C. So to do a simple match using this text, we'll keep the text on screen. First we import a regular expression, RE, and then we're going to use the match function that's associated with it. So first we give our matching text. This is the text we want to try to find, and then the text in which we're searching. So we can see if we do this using match, we get a match object back, and it shows us what we matched. We matched Ahab : which is indeed the beginning of the text. We can use this object with a simple conditional with an if statement. So here we can see we found Ahab. But if we try this with Peleg, you see we did not find Peleg. And the reason why is that with match, it starts and tries to match the very beginning of the text. So if your text begins with Ahab, as this text does, it does not find Peleg at the beginning. If we want to be able to find text anywhere within our text, if we want to find a match anywhere within our text, we can use the search function. So here's search. We're doing the same thing we did up here, except we've replaced search for match. And you can see, in this case, we did find Peleg. And we can look at what's returned. And you see we get a match object back, and we can see what it matched. So that's very simple searching and matching with regular expressions. As we get more powerful features, we can start talking about character sets. Now, when a character set is defined by brackets in your match expression, and the items within that brackets are what are matched. And so here we have two items, one for each set of brackets. And the first matches anything between capital A and capital Z. So that's all capital letters, and this is all lowercase letters. So in this case, the dash in the middle is a continuation between them. So you don't need the type A, B, C, D, E, F, G, etc. You can use the dash to represent a whole sequence of letters there. Because we have two items, what we have is a capital followed by a lowercase, and then we're going to call search on our text. And as expected, we get the first match, which is the AH in the AHAB at the beginning of the text. Now, we can use the plus symbol after our brackets to indicate more than one match. So in this case, we're saying we've got our brackets, we've got capital A through Z and lowercase a through Z, so that will match any capital or lowercase letter, and because we have the plus there, it'll match more than one letter. So now we get the whole word AHAB, which is the first case of letters strung together with no white space in the text. We can use the curly brackets to specify an exact number of items rather than the plus. So in this case, we're matching capital and lowercase letters, but 7 of them. In the first place we find 7 capital and lowercase letters as a string in the text, we can look and see, is Ishmael here. Now we can get more complicated with our match strings. So here we're still using character sets. So we have a lowercase letters in the first bracket with a plus, so that's at least one lowercase letter and potentially more, so it'll match until it finds something that's not a lowercase letter. We have the @ symbol, which we have to escape because it has meanings otherwise, and then another series of lowercase letters, a dot, which we escape to indicate that it is a dot, and another series of lowercase letters. So this should match, it's a very primitive match of an email address, but for the purposes of this demonstration it'll work. And you can see it matches on the first email address it finds. Now let's talk about character classes, which make a lot of this much easier. So a character class is kind of a predefined version of those character sets. And the one you use a lot is the \W, which indicates a word character. So this would be a single character, but it's could be lowercase, uppercase, very similar to what we did with the A through Z in the character sets. And then a \D is a number. And then once again, so here what we really have is a letter, a number, and a letter, and we don't know if the letter is capital or lowercase. So if we search that on this string here, we can see it matches on the first character, number, character case it finds, which is Y2K. Now, if we look at our match for an email address here with the character sets, we can make this much simpler by replacing these A to Z with the \Ws. And so here's the same match, just in a much easier to read format. Let's talk about groups. So we've matched our email address here. What if we want to break it up, and so we get the local name and the secondary domain and the top level domain as items? If we surround parts of our match string with parentheses, each area surrounded by a parenthesis will be a group. Now the 0 level group is the whole match, and then all the other groups are numbered thereafter. So this will be group 1, group 2, and group 3. So if we do our search on this and get our match, we can then, on the match object, access the groups by their index. And here we'll print them all out. So we see group 0 is the whole email address, group 1 is just the local name, group 2 is the secondary domain, and group 3 is the top level domain. We can go one step further with this, though, and make these groups named so we don't have to remember the indexes for all of them. So now we've got the same match string, but for each group we've added a question mark capital P and then put a word within these brackets. So that word will be the name of the group, or the key to get to that group in the match object. And so when we get our match object, we'll see we still have the top level group, which the 0 group we don't actually have to have an argument for. And then we can call a group by its key. So we can call the group here by name, and we can call the group here by its name, which is here, SLD, and group here by its name, TLD, which is here. And as you do more complicated searching and matching, this ability to name the groups that you've matched is really handy and makes it much less confusing. Now, up till now, we've matched on the first match we found, or searched for the first match we found. What if we want to find all of the email addresses in this piece of text? That's where we use the find all. So here we've got our same match we did before for an email address, but we're calling it with find all. And we can see that find all actually returns a list of strings. It's no longer a match object, but it has found all the email addresses or all the matches for this search term. With find all, we can specify named groups again, but because it's not returning an object, what it actually does is it gives you a list of tuples, and each tuple has, you can see, is broken up into the different groups. Now, if you want to be able to use these names as keys, like we were doing before, then what you probably want to use is the find iterator. So here we have find iterator with the same search term and the same text. And let's look at what it returns. It returns an iterable. With all iterables, we can use the next function to see the next object that's coming out of it. So this iterable, we'll call next on it, on our iterator, and see what we did is we called the top level group on that item, right? So that just shows us how to use an iterator. Now, if we put named groups on our iterator, so here we have our named group match string, and we can actually iterate through the iterator and call the group dict on each item in there. And you can see that what we get back is a dictionary where we have our keys to the values of our local name, our secondary domain, and our top level domain. So this is a great way to break up a string into usable data. And in this case, we're taking our iterable, we're getting the group dict out of it, and then we're using that data to create a new string where we've called the title on aspects in it. And you can see we get a whole new output. We've transformed our data through the use of regular expressions. Great way to work. Another thing that you can do with regular expressions is use substitution. So there's a regular expression sub function, and the way it works is you have the item you're looking for, the search term, in this case /d, which represents a digit. The item you're replacing it with, we're going to replace this one with a hash sign. And then the text through which you're searching. So here we have a text that has someone's secret PIN, and we want to replace the secret PIN with hash signs, and you can see that that works very well. We can also do substitution with named groups. This gets very powerful and kind of exciting. So here we have our email address again, our email address with the named groups that we've been using. But for our substitution, we use the \G to access a named group. So here in our substitution, we use the group top level domain, which is the last group here, and we're going to put that first, separate it with a dot, and then the secondary domain, and then finally the name. And then the final argument, of course, is the text that we're doing this to. So we're getting a new text, and we're going to see what we've done is we've gone through and replaced every email address with this domain backwards string. Now, if you're using the same regular expression over and over again, especially in high performance situations, you'll want to compile it beforehand. So here we've got our match string we had before, and we've called recompile on it, and that will give us a compiled regular expression object. Now this object has all the same functions we've been calling directly from the module up till now, so search and match and find all. but it's much more efficient memory-wise and runs much faster. But here's an example of just calling the search on the text as we did before. Anyway, as I said, regular expressions are a huge subject. There's whole books on them, but they're a powerful tool, and these simple examples should get you started with them. Now let's take a look at 𝑏eautifulSoup. 𝑏eautifulSoup is a library designed for parsing HTML and XML documents, and it really simplifies the process. If you're scraping web pages or other instances where you have to pull data out of complicated documents, 𝑏eautifulSoup is a really great tool. In this case, let's go ahead and we're going to pull some HTML from this website. And you can see the HTML comes back as a string. It's all one string, unparsed. We can import 𝑏eautifulSoup and create a parser. And then we want an HTML parser for this. And then Soup has a prettify method, so we can look at what it looks like, and we can see that it prints out the HTML in a much more readable format. We can look through that and see what kind of data we have there. Soup has a lot of methods for accessing this data. We can grab the title. In this case, we'll just get the string of the title. If we wanted to see the whole title tag, we could see the whole title tag that way. 𝑏eautifulSoup has search functionality, so we could, if we want to see all the A tags in our HTML, we can use find all on A. And we'll see it returns all the A tags in the document, which is quite a few in this case. If we wanted to take the document and find all the links internally, the wiki links in this document, we could use those A tags. So we could find all the A tags, get the href from each one, and then filter and say, well, we are only interested in the ones that begin with wiki, and then add those to a list of wiki links. And you can see we get those very easily. You can use 𝑏eautifulSoup to find links on a website, to pull data out of text on a website, to understand the structure of the HTML on a website. So it's a really powerful tool if you need to do web scraping. But this has been a simple introduction to it, but it gives you an idea of some of the functionality.
In this lesson, you'll learn to use sorting. Lessons include sorting in Python. You learn to create custom sort functions, and then finally you sort the data inside of Pandas. Let's get started. Python has a really powerful way of sorting that's just built into the language. Let's talk about those built-in sorting mechanisms. I'm going to use this World Food Facts data set that I've used through many lessons, and we'll use that as a basis of our data set so that we can do some sorting with it. So I'm going to, again, use Pandas, create a data frame, and now one of the things that you can do with Pandas is you can take, let's say, a column. In this case, I'm going to take all the columns in the data frame, and I'm going to return those back as a list. And so here you see that I actually have fat, carbohydrates, sugar, protein, salt, energy, and actually the name of the product. These are these values here, 7 of them, that show up in a list. Now, if I want to sort that, what I can do is I can actually just run sorted, which is, again, a built-in function in Python. You can see now the order has changed. It intuitively does the right thing, which is it alphabetically sorts the data that appears. I also can go and do a reverse sort, though. So if I do sorted and I pass in reverse is equal to true, then it takes that list of column names and it actually sorts it. Another thing that's really interesting that you can do in Python, though, so this is something where I intentionally put it into a list, but a list itself has built upon it the ability to do sorting. So if I go and I take that same food facts list and I say, before sort here, and I say facts.sort, and I use something that's available on the list itself, I actually can see that it does the same thing. So let me just show you actually how that works. So if I go to food facts here, and and I do a dot operation, you can see that it's actually sort is just built directly into the list, right? So if I do sort and I do a help menu, it says built-in function or method, and it has the same capabilities that the sorted function has. And if I go to here and I go sort, this is the built-in, sorted, and I do the built-in sorted, you can see that it essentially is the same thing. It returns back a custom list. Really, the takeaway for this is that you do have the ability to do either use the built-in sorted, which works on any iterable, or if you're using a list, you can also just do list.sort and they behave the same way. Now let's talk about timing those two different types of sorts. So again, if you have a list, you can just go ahead and use the built-in sorted. So I'm going to use this magic method here, time it. I'm going to say, I want you to run it 3 times for three different loops 3 times. And you can see that the best time here is 489 nanoseconds. Now if I use the built-in function, so again, I make a list and I use the built-in sorted, you can see that 3 loops, best of 3, is 656 nanoseconds. So really, they actually behave in a very similar manner. So there isn't really one advantage in terms of speed. The main difference is that sorted works on any iterable. And so we're actually going to do that next. We're going to go to a dictionary here. So I'm going to go to that same data frame, and I'm going to take just one row out of that data frame by using head 1, and then I'm going to convert that to a dict. Now you can see here that I have carbohydrates, then I have the values energy, I have the values fat, right? So I'm going to go ahead and take that, and I'm going to do a reverse sort, because you can see here it's already sorted in an alphabetical order. But if I use sorted, and I again pass in this dictionary that I created, and I do reverse true, now you can see that it actually swaps that out, and it gives me back a list as well. So a pretty powerful built-in functionality here, and it works on any iterable. It works on not only a list, but it also works on a dictionary. So let's go ahead and see here, if we look inside of here and we look at all the different products, maybe we can do some additional powerful things by plugging into a different type of iterator. So one of the iterators that we've used quite a bit in many of the lessons that we've shown is a generator. And what I'm going to do in this example is I'm going to create a function that takes a data frame and also takes a column. In this case, it's going to take the product column, and it's going to return back chunks of 10. So basically what it's going to do is it's going to grab 10 rows at a time, just the product itself. And that's, I'm also going to grab a count here, and then I'm going to grab all of the rows in the data frame, and then I'm going to yield back 10 products at a time until the data frame is empty. And that's one of the really powerful things you can do with the generator pipeline. Next, if I go here and I say rows, data frame rows, and I say next on it, you can see it'll grab basically 10 items at a time. Now if I want to grab the next 10, I go here and I say next, right? So this is really a powerful workflow, right? I grab these 10 products out at a time. But now what I'm going to do is I'm going to use the power of sorted, and I'm going to combine that with this lazy iteration style. And so what I do here is I create a generator pipeline. And so what this generator pipeline does is it goes through and it actually grabs one of the items inside of here and sorts it, these 10 items, and you can see that it actually is able to sort this result. So a really powerful style of processing. So I first go through, I grab a very lazy 10 products at a time. I then take those 10 products at a time, and as they're coming through this list here, you can see that they actually keep getting changed, right? I keep sorting all of those items one by one. So I could essentially create an infinite list of things that I actually go through and I sort, all based on this ability to do a generator pipeline-based operation. In addition to using the built-in functionality of sort or sorted, Another thing you can do is you can actually write your own functions and customize a sort function. Additionally, you can also go in and build your own, outside of the whole sorted mechanism, you can build your own custom functions. So let's go and see here and look at this example of these food items, right? These are just products that were originally from a data frame. They're now placed in a list. And what I'm going to do is I'm actually going to create a customized shuffle of this list here. So I'm going to basically randomize it. So in order to do that, I say from random import sample. I then pass in a list here. And then what I do is I use that random sample and I look at the length of the items right here. So we know that there's about 10 items in here, and I'm going to randomly pick a sample of those 10 items and return back a shuffled version of that list. So if I run this and then I go and I shuffle that list, you can see that it actually randomly changes the order of the things in that list. And I can actually just keep running this and it'll just continuously give me random samples. So what's powerful about this is that one, you could actually use this to build your own data processing pipeline or do some kind of sampling, and this is powerful. But what we're going to do is we're going to use that as the precursor to test our own sorting functions, right? So first this randomizes things. You can see there's no particular order. Now I'm going to write my own custom sort function, and I'm going to test out how I can actually rearrange that in a non-alphabetical way, just any way that I see fit based on building my own customized sort function. So I'm going to write a function called best snack. And what this function does is it takes an item, this is a custom sort function, and it says if the item is chocolate nut crunch, it's going to return 1. Otherwise, it's going to look at the length, how many characters are in an item, and it will return back the shortest character length first, and then everything else will proceed after that. So basically it's going to sort by first this chocolate nut crunch, which is going to be the top item, and then everything else will be the length of the item. So if I go through and I run this, you can see what happens here is I pass in this key here, which then calls this function for every single thing in the list. Now you can see that chocolate nut crunch is the #1 thing in the list, and now look, this is all based on the length of the string. So this isn't based on alphabetical order, it's a custom order that I've decided, and I can actually apply that. So really powerful concept that you can do whatever you want. Maybe you could sort by how powerful the customer is and what their impact is on your company, or maybe you sort by the best athletes, or you sort by whatever thing you can think of that's custom to your company. You can create these custom sort function and then apply them to a list. So really, really interesting concept. Now another very powerful thing you can do that's maybe not intuitive is you also can sort objects themselves. So what I'm going to do in this example is I'm going to take a class here called food, and this class has a product, and it also has the grams of protein that product has. And I'm also building out a repr override here that shows when I make an instance of this class and I print it, it's going to print out what the name of the food is and then how many grams of protein. So there we go, I make an instance of that. And then in this next section here, what I do is actually grab both the product name and I also grab the amount of protein that product has, and I grab just the first 5 values out of the data frame, and I convert both of those items into a list. You can see here's the results. So I have a list that contains a list of the product and also the grams of protein that product has. Next, what I'm going to do is I'm going to take those items here and I'm going to create a list comprehension that basically assigns it to a food keyword, and then the value would be the name of the product, and then a protein keyword, and then the value is the number of grams of protein. So there we go. So I've kind of teed that up. And now that I've actually been able to process that, what I'm going to do is I'm actually going to take that and actually apply that class that I created earlier. I'm going to go through and I'm actually going to call this food.protein method on every single thing that appears in that list. So I'm basically going to sort the list that has a bunch of objects inside of it, and I'm going to sort them by the grams of protein. So if I go through here and I go ahead and I click on this protein here, you can see that previously the sorting was slightly different here, right? This 14 grams of protein for cinnamon nut granola is at the bottom, and now you can see here that it's actually completely sorted by the order of how much protein is actually inside of the class. So really, really powerful workflow here. And just recap it one more time is go through, you create a class, go through and grab some things from a Pandas data frame. You use a list comprehension to populate all those objects so that they have both the product name and also the value of the protein, and then you go through and you sort those out. Now, one of the things that I'm going to show you as well here is if I go and I just grab, one of those things out of that list here, you can see that, and I do under dict on it, you can see that it actually has a bunch of data that's associated with it as well. All right, so to wrap this up, now that I've shown how you can sort objects and there's all this power in doing that, let's go ahead and just look at what's inside of one of those objects. You can see that if I go through here, these are the objects that were actually sorted. So there's a product that has the name of the product, and there's a protein that has the grams of protein. And also, if I go through here and I say type of food, and I say 0, you can see that the type is actually an object. We're going to talk about Pandas sorting. So we've talked a little bit about just regular sorting with lists and dictionaries and generators and objects, but you also can do sorting in Pandas, and you can also think of Pandas almost as its own different language. So let's go ahead and look at Pandas here, and let's see how you could actually take a data frame here and sort the entire data frame all at once. So here's an example of a data frame that I actually say sort values by, and the way you sort a data frame by a column is you say by, and then you pass in the name of the column name. And then you really have two choices. You can say by default it'll ascend, it'll be ascending true, and that'll be the lowest values to the highest values, or you can say ascending false, like I do in this example, and then it'll actually sort by the highest values first. So if you see here, this is 100, right? So that is in fact the maximum that the value could possibly be, because what this field is out of 100 grams total of weight, how many of those 100 grams are protein? So gelatin is actually pure protein. Cocktail shrimp is 86 grams of 100 grams of protein. And then I also just grab the first few rows. If I change this, let's just grab, let's say 5 here, it'll return back just 5. So really the combination here is that I'm able to cascade several things together to get the result that I want. So this is sorting the entire data frame, and then this just gives me back from that entirely sorted data frame the first 5 rows. Now I also can do true here just to see what that result looks like. Here we go, and now it should be completely opposite. So this looks like actually it's a bad value, which is actually a really powerful version of sorting, right? It's like it can show you that it can find outliers that should be discarded. So this is food, right? It's not even logical that something could have negative protein, right? That is not actually a real value. So this is an outlier that potentially I should throw out of the data set. Also, let me show you the differences if I swap it out with a different column, right? We should get a different value here. So here's carbohydrates. Let's look at the ascending true. These are the lowest carbohydrates, right? So these are all 0. That's what I would expect. And if I say ascending false, it should show me the foods that have the highest levels of carbohydrates first, and it does. SpongeBob SquarePants Valentine candy, probably not that healthy for you. And it has 100 grams of carbohydrates, and of those carbohydrates, 85 of those are actually sugar. So very, very interesting filter here. But again, this is the part that sorts it by that value, and also this is what toggles it back and forth. And then again, this head shows me how many rows I want to come back with. So that by itself is pretty powerful, but let's go ahead and sort by a little bit more than just one column. What if you want to sort first by one column and then additionally do a secondary sort by another? Well, you can do that with Pandas. And here's an example where what I do is I again do sort, and I say by, and I pass in sugar first, salt second, and then I can actually even toggle this too. I can say this is the primary sort and this is the secondary sort, but in both cases here, I want you to always show the highest values first. So the first priority in this case would be sugar. So you can see here, these are all 100. So it returned back what we wanted. And then you can see that the secondary priority is going to be salt. And so it then basically looks for all values that have this max value. And then it looks for, of those 100 valued sugars, let's see which ones are highest, right? So here's the secondary sort. You can see that this is turkey brine, right? So it's basically pure sugar and almost all salt. Again, probably not a very healthy thing to consume in large quantities. And if I toggle this, we could actually see what is very sugary but has 0 salt. So let's go ahead and do that. So now let's see the opposite sort. Now you can see here that I've changed it, and these are all 0 salt. So here's some candies here, dessert toppings that are actually showing. So radically different results, again, based on what I search for. So what if we look for, instead, we change this to fat. Let's go ahead and change that. And then we'll also say, so we want to look at really fatty food and also salty food. And let's see what pops up. And what we see here is that turns out that 100 grams of fat, so this is essentially almost pure fat here. And then in terms of salt, these are the 2 top salty results. So we can see that roasted pecans and horseradish sauce are both very fatty and very salty, and we've been able to sort it by that secondary sort as well. So really powerful concept. If you haven't done this in Pandas, definitely recommend you playing around with not just doing sorting by individual columns, but by multiple columns, and also changing the primary and secondary sort to get different results. If you're dealing with a really large data frame, this could be really a miracle worker, and allows you to really dig into, in the example that we saw earlier, for example, find an outlier. Now let's look at another way of manipulating data and changing it around so that you can actually understand what's happening. I'm going to go and use an example that we've shown in a previous lesson here, which is this high protein feature that I'm going to create. So again, what I'm going to do is I'm going to create a function here that says if the row is over 80, return high protein, otherwise return low protein. And what it's going to do is it's going to create a column on this data frame that shows me whether something is either high protein or low protein. So here we go. Again, I run that. You see here again that this is high protein column, and then either have high protein or low protein. So what's really powerful about this is I can use a function called group by. And what group by does is it actually grabs all of these high protein values here, and then I can apply some kind of statistical operation to that group by. So here I look at that column and I see that the median value for high protein foods here is 93, right? So again, we know that 100 is very, very high, right? That's basically pure protein, but we see that the median for the high protein foods that we selected is actually 93. And what's interesting is it also shows these associated columns. So for these, the median high protein food, you can see that the medium fat is actually pretty low. And also we can see that the salt is at 0.5 grams, so it's actually a reasonable amount of salt, and you can see what the energy characteristics. Now for low protein, you can see there's a completely different type of characteristics. So for low protein food, it has a little bit more fat, it's got a lot of carbohydrates, and also some sugar with it. So you could now start to create potentially even a model, based on this is, could you classify things and actually maybe take a picture of something and actually identify whether it's a high protein food or a low protein food. And all of it's done just by doing a couple things. Step one, creating a brand new feature. And it doesn't have to be just a high protein feature. It could be, a high carb feature. And then applying this group by operation and then doing a statistical, operation to this group by. Let's look at one final thing we can do with this group by here. If I go and I say df group by, again, by high protein, let's actually look at the descriptive statistics of that entire group by operation. So this is a great way to get a huge result set that shows us all kinds of really interesting things. So one of the things we see right off the bat is that there's only, of these 45,000 items in this data frame, only 4 of them are high protein. So that's interesting. And 45,000 are not. So in this data set, there are very few that are very high protein foods. And also we see that in terms of the low protein food, we have the 25th percentile for the median, the 50th percentile, the 75th percentile, and also we can see associated, again with those same results, what the breakdowns are for these other categories. So hopefully in this section we've demonstrated that group by operations, sorting are really powerful techniques that you can use in Pandas.
In this lesson, you will learn how to apply I/O patterns in Python. Lessons include reading and writing files, reading and writing data with Pandas, reading and writing web resources, and finally, use function-based concurrency. Let's get started.
Let's talk about reading and writing files and serializing data in Python, a really important thing for data scientists. When you're working with files, really the go-to way to do a file write in Python is to use the with context statement. So here's an example of using the with statement, and there's an open command that opens a file that's in write mode. That's what the W stands for. And then what happens next is that I write inside of that file whey protein. So here's an example. I open it up, and then if I cat it using this exclamation point command and using the Unix command cat, you can see that it was in fact written into this file. So I also can write multiple things as well. So I can go here, workfile.write, and I don't know what goes along with whey protein, maybe like a Cliff Bar. Here we go. And now I've actually got a couple things written. And if I wanted to actually add, for example, a new line character, I could also go here, and then each one of them would be on a separate line. So really straightforward way to do this is to use this with statement, and what it does is it alleviates the need to specifically close the file, which is a real problem, and it's very easy to do, and then all of a sudden you haven't written something to the file, you think you've written it, and that's really what this with statement does. Additionally, when you want to read a file in Python, you can also use with statement, so you also don't have to do a close. So it looks very similar. I say with open, and I read in that file that was created earlier, and then I say with open, give me this work file, and then print out the actual lines. And so workfile.readLines takes returns back an iterable from this file object. Now I also can tweak that around a little bit, and I can say instead I want to get a string back, and I can say workfile.read, and then it'll actually just return back a string. So you have a couple different options when you're reading a file in Python. So this alone is actually quite useful, and it will get you a long way. Another approach, though, is to think about different ways to store data. So I'm going to go and use this same data set that I've been using quite a bit. I'm going to read in these food facts, and what I'm going to do here is I'm going to read in some of those values. In fact, I'll just create one row, and I'm going to put that into a temporary data structure here. So I have a dictionary. It has just one row of data from that food facts database, and let's set up an imaginary scenario here that happens quite a bit. Let's pretend that you're maybe the first week on your job at a job, and you've been working all day, and you've, for example, come up with this data frame, and it's got all this value in it, and you actually want to write it to your company's database. And it turns out that you're in a place that has very strict IT policies, and they haven't given you access to the database. It could be weeks before you get access to it, but you've done quite a bit of work, and you want to save this data somewhere. Well, what do? Do you just hope that no one reboots your computer? There's a saying that hope is not a strategy. So what we want to do is we want to come up with a solution that can give us some temporary results here. So what you can do is you can use pickle. So I'm going to import pickle. I'm going to take this dictionary that again was just one row from a pandas data frame, and I'm going to actually write out the dictionary directly to disk using pickle. So in order to do that, I just define a file. It doesn't have to be called pickle, it could be called anything. And then I do write binary. And then if I run an ls command here, you can see that this was just created, and this pickle file now actually has a serialized version of that Python dictionary. If I want to read it back in, let's say the next day, I go res pickle, and then I type in res, and you can see the exact same data structure has been actually kept back into Python. So this is really an incredible workflow that for some operations can be extremely valuable. You take a dictionary that maybe was the pandas data frame, you write it out to disk, and then you bring it back in again. Now let's talk about a slightly different version of the same thing. So there's a data structure called JSON, JavaScript object notation, and this is another similar approach where I import the JSON library, I say with open, and I open it using a context, and I actually dump out a dictionary to a JSON format here. And so what's great about a JSON format is that I could give this to, let's say, the front-end developer team, and they could take this and they could do something with it. I could also take this data and easily pass it through on some API call. So JSON is a great format if you're dealing with developers. And then if I want to go ahead and read that JSON file back in, I can go ahead and read it back in. And then if I look at the results here, you can see that I was able to easily convert that JSON file on disk back into Python by using json.load. So this is another great way to deal with reading and writing data out, especially if you're doing things with developers. Now, another similar version to JSON is something called YAML. And what YAML is it's really essentially a subset of JSON. And if I look at this YAML file, I say with open.yaml, I use this YAML library, and I again dump something out to disk, and I say default flow style false, and I say safe dump. And what this does is it makes sure that I don't include anything that can be a security risk. And then if I cat that file here, you can see the format is really almost like a human readable format. So it's got the key, and then it's got a colon, and then it's got the value. So you could potentially give this type of data to someone that's non-technical, and they could just go in and edit it and change it around, and it would give you the ability to actually communicate with non-technical people in your company. So a lot of times you will see the YAML format be heavily used, and you can see that it's really just a dictionary. I can write the dictionary out the disk. I can then give that file to someone, maybe they can modify it, and then I can load it back in again. So let's talk about loading it back in. It's really simple. I go here and I say with open data.yaml, and I open up this YAML file, and then I again load it doing a safe load again, so I prevent security risks. And then I print out the dictionary, and I also look at the type. So let's go ahead and look at this type here. You can see it's a dictionary, and then if I add a line below here, we can see it's the exact same thing. So YAML is a great format to use, especially if you're dealing with people that are non-technical, and hopefully all of these different techniques are techniques that you can use depending on the context that you're working in. In this section, we're going to talk about reading and writing files and serializing data with Pandas itself. Pandas is its own real ecosystem. It has some real different characteristics than, let's say, files or regular Python. And so there's some different techniques that need to be used when you want to read data in and read data out from Pandas. So let's get into Pandas data frames a little bit. So one thing that we've shown actually quite a bit that I just want to specifically call out is that you can create a data frame from a local file, and that's a fine way to do it. Or you can also just create a data frame from something that's hosted on a website. And in this example, I'm actually reading in a CSV file that's hosted in GitHub. And I go through here, I say pd.read_csv, and then I do a little bit of data cleaning, and you can see I've actually been able to load this into Pandas. So this is one of my preferred methods of reading data into a data frame, is just to host it somewhere else. And then of course I can go through here and look at the median values, and it's a great workflow. A different approach that is worth calling out specifically is that you also can take a list of an existing Pandas data frame. You can actually take a column, convert it to a list, and then convert that into its separate data frame. So here's an example where I take products, and I take the entire column and I convert it to a list. And now what I do is I make a new data frame just from that one column. So there were 7 columns before, now there's just one. I then name specifically that column, product, and then I look at the first 3 things inside of that data frame. So this is actually a great way if you have a huge data set and you want to, let's say, just operate on one of the columns in your data frame. You could just export it out to a list, make a new data frame, name the column, and then play around with it. And then you can see here that it also gives you like a smaller data set to work with. And here's an example. There's 44,976 products, and actually ice cream is actually the top product that's listed in this database. Now, let's also talk about going out of Pandas. So we talked about bringing things in, but a really great technique to use that you should be aware of is that, of course, you can write out a CSV file very simply by just saying to CSV. In this example, I'm going to additionally capitalize on that and show you an interesting technique, which is if you use df.head, and if you remember, head just grabs the first 5 rows, or whatever number you want. If you want to put df.head 10, and it would give you 10 rows. In this example, what I do is I essentially truncate that file, and if I do the cat operation here, you can see that now I only have a few rows inside. So this is a great way to, let's say, work on the data engineering side of your problem. So you can make a small version of this, let's say you have a 1 gigabyte or 2 gigabyte or 10 gigabyte file, or 100 or a terabyte, or you have a really large file. You could actually, again, just write out the first 5 rows, get all of the data engineering problems solved, write custom functions, do descriptive statistics, get all the charting set up. And then once all that is set up, then you can actually put in the real file. So this is a really powerful workflow to know about, is this ability to truncate a file. Of course, you also can just write the entire file out to disk as well. Now, another interesting technique that is worth pointing out is this Pandas on Ray. And the reason it's important to bring up right now is that we were just mentioning the 1 gigabyte data set. Well, I've had many situations actually where I've used Pandas, and 1 gigabyte of CSV file actually blows up the machine that I'm running on. So a lot of times I do work inside of the cloud environment, and I may have a smaller instance. And Pandas, one of the things that it actually has as a limitation is that it takes between 5 to 10 times the amount of RAM to process the file that you're working with. So if you have a 1 gigabyte file, it could take anywhere from 5 gigabytes minimum to 10 gigabytes of RAM. So if you're working on a cloud instance that has 8 gigabytes of RAM, it's possible it just won't work, and you'll get an out of memory error. So one potential solution to that that's kind of interesting is this Pandas on Ray solution. And if I go ahead and I click on this, here's a recent example. What it does is it shows you that you can use an existing Pandas API. Here we go, import Pandas as Ray. And what it does is it actually uses Redis server, a cluster of Redis servers as an intermediate, and actually gives you the ability to actually handle larger data. So that's kind of an interesting use case for this Pandas on Ray ecosystem. Now, another version of a large-scale Pandas workflow is Dask. And so what Dask does is it natively scales Python, and it provides parallelization tools for you. So it works with NumPy, it works with Pandas, it works with scikit-learn, and so you also could use a Dask version as well. And so if we go ahead and we look at this version, we could spin this up and play around with the Jupyter Notebook right in the browser and use some of those same basic documentation workflows that we've just observed. So now let's shift gears a little bit and wrap this section up with Google Sheets. So it's not common to really think about Google Sheets as a database or as an intermediate data format, but because we're using Colab notebooks, actually Google Sheets are a really interesting intermediate data source for us to use. So in order to use Google Sheets, what I'm going to do is I'm going to install the Google Spreadsheet library, and then I'm going to do an authentication to their API. So you can see here, this is basically boilerplate code from Google Colab import auth. I go through and I authorize get access to their API. There we go. And now what I do is I actually make a sheet here. So this is actually calling their API. I create a sheet inside of Google Sheets. I open it up, and then I actually just operate on these cells A1 through A10. And what I do is I say for every cell that's listed, this returns back a list, go ahead and populate that cell with the products that we created earlier. If you remember, the products were all the food products. So I'm basically going to go through and like populate that list full of food products. And then what I'm going to do is I'm going to say worksheet.update cells, and then I'm going to go ahead and update that cell. So really powerful workflow. I could take a Pandas data frame, authorize the Google API, take that data, and then permanently store it inside of a Google Sheet. So then again, a non-technical person could go along and actually get access to that. So let's go ahead and look at what that created. So I'm going to go to Google Sheets. And then Google Sheets, I should be able to find very simply the last Google Sheet that was created. And here we go, pragmatic API test. Let's go ahead and look at this one. And now you can see that it was able to actually create a new Google Sheet programmatically from data that initially lived in a Pandas data frame. So I think this is just a super fun workflow that is really recommended. And I've actually used this in projects, like real projects with people, and I've had such a great amount of feedback with people liking this workflow. So now let's look at the other thing you can do, which is I can then go to that worksheet. Let's just say that this initially seeded this data, and then I've had some people that I've been working with, and they're helping me out, and they're putting new food items in here. Again, I don't know, we'll call this whey protein, right? We'll put some whey protein in here, and now if I go back to my notebook, I can actually go through and I can grab the data out of the Google Sheet, put that into a Pandas data frame, and then you can see here even the whey protein value was actually put inside. So really incredible back and forth workflow that you should consider, especially if you're using the Google Colab ecosystem, is do a bunch of processing in a data frame, take that data, write it out to a Google Sheet, work around with non-technical people, let them manipulate that data, then take that data and pull it back into a Pandas data frame, and then do statistics and machine learning modeling on that data. Another thing that comes up quite a bit when you're doing data science is that you may need to do things other than just use Pandas. And this is the real world, right, is that you may need to go and collect data from an external website. So one of the ways you can do that is using this Python request library. And it's actually built into Colab notebooks. And here's an example of something I've actually done for a real data science project where I use the request library, and then I actually made an instance of the Wikipedia page views API. So here's an example of how that looks. Here's the API. It says REST version 1, metrics, page views, and I look at the per article metrics for the English version of Wikipedia, and I want all of the records, and I look for LeBron James. I look at his daily page views all the way from this 2015 to 2017. And so if I go through and I look at that, it comes back into this result object, and then I say result.json, and I get back the results of that query. So you can see here that I was able to find out that the daily page views that were achieved during that period of time were 18,390. So you could use that later for some popularity metric, or directly take this data and call, let's say, 1,000 different pages inside of Wikipedia, and then put that into a Pandas data frame. So really important to know that this is also part of the workflow of being a data scientist, is being able to understand how to use web-based requests. And here's actually a great technique that you could use. Now let's talk about Bodo as well. Bodo, I would call it the language of default for dealing with the AWS ecosystem. And you can see, in order to grab, let's say, some data from AWS, you import Bodo 3, you then make an instance to Amazon S3. I then put in the name of my bucket, I put in the name of my file, and then I can actually load that somewhere on my disk. So this is also a great technique to use if you're not familiar with the AWS ecosystem, but you'll see this kind of a syntax quite a bit when you're dealing with other projects. Another thing that we've already talked about that I won't go into too much more detail about, but again, GitHub is a great place to store CSV files, and it's worth pointing out that you can put in both the small files that we talked about and also the very large files. And these large files can be stored with the GitHub large file support. So again, even like very large files like gigabyte size files can actually be stored inside of GitHub. Another thing as well, and we've shown this in another lesson, is that when you're talking about web resources, you can also just upload the Kaggle data into your Colab notebook or your Jupyter notebook, or download it locally and work with it. And so these are all four of these using web, using Bodo, using GitHub, using Kaggle. These are probably of let's say 15 or 20 different ways that you can talk to different web resources. These are probably the most common that you're going to be talking with when you're doing data science in Python. In this section, we're going to discuss function-based concurrency in Python. And with function-based concurrency, really what it means is that you're thinking about the ideal building block of distributed computing, which is a function. You're thinking about putting things in, doing some processing, and returning something back. And one of the best ways to think about that is to think about the multiprocessing module. It's worth pointing out, and I've said this in many different lectures that I've done and talks that I've done, is that threads are a really bad technique for Python in general. I mean, the simplest possible way to describe it is that because of accidental things that have happened with the language, threads are just a very bad choice. So in other languages, threads are a perfectly reasonable choice, but in Python, don't use threads. So instead, use some of these other methods that we're talking about. In this example, we're going to take a function and map it to some forked processes. So in Python, you say from multiprocessing pool. I take some standard library things in here, and all this is just a silly function that pretends that it's like a video game that does some kind of a punch. So I say sleep, I do some operations, and I do some kind of return back some value. So if I run this, you can see here that I'm able to actually spawn a few different processes, and they're all run in a random order, right? Because they're all randomly associated, and I just map that function directly to a pool of processes. And there's actually 5 total. So I could actually put in more things and I could do more processes. But this is a great technique because you just take a function, you spawn some processes, and you say for each one of those functions, hey, you do this work for me. So instead of this silly function, it could be k-means clustering, or it could be maybe a deep learning problem, or I want to try like 5 different algorithms. But this is a very simple and powerful approach to doing multiprocessing in Python. You also can mimic the thread type API as well. And so this is actually a great approach as well. So I can say from multiprocessing import process, import queue, and I put a few things inside of here. In this case, I put an armbar, a kimura, a monteleone, which these are all techniques for Brazilian Jiu-Jitsu, and I put those inside of a process, and then that process will grab them off of the queue, and I could actually do a giant distributed workflow that way as well. So what's great about that is that you can actually have more of a producer-consumer workflow, and this is actually fully multi-core. So this is more traditionally something you would do with threads, but you can do it quite easily with processes, and you don't have to worry about all the edge cases with threads in Python. Another thing that's worth pointing out here that is really a cool technique is this async I/O. And if you look at some other videos that I've done, I actually go into quite a bit of detail on it about how you can use it for a logging library for Amazon. And here's exactly that code. If I look through here and I say, I want to asynchronously send 100 messages, what happens here is that actually it's able to use networking I/O technology, and it's able to actually go and asynchronously send a bunch of messages without having to use other things like threads or processes. So this is completely thread and process free. It's a single threaded function, but what it does is it uses the network underlying technology to actually send a bunch of asynchronous messages. So really a pretty powerful workflow. You create an event loop, you do a bunch of stuff in that event loop, and then you wait till all the tasks are complete, and then you go ahead and you close that loop. So again, if you're just going to fire off, let's say 100 messages and you want them all to happen sub-second, this could be a great approach to use. Now, there's another version. There are still people using Python 2, and so I just wanted to point this out that here's an example of using a library called Trollis, and this is a real-world code that I wrote that actually talks to Amazon's metadata API. So this gives you back a bunch of data about your instance in AWS that you spawn up. And so what I do is I go through, I call that metadata API, and again, it looks very similar. I get the event loop, I append a bunch of tasks to it, and then finally what happens is I asynchronously get back all those results. And if you see here, this is an actual result that I threw into this interface. You can see here that I just call it once, and I can get something like 20 different API responses all back sub-second. So really, really powerful technique to use is this async networking technique. And again, it's completely running on one process. Now let's talk about a different level of concurrency that you can play around with. And this one is called serverless, or FaaS, or function as a service. Probably the leader right now is AWS Lambda. And there's a framework that I use sometimes called Chalice. And here's an example where I can just put app.lambda, so a decorator, something we've covered previously, on top of a function, and I can actually, in this case, send Slack messages. And what's interesting about this is that I could take this function, and just by putting this decorator, I could literally run 10,000, 100,000, a million concurrent functions, and these would all be handled by AWS for me. So this is one of the most powerful techniques that's available right now. I'm not overstating how incredible this technology really is the ability to just take a function and deploy it somewhere and not worry at all about scalability. So this is really, I think, the end game for many problems in the future, is that why do you need to manage this level of concurrency? Just focus on the logic, and you can actually let the cloud provider handle that concurrency. There is an open source version of this type of function as a service, and here's an example of this project. So it's very similar. Again, you say, I want to run this Python function, you pass in some data here, and you can actually run this on something that, for example, runs containers. So this is not unique to just the AWS cloud. Also, Google Cloud has functions as a service. So Microsoft Azure has functions as a service. So this is definitely an emerging technique, and for data scientists, and especially, I think this is going to be a really powerful technique to use. Now let's talk about some other large-scale concurrency solutions. So another thing to look at is AWS step functions. And so what this does is it allows you to define a state machine that is in basically a JSON format, and you can just wire together a bunch of lambdas and basically can create a workflow here that actually fits different operations. And this is obviously a really powerful technique because you don't have to write all this instrumentation code. Another one, AWS Batch, is a good example. You can actually go and use their distributed jobs framework to actually do big data processing. I've actually used this in the past to do large-scale computer vision projects where I've spun up thousands of instances of machines, and they've actually gone through and run functions and then return back the results as S3. So the nutshell here is that, you know, AWS, Google, Azure, all these cloud providers have these batch-based systems, and oftentimes that's really the best approach, is you take a function and deploy it to that system. Now, a more do-it-yourself approach, and I have an article that I've referenced in the notebook, would be this type of approach where you would use your own web service, and you would have the web service handle a bunch of requests. So let's just say that a Tornado web service, if it was configured properly with load balancing, you know, you could potentially scale it to, I don't know, 100,000, 200,000, 500,000 requests per second. So, I mean, you can keep scaling this out, and you can be pushing those messages into RabbitMQ. And now what you can do is you can do the same approach that we've talked about previously, is you can have a bunch of workers, and each one of these workers grabs a message off of RabbitMQ. So what happens is that you make RabbitMQ do all the heavy work and heavy lifting, and you have Python do basically nothing, which is run something after it's collected it from RabbitMQ. So really the takeaway of this kind of architecture is that, and this would be like a three-tiered architecture, is that you have something that is very async. It could even be a different language. It doesn't have to be Tornado. It could be Java or C# or something. And it just sits there and pushes messages. This could also be some other cloud-based data engineering system like Kinesis. It pushes things into a message bus, and then you have the workers just consume things one by one in a serial fashion. So really the takeaway here is that don't make Python do high concurrency work. It's horrible at doing high concurrency. Make it do what it's best at, which is write glue and scripting code instead. I'm also going to talk a little bit more on that process of Python and what's the opportunity. So a very famous computer scientist, this is David Patterson from Berkeley, who works on Google's TPU or TensorFlow processing architecture. He has mentioned this in a talk that I attended, that matrix multiply speedup over native Python. You can see that you can actually get 63,000 times better performance by optimizing matrix multiply speedup. And so here we see Python, here we see C, parallel loops, memory optimization. So you can see basically Python is such a poorly performing language at scale, at distributed computing. And the takeaway here is that really the improper use of Python is to ever even consider doing things yourself where you're trying to do high performance computing. Let something else do the high performance computing. Use a high performance computing framework. So use the cloud, use TensorFlow, or use some NumPy, or use something that someone's highly optimized instead of trying to do all this yourself. It's just not the right tool for the job. And speaking of that, let's talk about some of the high performance technologies you can use. So Numba is one of those. We've talked about it a little bit in some other examples. So what Numba does is it allows you to do many different high performance computing operations. It's a just-in-time compiler. It translates a subset of Python and NumPy into fast machine code, and also can approach the speed of C. So you also can parallelize true threads and GPU. So let's look at an example of a vectorized type operation. So I would import CUDA and also vectorize. So CUDA is the API for NVIDIA's GPU. And then if I grabbed a data frame here, I would then next want to convert that data frame into a numerical data frame. So I go and I make a numerical data frame. Then I then go ahead and I convert it to a float, and now I have this array. And then the next thing that you do is you would go through and actually convert that into a GPU-based workflow. Another thing that we've shown previously that I'll show again here is if I go through here and I say import numba, you can also just say I want to use numba on just some regular Python code, and you can also say no Python true, and it just massively speeds up regular Python code and actually converts it. So I need to go through here, import that, run that, and then now I can actually go through and I can see this Python-based numba workflow. Another thing that's pretty incredible here is that you also can do true multi-threaded programming. So we talked about how threads are just really the broken Pinto of concurrency on Python. It's got the exploding rear gas tank. You don't ever want to use threads in Python, except if you use something else that's a high-performance library like numba, and then it can actually go and do all the work for you. So in this example, which is admittedly a very contrived example, I can just tell this to just arbitrarily spawn true threads and just completely saturate my system with threads. And so in this example here, in order to do that, I say numba.jit parallel is equal to true. And then what happens is that numba p range, what that does is it actually will spawn a thread for every one of these operations. So I'm not going to do that because I don't want to blow up this notebook, but you can see that it did quite a bit of work last time I ran it. And again, it's completely saturating my machine. And the final thing that I'll point out is that with GPU, it's heavily used in deep learning. There's NVIDIA and AMD, and these are also a couple options to use. And if you want to use a GPU, again, you can go through here and actually use these GPU operations. You can do a CUDA operation, and really in a nutshell, this is how it works, is you make an array and you do a vectorized operation. You then take that data and you move it over to the GPU. If you remember, traditionally, things are processed on the CPU. So in order to get it to the GPU, you have to physically move that data into the GPU memory. Once you've done that, the next thing you do is you then do a calculation on the GPU using this vectorized function here, right? And so this is all done completely using massively parallel architecture. You can see here the target is CUDA. Then when you're done, you then have to take that calculation, and again, this could be a deep learning problem, and you then have to copy it back out to host, and then it's done. So this could be orders of magnitude faster than other operations that you do, and you can see this is a really simple workflow that you could reverse engineer. Finally, I want to wrap this up with talking about TPU, and again, the TPU is available as an option inside of your notebook. If I go through here, I can say TPU, and so this also is a great way to do large-scale distributed computing. So really in a nutshell, the main takeaway for this section is that don't do things yourself. Use a high-performance framework. That's what it's designed to do. And really in Python, you should spend your time writing very small functions that are very powerful. In this lesson, you'll learn to share your work and build your portfolio. Lessons include sharing with GitHub, creating Kaggle kernels, collaborating with Colab. Finally, you post public graphs with Plotly. Let's get started. I'm going to talk a little bit about GitHub and how you can use GitHub to your advantage as a data scientist or a future data scientist. It's really important to think about not only doing the technical work, which we've gone into quite a bit of detail in all of these lectures, but also to talk about how to promote yourself and how to make sure that people understand that you can do the job that you're going to be hired to do. One of the ways you can do that is to customize GitHub. And what I'm going to do is I'm going to walk you through how I customize my own GitHub so that people can see the work that I want them to see. To start with, when you first log into your profile, there's something called pinned repositories. And one of the things you can do is you can customize which of your repositories actually show up. So if I go ahead and I click on this customize your pinned repositories, you can see I have quite a few repos here, but what I've done is I've taken the repos that have a lot of stars and I've highlighted those repos first. So you can see I have a repo called Pragmatic AI, Managed Machine Learning Systems in IoT, Functional Intro to Python, and I've actually highlighted those so that they populate. Now when I go ahead and I save the pinned repository, you can see that they've been updated, but I also can reorder them as well. So my recommendation is go with repositories that you are really proud of and they're cleaned up and you really want to show people your best work. And you also can think about the order as well. So one of the other things you can do is if you grab this little menu item here, you can also sort things around. So maybe one thing to think about is take the repos that have the highest stars and maybe you highlight those at the top, and then you can go through and kind of sort around and make sure that you're putting your best foot forward. Another thing to be aware of is that in this pinned repository section, it's really important to show that you're doing original work. Some feedback that I've gotten from high-profile companies in my role as a lecturer is that they'll look at these pinned repositories, and if it's a forked repository that has no changes and that's actually one of the pinned repositories, it sends them maybe the wrong message. So that's another thing to think about is when you pin your repositories, make sure you're pinning original work. Another thing to be aware of is this contributions section of GitHub. And if you look about my contributions, you can see there's 1,000 contributions in the last year, and there's a reasonable amount of steady work here that you can see. So this shows that I'm a fairly active developer. I'm very frequently writing code, and this is something that you should also be aware of, whether it's good or bad, that companies may look at this contributions window here and actually make some kind of a judgment. So a couple ways that you could think about solving that problem is that if you are going to show this contribution window, and you can actually change this, right? So we can go here and we can say, private contributions or activity overview. If you are going to show it, just make sure that you actually have something where it looks like you're regularly contributing, because it could send either a very positive message or it could send actually a negative message, again, for better, for worse. Another thing to point out as well is let's go ahead and click on one of these repositories. So I'm going to click on this Functional Intro to Python repository, is that you also want to make sure that you're putting tags in. So in my case, I have tags that show these tutorials are Python 3 based. I also have a link to a website where people can find out more information. And also there's a nice README file as well. So you can see here that there's a README that describes my project. I also have a Circle CI badge here that actually shows that my code is actually being checked, and there's a quality control pass. I also have a tag here that shows that this is original academic work. And then I go through and I actually nicely format everything in my repository. So these little bits of information can make a really big deal when you're promoting your portfolio. And so I definitely recommend that you think about making a nice README, make sure that you have some kind of quality control listing here, and also that it's really easy for someone to get started with your project. Another thing to point out as well is that there's a directory structure here that has notebooks in one section, tests in one section. I also have a makefile, and then you can see here that these are all notebooks that were controlled by Collaboratory. And again, when you click on one of these notebooks, we've showed this earlier, it actually has a link back to Colab. So there's this feedback loop where someone can go, they can look at my pinned repository, they can then click on it, click on the README, and then they go and they look at this notebook, and they can actually go in and open up a Colab repository notebook like this. So in a nutshell, it does actually make a really big deal to think about using GitHub as one of the ways that people will get a window into your capabilities. And it's really good to be very pragmatic about it and to make sure that you've, again, highlighted your pinned repositories, you have put your best foot forward, and you're also thinking about how people can look at your contributions in the last year, and also that when you do a README file, that README file really is a pleasant experience. Let's talk about Kaggle, which is a really common and popular data science website. What it does is it allows you to work on kernels and do competitions, and also it allows you to upload your own custom data sets. And you can also think about Kaggle as a way to show a profile of work that you do and actually build up a portfolio of different projects that you've worked on. So I'm going to show you a project that I've done recently where I've actually uploaded my own data set. So this is a data set that I collected myself. It took me quite some time to collect all the different pieces, and I called it Social Power NBA. And if you go ahead and click on that, what happened is that I uploaded several different files here, and you can see that it has a list of how many rows were in each file. This one, for example, has 163,000 rows and 5 columns. And then I also labeled each one of these things so that someone could go through here and understand all of the different attributes that they could use to create a machine learning model. And what's great about this style of uploading is that it also gives you a bunch of descriptive statistics, and you can actually toggle through here and do actually some exploratory data analysis just by looking through all of the uploaded data. Additionally, what you can do is you can then create a kernel based on essentially what you uploaded, and then this could be a type of a profile. So you actually get influence and also notoriety on Kaggle by uploading a custom data set that people are able to use and get a lot of value out of, and also you can get a lot of value out of getting the actual data set itself. So here's an example of a version of a Kaggle notebook that I uploaded just recently, and you can see the different explorations I do here. I do exploratory data analysis. I go through and I show what I think is important about this data set, but at the same time, other people have the ability to go through here and make their own version of it. So this is really a powerful way to share your results with other people. Build up your own data set, maybe collect it from different places on the internet, or do surveys, or however you've collected your own data set, and then B, go through and create a kernel based on the data set that you actually uploaded. And what's really powerful about that is that you actually get to kind of really expose your brand in 2 different ways. So you get to expose it by one, showing people that you know how to create interesting data sets, and that's one way you can get some notoriety. And a second is that you get to expose how you can actually do data science itself by actually going through and actually uploading your own kernel. So these are 2 really powerful ways to collaborate and also to show your own data science portfolio. Let's talk a little bit about Colab notebooks. We've gone into Colab quite a bit in all these tutorials, but I also want to talk about how Colab is a great tool to build your own data science portfolio. So here's a lesson, just a random lesson that I picked, and I'm going to take this lesson and I'm going to save it a copy in GitHub. Here we go. I'm going to pick a repository where I'd like that to be shown. Here's a copy right here, Python for Data Science. And you can see what it's going to do. It's going to create a commit message that says created using Colaboratory, and then it's going to create a link to a Colab notebook that someone can actually see. Let's go ahead and do that. And what's really powerful about this is that it really shows other people that look at this repository 2 things. One, they can visually look at the output of this notebook and get a great look at all the different things that I know, and it's a great portfolio builder, right? So they can see all the different capabilities that I have as a data scientist, but they also can go through and test it out. If they click on this link, they can actually go through and see, maybe visually they see that I can do some work, but they can actually literally use the project that I created. So this feedback loop is such a powerful way to share, really your portfolio. And again, what's really powerful about this is that you can create a whole series of different Colab notebooks that check into GitHub, and then you can actually go through here and start to build out a README file. So we talked about that. So if I go into my README file here, I can then start linking and say, Colab notebooks, my portfolio, right? And then from here, people could go through and you could specifically talk about some conclusion that you found in this Colab notebook and talk about how a particular problem is solved, or talk about how you have used deep learning or used AutoML or used some kind of advanced technique like cloud-based machine learning. These are all basically tools that you can use in your portfolio, and Colab is a huge part of exposing your brand to the world. Plotly is a really powerful interactive data visualization library that we've used throughout many of the lessons, but it also is a great portfolio building technology or website. Here's an example of a bunch of projects that I've actually uploaded to Plotly, and you can just do this from a command line view inside of Colab. And if I look at these different projects here, you can see that, for example, if we take this one, I can view that chart, and someone can actually look at the work that I created, and they can actually see that there's some conclusion that I've come up with that they may be interested in. And what's really great about this is that I can actually store all of these really rich data visualizations in one spot. Like, this shows, for example, a interactive 3D visualization that I created, and it really gives you as a data scientist the ability to highlight not only the technical side, which is something that you would show in Colab and or GitHub and maybe Kaggle, but also you could specifically get into showing people how you've been able to do really powerful interactive data visualization. And it's all something that you can build out as a profile. So you could have all types of different visualizations that you've created, anything from a 2D to a 3D to a scatter plot. And Plotly is really a powerful additional component to building your data science resume.
In this lesson, we'll look at case studies. You'll learn how to do applied data science work. You write unit tests with PyTest. You edit projects with Visual Studio Code. You learn to edit files with Vim. And you learn to use AutoML with Ludwig. You will also learn Scilern algorithms workflows. And finally, you learn about how to create recommendation engines. Let's get started.
One thing that comes up a lot for new data scientists is that they wonder about some of the software engineering best practices and what's important to ignore and what's important to actually focus on. Well, I'm going to talk about one aspect of software engineering that data scientists really should know about a little bit, and it's called PyTest, and it's a unit testing framework. So I have a repo called MyRepo. You can actually go to GitHub, Noah Gift, MyRepo, and you can actually take a look at this. But in general, this is just essentially a toy repo that I'm going to show a few different examples with. So if we go into this test directory, and that's really what tests are really about, is creating tests that actually go through and instrument your own logic. And we look at this test MyRepo. The really simple way to do testing is to import the module that you're going to test. And in this case, I say from MyRepo, import repo mod, and actually take a very small function here and I assert a true statement. So inside of this function that I've created in my library, it actually returns back 1. And what I do is I assert, once I make an instance of that function that I wrote, that it's actually true. And really that's it. This PyTest framework does all the work for me. So if I go back to the top here and I look at this make file that I created, I have inside of this make file a test command. And so the command here is, it says python-m pytest-coverage, and these are traditional settings for pytest. It goes through and it runs all the tests that are in this test directory. So I'm going to say make test, and this will actually run that. So if I do make test, it should go through, do test coverage, also go through and make sure that the logic is correct. And you can see that it says 100% coverage for one of the files and 64% for another, and actually everything passed correctly. Now let's go ahead and break it, and that's a great way to test your test here. So I'm going to go into myrepo.lib, which is really just a file that has a function inside. I'm going to go to myrepo, and I see there's a print name function, really simple. There's a fake data section, there's call data, so and there's also this my function. This my function here returns 1, right? So it's probably the simplest possible function that you can create. I'm going to make it return 2. If we go back here, and now if I go back up to the top level and I say make test, this will fail my unit test. And it'll fail because if you remember, we created this assertion that said, when I call that library and I make an instance of it, and I actually compare the result, it should be 1. In this case, we see that the assertion is incorrect. And this is a great way to test little bits of logic. So if you're doing some data engineering, for example, you may want to divide up little pieces that are really important and actually run these tests on those pieces of code. You can see how simple it is to go immediately see the results. So then if I want to go and I want to fix that, I can go back to that file here, and I'm going to go ahead and edit this. I'm going to make it return back 1. So here we go. I go back, make it return 1. Close the file, and then I go back and run make test, and then it'll actually go through and test that code. So PyTest is an incredibly powerful framework that takes just a really tiny amount of work to actually get set up and get running for your project. Another thing to point out is that I also can test my Jupyter notebook. And so inside of here, I actually have a notebook file. And one thing to point out is that if we look at this notebook file here, in my make file, this is where I've actually designed my test runner. You can see that it actually runs a plugin called NBVal. And what NBVal does is it actually executes cell by cell my Jupyter notebook. And this is also a really highly recommended way to control your project for if you're doing data science. So you do some testing around the libraries that you write. Again, these could be like, let's say, data engineering libraries, or maybe some custom logic around customer segmentation or k-means clustering. And then you also have some key notebooks that you go through and you run automatic testing on. And in a previous lesson, we had talked about this concept of if it's not automated, it's broken. And it really is the same with tests. Is it having some automated testing that works around your project is really an important aspect of quality control, and it'll actually bring you to the top level of being a data scientist. It's really going to separate you from other people. Another thing to point out is this lint section. So I'm going to say make lint here, and what that does is it runs this command pylint, and it actually goes through and checks all my code for syntactic errors. So this is, again, this concept of automation where it does a quality control pass. So if I go and I actually change one of these things, so we know that my repo right is being tested for both linting and also for logic. I'm going to go through this repo mod, and I'm actually going to change this. I'm going to just put some kind of a bug inside of here. I'm just going to say, some nonsensical logic inside of here. And then if I go back upside and I say make lint, you can see that it actually completely blows up all of my code. It actually can't import this module anymore because there's errors in it. There's invalid syntax, and it tells me exactly where that invalid syntax is. And so this is another thing that is incredibly powerful to do in your project. Why wouldn't you want to have automated quality control around not just the logic, the business logic, but also just the syntax? So if we go back here again, I go to that library, and I go ahead and I take that out, and now I go through and I run make lint. we can see that it actually goes through and cleans up that logic. So the takeaway here is that it is very important to know how to do this, and there is going to be a point where you may want to move some of your logic out of your notebook and also build it into a library. And PyLint and PyTest are incredibly powerful ways to make sure that you have a high quality data science repository. Another concept that comes up quite a bit in data science projects is, how do you edit a file? You may be in Colab Notebook or Jupyter Notebook working for years even, and then all of a sudden you've decided that you want to do a little bit more. You want to build a data engineering pipeline, or you want to build a production machine learning pipeline, and you have a whole bunch of code and you want to edit a tree full of code. Well, one of the ways to do that is to actually go for high-level tools. And so what we're going to cover here is actually how to use something called Visual Studio Code. It's probably the predominant editor in Python right now. It's made by Microsoft, although it's open source, and it has many new features that data scientists would really benefit from using. So the first thing I'm going to do is I'm going to source a virtual environment. So I say source tilde, the name of my virtual environment. Virtual environments are built into Python 3, and I'm going to go through here and I'm going to source it. Now that I've sourced it, I can actually launch Visual Studio Code inside of this environment. So I'm going to do that. So I'm going to say code dot. That goes and it fires up Visual Studio Code, and now you see it's launched here. And some of the really powerful things you can do with Visual Studio Code is you get a tree that you can actually scroll through here, and that alone is just an incredibly powerful tool. And I can see things like a YAML file, and this is something where I can actually look through and see all the different sections of the YAML file, and it's syntax awareness, so syntax highlighting. And we talked about how YAML files can be a great format to exchange data. Also, I can go through and I look at a makefile, right? It understands what a makefile is. I can go through and look at tests, and it actually goes through and it understands that this is actually a test. It will give me a complaint here that says PyLint's not installed. It'll give me the option to install PyLint. Now, in this case, though, I'm going to do something a little bit tricky. Is I'm going to say select linter. So if I go here and I actually ask which linter to use, I can actually go through and pick all these different styles of linters. I also can go to this section where it says Python 3.7, and I can actually pick which Python environment I want to run in. If you remember earlier, I had created this virtual environment. I don't have to use this virtual environment. I could use, let's say, Python 2.7 or Python 3.6 or even Python 3.7 here. I'm going to go ahead and, again, use this virtual environment that I set up. Once I do that, it actually will automatically inherit everything that this virtual environment has. So one of the things that it has here is that I have a requirements file where I've already loaded a lot of libraries. You can see I've installed PyTest, PyLint, Jupyter, Pandas, NBVal. So actually this should at this point know how to do syntax highlighting. So I'm going to go through and look at this command line tool I've created using an excellent command line tool framework called Click, and I'm going to show you how this could actually work. So if I go here and I say this is bad code equal dot, just kind of something that's nonsensical, right? That what'll happen here is that this will actually get flagged, and it'll know that this is an incorrect statement that's actually listed here. And so once I save it, it says PyLint invalid syntax. So this is a really powerful workflow that many newcomers to the Python language aren't aware of. And if you're writing a really large project or you're creating a data engineering pipeline, not having these tools is really going to put you at a disadvantage. So it's important to think about, all the power that you can get by using something like Visual Studio Code. And another thing you can do that's really powerful is you can even go in and open up a new terminal, and then it'll actually open it and source this virtual environment because I've told it that this is the Python interpreter I want to use. And so if I go through here and I say which Python, you can see it's using the Python in my virtual environment. I can even open up an IPython window, and then from this IPython window, I can go in and I can import the library code that I wrote. So I can say, import my repo lib right here, and then I can say my repo lib dot, and I can actually inspect things that are inside of there like repo mod. dot, and I can actually go through and get dot completion. So these are really powerful aspects of having an editor that a lot of times you may not think about when you're using just a Colab notebook, but it's really an incredible tool that you should take a look at. One other thing I want to close with is that you can also do a split tab here as well. And where that comes in handy is when you're doing unit testing, which is hopefully something I've convinced you is important. I could go through and I could look in one hand at my code, and at the other hand, I could go through here and I could look at my test, right? So I could actually kind of have those, side by side, and I could actually be writing my test and looking at my source code at the same time. So let's look at one more final aspect of Visual Studio Code that's a really powerful aspect. So if I go here and I look at this command palette, what this does, it actually allows me to do many new things like install a new extension, select the Python interpreter. So it really is the place where you can go through and you can actually add more power to Visual Studio Code. So if I go through here and I look at all these extensions, you can see it has things like Azure integration, Terraform integration, Kubernetes integration, Docker integration, really powerful features that all show up and allow you to do new and powerful things. Give Visual Studio Code a try. I promise I don't have stock in Microsoft, but I think it will really help you be more professional when you're doing projects in Python.
Now let's take a quick look at a widely available text editor called Vim or VI. Up till now, we've been mostly working in Colab, which is a great environment for doing data science. And you've seen a bit of Visual Studio as well, which is a great integrated development environment. But there may come a time where you need to fix some code on the fly on a server, and you won't have access to those environments. Any Linux or Unix-based server, you will have access to Vim. So I'm going to give you a quick introduction to how to edit a file using this text editor. So you can open a file. You see here a bash command line, and we can see the files that are available in this directory. We'll go ahead and open one of them. Let's see, using Vim. Unlike word processors you've used before, or even other integrated development environments, editing in text in Vim is a different experience. There's essentially an idea of modes in Vim. And so the normal mode, which is the mode it opens up in, allows you to navigate around the file. When you navigate around the file, you'll do this using the H, J, K, and L keys. So J is down, K is up, L is to the right, and H is to the left. So this is the basic navigation around the file. If you want to change text, there's a number of ways to do it, but the most basic way is to enter into insert mode. You do this by hitting the I key, and you can see at the bottom it says insert. Now at this point I can begin typing, or I can delete something, or do whatever else I need to do to the file. You will undo your last changes if you're in normal mode. To get back to normal mode, press the escape key. So these two modes are the basic things you need to know to edit any file. You use escape to go to the normal mode, and use I to get into the insert mode. There's other ways to go back and forth, but those are the two basic ways. The other thing you need to know is the command mode. And to get to that, press the colon, and then you can do a command. The first command you probably want to know is how to save a file, and that's W. And the other command you'll probably need to know very quickly is how to quit a file, and that's Q. So that's the basics of using Vim. It's a very powerful and complex tool that you can dig in much deeper, and there's a lot of more functionality. But being able to open a file, edit it, and then save it should at least help you out if you're in an emergency out on a server and you need to get something done.
Ludwig is an open source AutoML system that's out of Google, and you can see from this project URL, it's available in GitHub. So let's take a look at what you can do with Ludwig. To start with, you'll need to do some installations in Colab Notebook. You can see pip install, upgrade NumPy. upgrade sklearn image, install Ludwig, and also do a 𝑠paCy download as well. So once we've gone ahead and done that, you'll actually have to restart your runtime if you're doing this in Colab Notebook. So some basic ideas with Ludwig are that it is an AutoML system that is training your model, is doing a prediction for your model, and it also is able to do work with binary, numerical, categorical, set, bag, sequence, text, time series, and image data. So here's an example of some classification that we're going to do. And what I first start out with is I download a Amazon book listing of about 50,000 rows. And I also download a model definition file that I created separately. So let's go ahead and do those. Here we go. And then once I've downloaded those files, I go ahead and I look at this ingest process here, and I see that there's an Amazon serial number, a file name, an image URL, a title, and this title is going to be used to predict the category here. So like children's books, Christian books, sports and outdoors. And then I go ahead and I write this out to my local Colab ecosystem. Next, what I do is I go ahead and I do an exploratory data analysis where I look at the columns, I go ahead and I look at shapes. We see, in fact, that there are 7 features and there's 51,000 rows. And now what I do is I also just take a look visually here by using the head Unix operation so I can see all of these different attributes. Now, if I look at the model definition file here we go, we can see that the name here, title, again, the title is included right here. I call it text type. I use an encoder. I use the parallel CNN, so it's going to be using TensorFlow deep learning to actually do this classification, and I do it at the level of word. I then output the features. Here I say the name is going to be the category, and again, here we go. This is that column, and I'm going to make it the type of category. So it's going to do a multi-class classification. Now what I do is I run Ludwig, and Ludwig can be run inside of Colab Notebook or a Unix shell. You can see here I'd say Ludwig experiment --data CSV, and then I pass in this CSV file that has the 50,000 plus rows. I then give it that model definition file right above here, and then that's all we need. So now once I go ahead and I run this, you can see that it actually starts printing out all these values like the true positive rate, the accuracy for each one of these classes. So it gives me a lot of really valuable information that's, again, I didn't have to do any of this stuff. It's all available via this Ludwig framework. Another thing as well is you can see there's, this is the 10th training run here, and I can actually see the accuracy as well. So you can see that I have training, validation, and test accuracy, and also the loss as well. So a really powerful deep learning framework that automatically it actually takes advantage of the GPU as well. So if I go here and I say change runtime type, you can see this was actually using a CUDA-based GPU. Now, if I go down here and I look at the end of this section here, you can see that the children's book accuracy also includes F1 score, fallout, false discovery rate. So in a nutshell, this Ludwig environment is a great framework to do AutoML. It could massively speed up your ability to create models that go into production. Scikit-learn has a really valuable algorithm cheat sheet that I'm going to walk through right now. So it looks like this, and what sklearn model selection does is it allows you to start at the beginning and really walk through what model you would like to select. So if I go here and I say I have under 50,000 examples, it's going to say get more data. If I want to predict a value, it's going to say, do you have labeled data, or do you want to produce a quantity? And it's going to pick down a different tree. So in this example, if I have over 100,000 rows, it's going to tell me to try the linear SVC algorithm. And then I can go through and walk through other methods. Likewise, if I'm going to work with something that doesn't have labeled data, then I'm going to go into an unsupervised example here, and I'm going to use things like k-means clustering or mean shift. Also, if we're looking at things where, let's say it's highly dimensional data, you can see that it'll go through here and actually give us some examples of dimensionality reduction that we can do. So in a nutshell, this is really a recommended way to get started with scikit-learn. And if you haven't had a chance to play around with it, it really is a helpful way to give you a guide. So on that same note, I also wanted to talk about model explainability with SHAP. And what this is it's a unified approach to explain the output of any machine learning model. And let's go ahead and see how you would install that. I just do a pip install SHAP. Here we go. Once that's actually installed, to use it, you would again install scikit-learn and then actually just use import shap and then shap.init.js. And what that does is it actually loads inside of a Colab notebook the actual JavaScript that does the interpretation. Next, what I do is I go and I load this census data, and you can see it's a really similar scikit-learn type process. I go through here, I download the data set, I then go ahead and I split the data up into a different test size, and I use this random state variable so that I can repeat the runs. There we go. And now if I look at the training shape, we can see there's 26,000 observations, there's 12 features, and we're going to be predicting, again, this Y train shape. Now what I do is I go and I train a k-nearest neighbor classifier. Very similar scikit-learn process. I go through here and I train that. Again, here's the train data, here's the Y. I go ahead and I fit this, and now let's explain what's happening here. So if I go into this Lambda model here, I go and I see that I explain the SHEP values, I plot it here, and then what happens is at the very end, we can see that these are negative associations, positive associations, and you can see that the lower the significance, so in this case, the education plays a huge role, and then as we go down here, capital gains plays a smaller role, but on a negative level, you can see the age and also the work class right here, state government. So you can see that these are the different features that add both positive and negative predictive value, and they're explained right inside of this visualization. So this is another way to really get into the details of a model and start to learn what model is the best model. So between the algorithm cheat sheet and also SHAP, these are great ways to really learn about what's the best algorithm to use. Let's get into recommendations. So one of the things that's great about the scikit-learn ecosystem is that there is a library that allows you to really experiment with recommendations. Here's an example of how I do it inside of Colab Notebook. I install this surprise recommendations library, pip install, and then what I do next is I go and I actually run the initial setup here, which loads the data set, which is this 100,000 movie lens open source data set. I use the SVD algorithm, and then I do a cross validation using that data, the algorithm, and also I want to measure root mean squared error and mean absolute error. And I have 5 actual cross validation folds. So here we go. We have fold 1, fold 2, fold 3, fold 5, mean, standard deviation. And we can see that the mean root mean squared error is 0.93. And we can see the fit time, test time. So in a nutshell, it's a great way to play around with doing a machine learning based recommendation engine with the ability to measure the error and also accuracy. Now, intuitively, I wanted to bring up an example of how recommendation systems actually work. So this is a really simple recommendation engine that I hand coded at one point. It's called Tanimano coefficient. And what it does is it actually just measures the similarity between two lists. This is really similar to like a Pearson similarity score. And you can see here that whatever's different between the two, there's only 11% similarity. So what I typically would do is find maybe a closer list, and these could be products or these could be users, and I want to find a very similar list and then find what they have in their list and then recommend that thing to the other list. And really, this is a great way to intuitively think about recommendation engines. Next, I want to go into a real-world example here of collaborative filtering and how to explore it. So first, import the surprise framework again. Here's a helper function that really is just some boilerplate code that goes through and cleans up this example a little bit. And now here's the fun stuff is we take that data and we use this Pearson baseline, again, a kind of a similarity score, and we fit this to an algorithm using, again, that built-in 100,000 row data set. We go through here, we train it, there we go, computing the Pearson similarity matrix. And now we can go through and we can actually map things inside of here. So what we want to do is we actually want to figure out who's a Toy Story neighbor. So in this example, again, using the same kind of intuition that we showed earlier, I want to find out who's similar to Toy Story. So who are the neighbors that we can actually recommend to people. So if I go ahead and I click this, you'll see that Beauty and the Beast, Raiders of the Lost Ark, That Thing You Do, Lion King, these are all similar movies that if someone was a fan of Toy Story, there's a very high likelihood they would also be a fan of one of these other movies. So this recommendation engine, Surprise, is a great way to play around with recommendations without you having to do a ton of work yourself. Hope you enjoy. Thank you.